Your MC.
Hello, everyone. Welcome to Dev Day. It's a great honor to be your MC this morning. My name is Steve Schonebeek, and I'm the business developer at Trident One. I hope you all came well rested. We have a packed schedule for you. But first, a word from our head of product at Solana. Please make some noise for Solomon.
Thank you, thank you. Thanks. Hey everyone, hope you're having a great second day at Breakpoint early in the morning. I'm Solomon. I'm a product engineer at the Solana Foundation, and I'm super excited to bring to you day 2 at the dev stage. This is my third Breakpoint. It's been really great to walk around and see so many new faces, so many familiar ones, and to see all of these ecosystem activations around the venue. There's some really solid ones that are very fun, unique, and quirky, so please make sure to go through the entire venue and see everything that's happening around. For today, I wanted to do a quick intro on why we're here in the first place, and then go through some logistics for the rest of the day. So a year prior, we used to have a lot of developer-focused events called hacker houses. Hacker houses were these sort of event venues maintained by the Solana Foundation to allow developers from across the world to congregate in certain areas to dive deep into certain technical topics and applications. And unfortunately, hackathons do exist, but hacker houses in their old form do not. And we got a lot of feedback from many developers in the ecosystem, basically saying, hey, we really want more serendipity. We want more of these events to talk about what we actually care about, which are these deep technical topics that typically you won't find at these events where it's mainly products, marketing, sales, and BD. And so we thought really hard. We didn't want to basically recreate what we had in the past, but we wanted to make sure that no matter where we're showing up across the world, that we would still have these events that are tailored towards the audience that they should be for. And so beginning of the year, in May, we actually had the first version of a new type of event called Accelerate. Accelerate was during May in sunny New York. And we basically wanted to recreate a new type of event that was at the time mostly focused on finance, policy, and regulation, but we also wanted to have a separate event primarily for tech. And so we had this week-long event, and at the beginning we had a very specific event for the developers, which was called Scale or Die. And Scale or Die was my baby. It was a really awesome event, and a lot of people had really, really great things to say. The outcomes were very clear. We wanted all the developers in one place to dive deep into really important ideas across core dev, across security, across infrastructure, and we did exactly that. We actually got a lot of really, really rave reviews. Developers and teams would come up to me and say, hey, this was one of the best events I've ever been to because they were able to congregate around specific topics that only mattered to them. And so as a result, we're like, okay, well, we should have developer events at every venue that we're showing up at. And so here at the Dev Day at Breakpoint, we wanted to basically reinvigorate the developer community and make sure that we had talking points and an event for you guys. And so today we're going to have a lot of really awesome talks across security, across infrastructure. We're going to have a really interesting block with Firedancer called One Firedancer, where they'll talk about Firedancer on mainnet and accruing more stake. We'll have Anza have their own block of talks, primarily focused on performance and IBRL at all costs. And then we'll have some things like Anchor and 1.0 and some other pieces across the stage. So I'm really excited to bring the Dev Day to you. For logistics, all talks today are actually only 10 minutes or 15-minute talks. Usually at dev stages, we try not to do fireside chats or panels. We want to get deep into the actual content and make sure that people are learning net new things and are sort of getting new information that they usually wouldn't have. It's available for everyone. It'll be live streamed and recorded, and so I'm really excited to have this developer-focused day to make sure that we're all reinvigorating the tech, and next year we'll focus on developers and distribution. Thank you.
Thank you, Solomon. All right, to kick things off straight away, please put your hands together for the CEO of Chorus One, which is one of the leading staking solutions for institutions. Give a big round of applause for Brian Crane.
How do you change the slides? Is there a... Thank you. Cool. Well, thanks so much for coming. I appreciate you being here. I think there's some competition somewhere else for this talk, so thank you so much. So yeah, so the Solana vision, right, is basically to create these internet capital markets where you can have people from all over the world create applications, transact with each other, potentially accommodate all kinds of economic activity. But for that to happen, right, the network underneath also needs to perform at a certain level. So today I want to look at a bit where is Solana right now in terms of its performance and capacities, and what are the main changes that are coming up that really will get this network to the place where it's sort of fit for the Solana vision. So yeah, briefly about ourselves. So we've been deeply involved in Solana since the very beginning. Met Toli and Raj in like 2018, invested in Solana. We were there at the very first testnets. We were Genesis Validator. Helped also patch a bunch of vulnerabilities before mainnet, including one that allowed someone to mint lots of Solana. We built the first liquid staking solution on Solana that didn't end up surviving, but we did a bunch of the first MEV research. And today we run a whole bunch of different validators, and we do a lot of quantitative experiments as well, where we measure performance and compare different configurations, and we'll talk a bit about that. So first of all, high level, where is Solana today? So we have seen Solana really improve tremendously in the last years. Even from the beginning, Solana had these ideas of 400 millisecond block times, but it wasn't the reality for years. It really was like 600 milliseconds, 500 milliseconds, and it took years to get us to the point where actually the network, if you look at this year, was really consistently below those 400 millisecond target. So tremendous improvement on that side. We've also had skip rate, right? In the past, we had a lot of issues with stability, blocks being skipped, I mean, downtime as well. So that has gotten way better, and today, skipping blocks has become a rare event. And of course, Solana has consistently high economic activity, a lot of transactions. So I think today it's around 400 transactions from users, right, per block. And it's definitely probably the most used of all of the blockchains in terms of economic activity happening. But there's challenges as well. So at the moment, right, the economic activity on Solana is at the low point in the last 2 years. So MEV and priority fees are pretty low. You can see this chart here. And of course, we had a crazy boom earlier this year. Sort of with the whole meme coins, Trump, there was an enormous amount, like the most ever, but now it's retrieved a lot. And that creates a lot of challenges, including pressure on validator earnings and, yeah. And one of the most interesting things happening right now is that we're seeing this explosion of custom schedulers. So maybe it's worth talking a little bit about what that is and why it matters. So if a validator is up there and producing a block, they have a certain amount of time and they receive lots of transactions, and in that time they can process these transactions. And they can do this in different ways. But in the past, nobody really did that. There was just a default software and it processed things in one way. But today we are seeing a sort of divergence in different ways. So we see here, like at the top one, that's the default client, that sort of processes things at the beginning as quickly as possible, and then it sort of tails off. But there's been other ones, for example, that will try to wait and then process all of them in the end, which can generate more revenues. Or there's at the bottom, you can see this is the Jito BAM one that tries to have a regular cadence and basically process things at small ticks throughout the block. So we see these different things, which is interesting because it gives a way to differentiate and create higher APY, but at the same time it creates unpredictability for application developers. But Solana's culture has always been one of radical innovation and just reinventing itself and pushing the limits. And despite all of the success of Solana, the ultimate vision is still far away, and the network is also still far away from being able to accommodate that vision. And so if you look at actually a lot of the roadmap today of Solana, it's very ambitious, and it's really completely changing how Solana works. And so I'm going to talk a bit about these changes, and I think it's going to be tremendously interesting how that's going to play out. And it's going to have very big implications for validators, for application developers, for users, and hopefully for Solana holders, because if it makes the whole thing much more successful. So a few of the main changes coming up. One is Alpenglow. So Alpenglow is a complete rewrite of the consensus algorithm, and it will reduce the time to finality by a lot. And Alpenglow also kind of facilitates then decreasing the slot time. And decreasing slot time has some benefits, and that should reduce MEV a bit, especially as a percentage of the overall trading volume and activity. So that could be a positive change. And another one, which I don't know how many people are aware of that, but today validators, they have to send transactions to vote on the state of the chain, and they have to pay fees for that. And so if you're small, and there's like a fixed cost of about 1 Solana a day, and if you're a big validator, then you basically get fees from all the other validators voting on the chain. So it's a bit of a weird thing, right? The small ones are paying to the big ones. It really doesn't make any sense. So that is also something that's going away with Alpenglow, where validators will no longer have to pay fees for their votes transactions. So that's one change. 00 is another one. 00 is basically trying to create this high-performance fiber network to replace the internet routing. We recently ran an experiment with this where we sort of tested how well it worked. It helped on the low, far away peers to reduce latency. On the short ones, not yet, although I think they are working on changes there. But I think the thing with 00 really will be to give faster access to block space. I think especially for RPCs, right? You could have better RPCs so that you can read and write to the blockchain faster. But let's now talk about probably the two most important changes that are coming and also the most complicated ones. So one is proposer-builder separation, or I would say there's a question whether that's coming and to what extent. But basically, so far in Solana, right, we've had that the validators would get the transactions, create the blocks, and then they would also engage in consensus to basically create the valid chain. But in Ethereum, for example, it's been working differently for years, where you have one party that gets the transactions, creates the blocks, and then the validators basically receive different block proposals from the builders, and they choose whichever one pays the most. So you have this separation of the block builder and the validator. So that has pros and cons, but there are attempts to creating something like that on Solana. So first of all, Jito has created BAM, and BAM basically has a sort of, it's also trying to address this earlier issue where you have different schedulers, right? So they have one scheduler that processes transaction in a specific way and that runs in a trusted execution environment, so somebody can verify that it's really running like that. And then as a validator, you would just receive the blocks from these BAM nodes. There is a pros and cons to this, right? First of all, it would standardize how these BAM blocks work. So that might be better for someone who wants to create a DEX or some financial applications on it. At the same time, it will reduce competition if it really succeeds, reduce the role of the validators. It's a big open question. It also creates a different kind of centralization because now you have a few nodes that basically will produce all the blocks. And the big question here is, what's the threshold at which BAM even starts working? Because if 10% of nodes use BAM, it's probably pretty, doesn't really make a difference. So you might need to get to a very high percentage of the network adopting BAM for it to bring benefits. Then there's also a harmonic. Now, not so much is known about harmonic, but I think what harmonic is trying to do is more like what is the case on Ethereum, where you can have different builders, they compete with each other, they can have different methods, propose a block, and then a validator can choose which blocks to take. So that might have the advantage that there's more innovation, more diversity. But it also means probably less predictability and probably the sort of profit maximizing schedulers would win there, which has its pros and cons. So that's proposer-builder separation. But then I think actually the really biggest change is going to be multiple concurrent proposers. I think Max Resnick is doing a talk about this later, but that's really, I think, one of the most ambitious changes in all of blockchain sort of architecture. And the idea here is that instead of having one leader that processes transaction, creates a block, you have many of them. How many TBD? Maybe a few, 15, 20, 100 I've heard, that do it all at the same time. And they basically create partial blocks at the same time. And that will have some really profound implication because all of these MEV games, the scheduling thing we saw earlier, it all depends on waiting and taking some time and then doing something. But if 10 people all try to create a block at the same time, they get the same transaction, and then whoever includes it first sort of gets the rewards, it makes it very difficult to do that. So I think this will completely change the MEV landscape. Even these previous things like BAM, harmonic, they wouldn't work in the same way. It will really totally change things, but I think in a good way. I think there will be a lot of upsides coming, but of course it's early, and the second order effect of this is still unclear. I think the latest I heard is maybe like early 2027 or something that this could come. And the other thing is also cool is like, okay, if you have lots of leaders across the world, then if you send a transaction there, you get a quick confirmation. It could sort of reduce latency of the whole network. So those are, I think, the most important changes. So I think if those things happen, really, we'll have a completely different network. It will look completely different. And it might actually be the kind of network that's now able to accommodate a massive amount of economic activity, that's able to have also trading and exchanges work on Solana at a really high level of performance. And then it can live up to the Internet Capital Markets vision. So thanks so much.
All right, thanks. Thank you, Brian. Our next talk is about maintaining safety while using Pinocchio, which is the new lightweight zero-dependency Rust library. Who here has used Pinocchio? Please, yeah, small round of applause if you used it. It makes it a lot easier or much lighter to build on Solana. So please give it up for the expert on this subject, Daniel Cunning.
Wonderful, thank you. Hello everyone, my name is Daniel Cumming and I'm here from Runtime Verification to talk to you about Compass, which we're using to prove the equivalence of the Solana token program with Pinocchio as the backend. I've got a lot to get through, so I'm going to probably talk fast, so buckle up, everyone. The Solana token program is the topic of our talk. You might know that at the moment this is using SPL token as its backend, but shortly it will be upgraded to using P token. The difference between the two is that the SPL token is using the Solana SDK, whereas the P token is using the Pinocchio library. The benefits of which is that Pinocchio is more efficient, and so P token is going to be more efficient. But while we want the change to be an increase in efficiency, we do not want there to be a change in behavior. We still want to have the Solana token program that we have come to know and love. So we are in a reality where there's two programs which are essentially trying to do the same thing, but they are slightly different. We do want there to be a difference in efficiency. So the intersection of which is the idea of what ought to be the Solana token program. So we can be explicit and talk about what this is in particular. And what we want to be the same is all of the logic of the program should be, as we expect, the minting, the transferring, the burning, the effects of which should be the same if we do the upgrade to P token. And we want to know that the errors are happening under the same conditions and that we get the same error code. We don't want there to be any new behaviors or any new restrictions when we perform the update. And so that leaves what we want to be different is simply that it's more efficient. That's what we want, lower CUs. How are we going to check this? Well, in determining equivalence between two programs, we have a few different options. In increasing order of confidence, the first thing that we might do is a manual review. So an expert would look at both programs and try and determine that they are in fact doing the same thing. This was performed by Neodyme and Zelic. They did a fantastic job. Kudos to them. And we would still want more confidence that the programs are going to behave the same way, so we might do differential testing. This is where we have a test suite. We run both programs through the same test suite, and we check, do we get the same results for those inputs? The fuzzing for this was done by Neodyme as part of the engagement that I spoke of earlier, and we also are running the integration and Mollusk test suites as we write our specifications. We're writing specifications because the next highest confidence, I guess, that we can get is formal verification that the two programs are equivalent. So using the power of mathematics, we can prove that they're going to do the same thing. This is the approach that we're taking. And I'll describe to you what one of these proofs is. So a formal proof of code correction, I have a diagram here to explain what that is. In the middle, we have the proof engine. This is what Compass would do in this case. And it can output we can be proved correct or it can be proved incorrect. It needs some input, which is on the left-hand side, And there I have color-coded yellow is the implementation. This is the code that Anza wrote, which is what we would actually have executing when we perform a transaction. And the specification is split into a precondition and a postcondition. The precondition is what is the generalized valid initial state that must hold in order for us to call the implementation. And the postcondition is the guarantee of what must hold if we do call that implementation and we satisfy the precondition. So this is where we know what the effects ought to be of the program, and we check that that did in fact, or that will in fact happen for all inputs. So bringing this to P token, what we have for the implementation in the yellow there is the P token program. This is written in Rust by Anza. And then the specification, the precondition and the postcondition, this is written by runtime verification. This is where we assume the valid initial state and we assert the valid final state. All of this gets bundled up and put into the Compass prover, which is the step in the middle, the proof engine. This is written in our K framework. And from there, we can prove that the implementation is satisfying the specification, in which case we're happy, we can go party. If it fails, we might cry. We'll find out. But we're going to do the partying. It's going to work. That's not enough, though. We also need to do this for SPL token. So we need to do the same proof again. Now the implementation, the yellow box there, has changed to have SPL token program. And we use the same specification. So by proving both, we end up in this, the same specification is going to prove both implementations. So we do two proofs, and then we use the cross product of the proofs, which could be formatted slightly better, I think. But anyway, you get the idea. We want both proofs to pass. And what that is communicating is that both SPL token and P token are in that intersection that we spoke about, where we have proved that they are correct implementations for what the Solana program ought to do. And by nature of them both being correct implementations, we can assert that they are equivalent modulo that specification. So that's our definition of correctness. To give you some idea of what this looks like in particular, on the left-hand side, this is a proof harness that we would prove an instructions behavior correct with. So using the same color coding, the blue box up the top, that is the precondition. This is where we're assuming the valid initial state. And the yellow box, this is the instruction that Anza wrote that is actually going to process mint2. So this is for the example mint2. And then afterwards, we need to assert, did we error under the conditions that we expected? Did we get the correct error code? And also, if we didn't error and we're in the success case, did the supply get increased? Did the destination account receive their tokens? On the right-hand side is a graphical representation of what this proof sort of looks like. Of course, it ends up actually being in some machine language, but we can think of it as it's an exploration of all possible states. To give a little bit more insight into what's going on, the harness on the left-hand side, what we're doing in particular is we're setting up the inputs of the particular instruction symbolically. So mint2 takes some account infos and some instruction data. When you're performing a test, you will instantiate these with concrete values, and you will run that test and you will get some information about those specific values that you tested. We want to represent these values symbolically so we can express all paths and have a higher degree of confidence. That's why in the Pinocchio account there, we have question mark borrow for the borrow state. Is it a signer? Is it writable? Is it executable? We need to think of the same idea of the cross product. What are all the options together? Same thing for the input data. We want to look at all of the bytes symbolically. From there, we also know that in order to mint, we need a mint, and we need a destination account to receive the tokens. We also represent these, the mint and the destination account symbolically. So the authority for the mint, the supply, the decimals, whether or not it's initialized, the freeze authority, all of these are represented symbolically. Once we've established our initial symbolic state, we can start traversing a graph and looking at all of the potential. So one thing that we might start with is it true, or is it false, that the token mint is initialized or uninitialized? We need to look at both branches, and so straight away we have a branching condition. And then the next thing we might look at is the destination account within the range of less than or equal to. And so this is saying the only valid states that we would expect is initialized, uninitialized, or frozen. But we also need to consider that we're in an invalid state. And so you can see that if you do this for everything that might change, you get a massive tree of everything that could possibly happen. Once you go down to the end along your branches, we want to be able to look at the path condition and decide what ought on this branch the result be for this to be a correct implementation of the Solana token program. And so this is where we assert, are we getting the error code that we expect, or are we getting the state update that we expect? All of that needs to be done for each instruction, and also sometimes the instructions behave differently under different conditions. And so it's a repeated process that needs to be done across 27 instruction proofs and 20 multi-sig proofs. But then we multiply that by 2 because we got P token and SPL token. So there ends up being quite a lot of proofs that need to be done. And in order to do them, we need to write out a sound semantics of Rust so that the Compass prover is able to do these proofs. So this was a lot of work. And originally, for the first cut, these proofs were running on the order of over 5 hours each. So this is not a great feedback time to get for anything in engineering. We've reduced that down to about 10 to 20 minutes a run for most of these proofs, and we expect that we're going to get them more efficient shortly. That's everything that I have for you today. I thought I'd give you a flavor of what these proofs are doing. Thank you very much for your time.
Thank you, Daniel, for keeping us safe. Our next speaker is the founder of 7 Labs. 7 Labs is a Solana engineering company that helps other companies materialize their vision for their products on Solana. Here to talk about carbon. Please put your hands together for Kellyan Vitre.
Hi guys, I'm Kellyan, co-founder at 7 Labs. Today I'm going to be talking about Carbon, the data pipeline for Solana. So Carbon is a Rust framework to build indexes on Solana. Just for more context, we've been a dev shop for about 2 years on Solana, and about a year ago we realized that a lot of teams were basically just rewriting the same pieces of code. So for sourcing data, be it historical or real-time data, for decoding it from their IDL, and also for processing it, so like storing it or triggering workflows. So that's when we started actually building Carbon, and the goal was to have a single pipeline that is modular and that you can just plug things into. So just so you get a bit of an understanding of how you actually compose the Carbon pipeline, you can plug in any data source, and here we actually support most of the ways in the ecosystem to get data. You can then attach decoders for instructions and accounts. This will directly use your IDL. And then you can add processors like for Postgres storage, or could be really anything. And then you just run the pipeline end to end. So as you can see in the code, you have a simple builder pattern. You can choose your source, then add instruction and account pipes, and you have your indexer ready to run. So let's get into each of the components a bit more deeply. The first one is data sources, as I mentioned. So it's a component that sends account and transactions into your pipeline. And so it's modular, so it's a trait. That means if you have a custom endpoint from an infra provider, or if you have a local dump of data, you're able to simply ingest it into your pipeline by implementing that trait. But of course, for most people, they don't want to do that. They want to just use something that's already implemented, because there are standard ways to actually get data to index. For real-time data, that would be gRPC, and for historical data, there's been a lot of teams pushing it this year. So as the ecosystem grows, we actually maintain and publish a lot of different crates for data sources. So I think this year there's been a lot of teams pushing historical data, on the OSS side, there's been Triton and Anza that have been building Old Faithful, the archive, and Jetstreamer. So we've integrated that. That means you can pretty much just for free stream historical transactions to your Carbon pipeline. And that's at very high speed. So that's a good one. And then on the vendor side of things, you have Helios that has released like get transactions for address as a new RPC endpoint. And so these are all methods that you can directly plug into Carbon, and you'll get the data inside your pipeline. So that's an example of how you would do it. This would be for the Jetstreamer data source. So as you can see, you just choose your slot range, you choose your filters, and you're able to add it to your pipeline. Would work the same way with other data sources. You'd simply import another crate. So then at that point, you have all of your raw data flowing inside your pipeline. And so you need then to make sense of it, because that is the main point of Carbon, actually. It's getting all of your updates and then doing what you want with them. So here, again, you have two traits inside the framework, but you don't really have to implement them. You could implement them if you want a custom deserialization logic, pretty much. What you can do, and what most people should do, is actually use the CLI. So the CLI works with any IDL. So we support Anchor and Conam IDLs, and it will basically generate the whole decoder implementation from that IDL. That means you can then just import the code that's been generated and add it as an instruction or account pipe, and you'll have all of your decoded account or instruction updates for your program directly flowing to your pipeline. Once you've done that, you just need to do whatever you want to do with that data, and that is the part that actually you will spend most times writing when you're using Carbon. So this is also a trait that you can implement, and you can do whatever you want inside of it. The good thing is basically you get all of your decoded updates, and you can use it. So here you have a logger implementation as an example. So what this would do is actually load the decoded updates, and it would also log some transaction metadata. So you have access to the whole instruction or account update, all of the metadata that you need, and most importantly, your decoded type. So something that's cool actually about the CLI is if you generate your decoder through the CLI from your IDL, you have a Postgres feature that is already implemented inside the generated crate. And so if you enable it, you'll be able to directly use our Postgres account or instruction processor, and you'll be able basically in a few lines of code to have a full index of all of your accounts and instructions in like a few lines of code inside Postgres. So here, you just use the migrations inside of the generated crate to generate your tables, and then write this pipeline, and you'll have pretty much everything running. You just need like a gRPC connection to whatever infra provider. So this wraps it up for how you would actually use Carbon, and I recommend that you guys also use the scaffold command of the CLI to try to generate a project and like play with it. But it's really simple to use, and after about a year experimenting with the API of the library, we're going to go to V1. So we're going to have a stable API across all core crates. We're going to follow a semantic versioning finally. We've had a performance update with like more than 5x in raw pipeline throughput, which is huge for historical backfilling, because you're able to basically have a Jetstreamer data source and have between like around 100K that 100K TPS that flows through your pipeline, and that you then just decode and index. So it's actually very quick to do historical backfills with V1 now. We've also reworked metrics. We already had a metric system, and it was basically fully extensible, which means you can record any metric that you want with Prometheus, and you can also just log them. But we've made it like way faster, so this is going to be released. And then we are finally going to release a documentation site with guides, examples, best practices, and like a full reference of the framework. So this will help everyone get into it. And this V1 will be the foundation for everything that comes next. So we have more processors for ClickHouse Kafka that are going to be generated off of the CLI command. So it's always gated behind features, meaning most people are just going to want to have their custom logic, so you can have it. We're going to build speed optimized decoders for like the most important programs, so things like SPL token. I mean, probably most SPL programs actually, Solana program library programs. We're also going to build version decoding afterwards, which means you can, based on the version of your IDL, decode things differently based on different slot ranges. And we also have in plans to build language-agnostic gRPC streams for teams that want to be indexing in other languages than Rust, because right now you can only index with Rust. So now is a great time if you want to raise issues or if you have any PR that you want to open on the repo, because we're actually currently in the final push to release V1. We've reached more than 500 stars on GitHub recently, so wanted to thank all of our contributors, and thanks for listening.
Thank you, Kellyanne, and thank you all for joining us at the dev stage. So a little round of applause for yourself. Is everyone still feeling energized? All right. So I'm not sure if there's any EVM developers in the room, but this next talk is for you, because I'm going to welcome on stage the CEO of Neon Labs. So if you're an EVM developer that is looking to access Solana speed, liquidity, and users, please put your hands together for Ivan.
Pleasure to be here, and little bit of a surprise. This is actually my first breakpoint, and I'm coming to it as a speaker. I'm actually one of the people that Solana, through Neon Labs and Neon EVM, was able to convert from Ethereum space to Solana, and I'll try to explain why in a couple of sentences. I was a part of Ethereum from basically early 2016. I was one of the people in charge of Polygon Edge, which used to be Polygon's EVM client. So I brought over 300 different blockchain use cases to Polygon Edge as a client, back then. And after that, for the last 2 years, up until recently, when I became the CEO of Neon, I was in charge of strategy at Tenderly and brought, Tenderly infrastructure and tooling to all of the EVM developers on over 100 EVM-based networks, mostly L2s. That's actually how I first heard about Neon EVM and started being interested, in it a little bit more. And a couple of months later, what happened was I became the CEO of the company because of some interesting reasons. I think that it's extremely interesting and gratifying, what happened with Neon EVM over time, because when you look at it from the initial perspective, the main goal of Neon EVM when it started in late 2021 was that we are actually able to bring EVM developers, that know how to write Solidity, to Solana as an ecosystem, and to let them have their then existing dApps there. Didn't work out fully well. I would say the main reason why is that the main blocker for these people was actually not to learn Rust instead of Solidity. There are many constraints in Solana, that make you change your EVM application business logic if you actually want it to run on Solana. And this is something where Neon EVM tried to do it through a then novel concept of network extensions. So we built an EVM inside of the SVM and said, let's try, to do this in the best possible way. However, the amount of those things that make Solana able to provide us with internet capital markets and to be a Nasdaq on-chain makes it also very hard to make this fully possible. And when I look at it today, this became also the reason why some people are now using, Hyperliquid, for example, for high-frequency trading, but also why people that are rewriting their apps into Rust to run on Solana are also having problems changing their business logic to fit into this. And the reasoning is that Solana did a lot of amazing things to achieve this great speed. However, it also had to do a lot of different changes that made it less possible to run complex programs on Solana in full without offloading your computation to something like a network extension. So we decided as Neon Labs to fully enable now these reasons why people who have more complex DeFi apps are not maybe migrating to Solana yet. And we decided to help those that have existing Solana apps but want them to run at 10-20 milliseconds to maybe work with this. So we said that if we are talking about a network extension as a concept where you are still using your Solana wallet, you're still using Solana block space and Solana consensus, and you want to just seamlessly use off-chain computation to do this. And then we said, well, the only way for this system to work for us and remain trustless is actually to use zero-knowledge proofs. However, on Solana, zero-knowledge proofs are not that easy to do. With Ethereum being slow, it's much easier for it to actually prove something using ZK and put stuff using ZK onto the main network. With Solana, it's much harder precisely because of the limitations of ZK technology itself. It requires relatively large, slow, compute-heavy proofs. And when we look at it, from this perspective, even though we are seeing already some of the things that are going to get implemented to make Solana even faster, even without off-chain computation, there are many things we can have today with off-chain computation, such as application-controlled execution, which we will wait for a long time, otherwise, that are possible actually today with ZK. But in Solana, it is a little bit tricky, as I said. So we at Neon Labs, increased our, ZK capacity, mostly through acquisitions. We tried to see what is working in Ethereum world and what is not, because, real ZK EVMs and ZK VMs are not also that common there. They have also a lot of problems of their own. And we sat down and tested out some of the examples of technologies we could actually use to bring you this. And each technology had a problem. However, we realized, that, like a kid, jumping through colored, squares, maybe we can do something to go through just the green part of this picture, And the thought about that was actually, ZKs are just ZK circuits, as a way to do this, are basically just mathematical representations of computer programs. So if I run one ZK circuit customly built for that computer program, and it generates a large proof, still less large than the program itself, I can then run another type of a ZK proving system on that proof and then prove that proof. So by running simultaneously one after another two different proving systems, we can actually, maybe in some cases even faster, prove something and make it small. So this is something we were able to verify we are completely able to do with Plonk, and these are the results we achieved. So right now we can say that we are definitely capable of enabling a real ZK in this manner on Solana through a network extension without you going to a layer 2 or a different network. So you are just, at the end of the day, using your Solana wallet. You are not moving away, only the computation is. The second thing that we tested is that we are able to do this 10 times faster with GPUs. We are still working on our end goal of making this proving nearly instant. And we realized that, by what I said, we do need to write ZK circuits for each of these programs we are running. So our decision was at that point, what are the most used use cases right now? And if you are at Breakpoint today, you know that the most used use case is perps, because everyone is talking about perps. There is lending also, there is, spot, there are other things, but perps are the way to go. So we said, we cannot be just an engine, we have to showcase this somehow. So we went on and are now, finishing and building our specialized VM just for trading on Solana that will allow you to run a perp CLOB DEX on Solana fully. It has to specialize the circuit. So for each of these, we will have to run, separate newly written ZK circuits. But, in the end game, we hope that we will be able to build, and maybe some of you want to contribute, on general purpose ZK solution for Solana, like, we have Snarks and Starks, for example, in Ethereum world. If you are interested, you can check out Parasol, which is the engine that we were able to build. Please do, scan the link, follow up, register for the beta, and become people that might be interested in building on top of Parasol. We really invite you to, first of all, try building, with us on top of Parasol, to try using our VM for trading. If you are building a DEX, or if you are building any type of application that already has users but want to add a DEX to it, please do, reach out to me and the rest of my team wearing these t-shirts, and let's discuss it. Also, if you are just interested in ZK and applications, that you could run, or contributing to a more open source environment for something like this inside of Solana, do also reach out. We would love to help everyone who wants to migrate from either EVM or another ecosystem to Solana, and that was the main purpose of Neon Labs through Neon EVM, but now also through Parasol. Thank you all, and really hope to speak to almost every one of you.
All right, thank you, Ivan. So the next project, their team, I met for the first time in Thailand during Island DAO. And I must say that I believe they are all work, no play, because they have been shipping and I rarely saw them there outside. So please welcome to the stage the CTO of Bulk, June.
Hello. Okay. GM, I'm June from Bulk. We're building a next-gen perps exchange on Solana. A little cool backstory about us. We started out as market makers on Solana, and we market made various venues, spot and perps. Through that, we quickly realized that Solana is the best chain out there to build on, the best chain that also has the highest amount of net inflow of assets, various communities, and various products. But it lacks a serious trading experience. And it all boils down to a couple of things: latency, robust risk engines, and user experience. And we are here to solve that. Our aim is to provide execution worth quoting into. And it all boils down to blending in performance with decentralization. And we provide out three different things. One's extremely fast and pipeline ticks. So essentially, that translates to 20 milliseconds of latencies. And then multi-operator owned matching, where you have multiple validators owning the matching engine, the risk engine, various settlements, and various other parts of the stack that can be run independently by any validator. And then the most important part, a real-time risk engine that actively protects you whenever you're trading perps. Talking a bit more about what ticks are, essentially ticks can be thought of as blocks in terms of bulk. Essentially, three things go into ticks. One's data transactions like oracles and risk signals and various other updates, and cancel and post priority orders. And the bucket number 3 holds all other market transactions, limit, conditionals, and various other things that you want to put. But we arrange bucket number 2 and bucket number 2, 3 transactions in pseudo-random order to prevent last look attacks and also give priority to market makers and latency-sensitive participants who want to post cancels and then post. And this also brings us to the next part about how we give this 20 milliseconds of performance into order pipelining, a async pipeline execution that takes place in 2 phases. Phase 1 of that is we collect all the orders, send it out to all the validators. All the validators create something called mini sketch, which I'll be talking a bit more in the next slides. And then we finalize the mini-sketch, push it to matching. Don't wait for state confirmation. Keep this pipeline moving. But in the next 20 to 40 milliseconds, create a new state digest, finalize that, and commit that into a BFT kind of chain. So keeping this in a very fast pipeline way, we get 0 to 20 milliseconds of latencies for all these sorts of market makers or any other HFT participants, and then 20 to 40 milliseconds of hard finality for people who want hardcore finality on the state. And talking a bit more about why latency is very, very important in high-frequency trading is that this is a Monte Carlo distribution of price over frequency. And from our simulations, we found out that every 1 second you lose up to 1 bips in price changes. And it's very, very important for a participant who is very latency focused. And with Solana's 400 block times, you lose up to 0.06 pips on chain. And compare that to Binance, who's the liquidity leader right now, you're always ending up losing on your trades. And market makers or any other HFT participants who are quoting, they always make a loss. And there's a bunch of things that go on, like arbitrage and a bunch of other things, which are good and which are also bad. And our goal with Bulk, keep that latency as close to Binance as possible at 20 milliseconds. So don't wait for risk checks, don't wait for anything. Pipeline everything very, very fast and push it to matching in 20 milliseconds. And moving to how all this happens is broadcast version 1. Right now, Bulk's testnet, that's taking place in Europe with 5% of Solana stake, runs on an all-to-all broadcast model. All nodes broadcast to each other, create mini sketches, move to execution. And version 2 will be a global view where you can also embed 00 or Alpenglow rails of having this tree-based model or stake-based model wherever you want to do it. Have different regions with 5 to 20 milliseconds of localized latencies and a way to globally sync them in some way. And at the last couple of months, we essentially spent a lot of time into this to build up a new sort of consensus, a state-of-the-art consensus that essentially is dual phase, is leaderless, and also does state and execution separation. And at phase 1, all we are trying to do is agree on what orders to use for this execution. And then phase number 2 is what the result of this execution happen. Let's finalize that. But how do we agree is the hardest problem right now that we have. And with leader-based solutions, like Solana's leaders today, we have a couple of adversarial things happening. Could be malicious leaders, censorship, and a bunch of other things that go into that. And then we have single operator-based exchanges, or you could call sequencers. Again, censorship, just a different model than a centralized exchange with different custody setups. So we thought about this a lot more, and we came up with something we call set reconciliation with mini-sketch. I'll talk a little bit more about mini-sketch in the next slide, but the flow is every honest node creates a mini-sketch after sending out the orders. And these mini-sketches can be computed locally. And if there's no 2f plus 1, you request for any of the missing 2f plus 1, and then you proceed to matching. And what is Minisketch? Minisketch is a BCS-based library, first developed in Bitcoin Core. There's been a bunch of research towards how we can do set reconciliation over the last couple of decades. But you can think of Minisketch as a way you can, it's a tiny checksum of set IDs. It has a fixed capacity C. But as long as the difference of two sets is under that C, you can easily decode, encode, and do whatever you want with the difference. It's 12 times less bandwidth efficient. It's 12 times more bandwidth efficient compared to any other sort of encoding protocols out there. And you could essentially think of it as a way that Bulk encodes all of your orders in these mini sketches and sends it out to all the other nodes. And moving to phase number 2 is all about how we agree what happens after matching. So we create a state digest. We, again, sign it, use a BLS, use anything that's very fast. And they all need 2f plus 1 again. And after that, essentially create a state update to Solana, change the state on the program on Solana that's taking place, that these were the fills, these are the balance changes, this took place in 40 milliseconds. And every single round, phase 1 or phase 2, both needs 2f+1 signatures to go ahead. And this gives us, again, the BFT securities and all these sorts of things. We obviously need 3f+1 operators to be alive, 2f+1 votes for phase 1, phase 2. And this gives us like security up to f faulty Byzantine nodes anytime. And the best part about it is you can keep it very simple. You don't need very advanced ways of keeping it alive. And this is very much inspired by Alpenglow's 20% security model. And the best part about Minisketch is that it acts as an inclusion proof, where you can detect early that this node is a censoring node, or this node is out of sync. And based on that, you can actually build very robust systems, like jailing systems, slashing systems, and various other systems. And also, it's very helpful for any RPC API providers that, oh, this node is out of sync. I can just skip this node and send it to some other node. And moving to what makes this good and how is this good, by separating the states agreement with execution, we get to keep the latency very, very down low at 20 milliseconds. And that gives us very nice UX for a user and a very good user experience for HFTs and market makers and a bunch of other people without having to give up any BFT guarantees that we get. And at the same time, it has this leaderless architecture where every node is an independent operator. As long as the whole network, majority of the network has your orders, you can independently propose and have it executed. And then decouple timelines, you can decouple everything, decouple execution, risk, matching, and a bunch of other components that go into it without having to worry about consensus being the hardest part. And over the last couple of years, we have noticed that consensus is the blocker. We need at least 2 to 3 round trips to confirm something, to agree on something. By doing this, we separate out the most important part, which is very, very safe for market makers to know, oh, wow, my order's been accepted at just 2 milliseconds, or 20 milliseconds, or 40 milliseconds. So 3 different sort of commitments that you can take. And the last and the best part, Solana validators make more money from it. So I'll talk about this a bit more on the last slide, but this whole components is built down into something we call bulk agave, a new validator client that essentially shares 12.5% of bulk exchange fees to the validators in a new form of fee mode. And coming down to the last part is we spend the same amount of time on the risk engine, thinking a bit more what is the blocker right now in current risk engines in the design. And I believe that risk engine is the secret sauce of any exchange, and how it's implemented is very, very important. And any margining system is the hardest part about an exchange to run. So we have a couple of goals, like let's prevent insolvency. No account is ever allowed to take any position that can't be covered during any stress. Then preserve the latency. Don't blow up this computational time of 20 milliseconds. And make it deterministic so that any and every operator around the world can have the same inputs and can come back to the same risk conclusions that this is what happened with the risk. And again, with that, we added 2 more things: portfolio margin, where you will be able to use different sorts of hedging at a portfolio level and accept any collateral, any and every collateral from Solana and other ecosystems. And this brings us to how we do it. We use a Markov-based regime system. Essentially, we identify what's happening at the market now, whether the market's trading, volatile, dislocated, sideline, and we optimize your margin for that. Good hedges get better credit, tail risk gets disincentivized, and the whole system just moves along as the regime changes. So instead of saying Bitcoin on your new order is 5% initial margin all the times, we say, oh, your initial margin, or your margin that's needed to cover this position, is a function of your portfolio, and the regime that we are in right now. Not a static number on a config file that we wrote 2 years ago and gets applied everywhere. And coming to the last part, tying all this together is bulk agave, which houses all the components that I talked about and more, from the consensus to the net and the whole database that we wrote for this. The biggest thing here is that it runs as a sidecar network on Solana. So you have your standard Solana client, which has the same upstream as G2 Agave right now. And it is essentially the same without touching any of the Solana components. And then we have the bulk sidecar, or the bulk net, as we call it. And that has access to all consensus, broadcasts, the database, the external APIs, and a bunch of other signals that we need. This gives us a couple of advantages. We get to secure this sidecar network with Solana stake, which is already live and is economical, and it gives us this huge amounts of billions of economic security for this newly created sidecar network. At the same time, validators get 12.5% of the fees, which trickles down to Solana stakers, and that makes Solana more secure, making bulk more secure. And on top of that, being embedded so in Solana stack, we get to see Solana state very, very fast. Anytime you're a leader, we get to react to it very, very fast, that there is a way for us to read Solana state, and this boils down to our next vision of creating unified margin accounts, where you will be able to connect your wallet, have your positions on, let's say, USDC Prime on Camino, or a looping vault on Loopscale, or something like that, and you'll be able to trade perps with just signing a single message. Don't have to tokenize, don't have to move, don't have to rebalance. All you got to do is connect your wallet, start trading perps, and the risk engine handles all of this. As we have the access to the state, we look at the state, we rebalance you very, very fast, and we keep you safe, keeping bulk safe along the way. And that essentially makes bulk an F1 circuit in Solana's highways, where we have Solana specialized for a lot of things. Now bulk is specializing trading for Solana. Current state of development, we are live on a local cluster, but in the next couple of weeks, our Genesis testnet is going to be alive, and anyone will be able to participate in the testnet, trade up to 50x leverage, 3 different markets, portfolio margin, get to experience the risk engines and all these sorts of things. At the same time, we also have the bulk agave code that is undergoing a bunch of audits and a bunch of other things right now, which will be available to everyone. Right now, 5% of Solana stake is ready and already running bulk agave, which you can check out from Solana's gossip table right now. And we have a bunch of resources I can share too. But essentially, we are trying to build a new gen perps exchange that doesn't sacrifice on ethos of decentralization, but also upholds a lot of performance that we need to battle trading on Solana. Thank you.
All right, thank you so much, June. I can't wait to see this in production. This is the end of my emceeing time. The next person does not need an introduction. That does not prevent me from giving him a very small one. So please make sure when you start giving the applause that they can hear you downstairs. He is the chief scientist of Jump Firedancer. Please make a lot of noise for Kevin Bowers.
Hi, I'm Kevin Bowers and Chief Scientist of the Jump Trading Group. This is our 4th consecutive time presenting at Breakpoint. Thanks for having us back. The title of today's series of talks is When Firedancer. Richie Patel, Philip Taffet, and Michael McGee will be delivering additional talks on stage today, and Wei D will be helping to run the live demos here at the end. Today, I will give some introductory remarks to to cover what we've been up to since Breakpoint 24. Then Richie will talk about fast snapshot loading. Philip will talk about fast replay. And last, Michael and Anway will do some live demonstrations. On a validated podcast in 2024, Austin Federa asked how far along we were getting to mainnet. I answered this was less a question about technical capability than it was about choosing a comfort level where we felt it was safe to deploy so that users would have a boring experience. In a world where developers are encouraged to move fast and break things, this sounds counterintuitive. But the only time users get excited about infrastructure is when that infrastructure breaks. Users aren't often even aware they depend on some infrastructure. Most users interact with infrastructure through applications that rely on it. The recent failures of traditional cloud providers and the resulting far-reaching knock-on effects, including across many parts of the crypto ecosystem, demonstrate this quite dramatically. To provide a credible alternative to big tech and traditional finance, technologies like blockchain need to be more reliable, more predictable, and more affordable to be run by operators, trusted by developers, and subsequently adopted by users. The last thing in the world we wanted to do was jump the gun on deployment. We knew that if a mainnet Firedancer launch was exciting, it would almost certainly meant the launch didn't go right. That kind of excitement is not a good thing. That kind of excitement wouldn't just devalue all of the effort we put into Firedancer, it would devalue the whole ecosystem that wanted and needed a truly independent second validator. As I put it on Validated then, my dream was to go live on mainnet and nobody notice. We view deploying Firedancer as akin to upgrading a utility. Consider the power grid. Users do not and should not get excited when a generator comes online. They just don't want brownouts. Users do not want to have an exciting experience when they flip a light switch. They just want the light to turn on. Users do not want to have an exciting experience when they open their utility bill. They just want their power to be affordable. We believe that upgrades to Solana should be just as uneventful. Unsurprisingly, we are heavily focused on minimizing risk to on-chain activity as we move Firedancer from the lab to the real world. There are two components to this risk. One is the probability things don't go right. We've been driving this down with ever more testing, auditing, fuzzing, and so forth. The other is the impact if things don't go right. Here, the community has grown faster than we could have hoped when we started the project. But this also increases the pressure to get it right the first time. This is a good problem to have, a great problem even. Consider the opposite, a shrinking community huddled around a stagnant protocol. Would it matter if an upgrade doesn't go right? Because we often see confusion between Firedancer and Firedancer, it is worth covering the difference and how it arose from our development philosophy. Recall computer science decision paralysis. When nothing is optimized, AMDL bottlenecks mean there's no immediate payoff to any one optimization. Everything must ultimately be optimized, and most of the benefits are seen when that last bottleneck is removed. Recall Amdahl Street justice. When we throw in latency and bandwidth constraints, everything must also be in the right place at the right time. That is, in addition to optimizing everything, we must streamline the data flow. Fortunately, the protocol is designed for parallelism and conceptually has a streamlined data flow through a validator. This means we can isolate agave components and incrementally replace them with independently developed ones. We call these hybrids Frankendancers, and this approach is very practical. As the protocol and agave evolve independently, we naturally keep in sync with protocol updates and code changes. The resulting validators are composed of documented and standardized tiles that others can replace to make their own validators. We get community participation, release, and operational experience during development. Today, Frankendancers use our kernel bypass networking, core-to-core communications, quick implementation, signature verification, block packing, parallel transaction scheduling, parallel transaction execution, proof of history, Reed-Solomon encoding, turbine block distribution, etc. The main remaining Agave components are the Solana bytecode interpreter and Tower consensus. Ongoing work is mostly putting the last pieces into place, and testing and polishing, and testing and auditing, and testing and fuzzing, and testing and documenting, and so on, to realize the Foundation's primary goal of having a second, completely independent validator, a full Firedancer. At Breakpoint 2024, we showed this timeline that covered key milestones up to that point. We officially announced the open secret that Firedancer was live on mainnet, and Firedancer was live on testnet. At the time, we expected to spend 2025 doing the grinding necessary to give the boring experience necessary to compete with big tech and traditional finance. Because this doesn't generate obvious milestones, we were worried there wouldn't be much else to show on a timeline like this. But we were wrong. Firedancer usage grew dramatically over the year. At Breakpoint 24, Firedancer 0112 was live on mainnet with a tiny amount of total stake across a couple of validators. We had been running it on mainnet on and off internally since mid-2024. By May, Firedancer had over 5% mainnet stake. Multiple operators were running it with around 30 validators. Firedancer is now up to version 0806 and has been fluctuating between roughly 20 to 30% of mainnet stake. Multiple operators are running it with around 175 validators. Operators were even discouraged from migrating even more stake. Firedancer's current level is adequate to get real-world production statistics necessary to tune the full Firedancer while minimizing ecosystem risk. That is, we walk the walk. Our goal has always been to foster the development of a high-performance, enterprise-grade ecosystem with multiple independent validators. A big part of this is developing Firedancer in public to encourage the community to adopt the types of technologies necessary to compete with big tech in traditional finance. In previous talks, we showed blockchains could be accelerated by using the same advanced hardware network techniques deployed by big tech in traditional finance. One of these was at an offsite with folks from Anza and Foundation in mid-2024. I was asked to give some opening words that sprawled into 4 stories about the technical challenges created by community growth. We called these the amazing stories of Firedancer. One of the stories was a gigabits per second attack is a you problem, a terabits per second attack is a we problem. The point of this story was, even if you had an infinitely fast validator, it did not matter unless you also had a fast physical network. We described how to distribute a validator's functionality into 2 or more logical rings connected by a community multicast capable wide area network to overcome Amdahl Street justice and get everything in its right place at the right time. A few months later, 00 built this. We contributed some of the FPGA technologies from our demos at Breakpoint 22 and 23. We also contributed some of the same network capacity we used for our 1 million transactions per second global network demo at Breakpoint 24. Throughout the year, we gave back to the community and are happy the community has adopted our testing and conformance suites and to prove reliability and create additional independent validators. Oh, and one more thing. Firedancer is live on mainnet. It's been hiding in plain sight. Just like last year with Firedancer, this is a bit of an open secret, in part because Michael and Anwei demoed it a few days ago at Block 0. Firedancer started voting on mainnet in July and producing full blocks on mainnet in October. Full Firedancer is currently running on a handful of our validators with a tiny amount of stake. It has accumulated over 100 days mainnet runtime across 3 validators, produced over 50,000 mainnet blocks, and landed over 20 million mainnet votes. Just like last year, we expect the number of operators and validators using the full Firedancer to grow in the coming months as we get more soak testing, complete external audits, and start encouraging other operators to upgrade. In short, This year, a significant fraction of mainnet stake migrated to Firedancer. A significant fraction of mainnet stake migrated to 00. We started running full Firedancer on mainnet, and nobody noticed. Dreams do come true. With that introduction out of the way, each time we present at Breakpoint, we try to have an underlying theme. For example, at Breakpoint 23, the theme was how the speed of light creates a natural parallelism hierarchy. Each talk covered an innovation we made at a level of the hierarchy. We will follow the same pattern as Breakpoint 23 this year. This year's theme was inspired by another amazing story of Firedancer. Big snapshots, slow recovery. The point of that story was, even if you had an infinitely fast validator, it did not matter unless that validator could start up fast. We chose this theme because it is a nice example that we really do have to optimize everything. Startup doesn't even seem to be in the critical path, so it is easy to neglect in development. But it is critical for real-world success. Like Firedancer's development followed the data flow through the leader pipeline, today's talks will follow the data flow through startup. Now, in the past, we've talked a lot about high-performance computing and high-performance networking. But we haven't talked much about high-performance file I/O, compression, and databases. And that's what snapshot processing is all about. So first, Richie will talk about how to optimize loading a mainnet snapshot. Then Philip will talk about optimizing transaction replay. Because the transactions to catch up at startup can be streamed much faster than real time, accelerating replay accelerates startup. But it does more than that. A validator spends most of its time replaying and voting on blocks from the current leader. Accelerating replay allows Firedancers to vote in a timely manner while increasing chain capacity. Then at Block 0, 2024, Michael and Philip had an hour slot for a talk and live demo. The demo was to procure a node from AWS, download Firedancer from GitHub, build it from source, and then fire it up on testnet. While this all worked, the demo had barely caught up to real time by the end of the talk, and they weren't lucky enough to get a leader slot in the remaining time. This year, Michael and Anway are going to do a similar demo. But this time, they're going to use the full Firedancer on mainnet to show the impact of these optimizations, plus many others that we do not have time to cover. Now I'll disappear and turn the stage over to Richie.
I'm Richard Patel, and I'm an engineer on the Firedancer team. My talk today is about fast startup of a Firedancer validator from a snapshot. Cold starting a validator is actually a pretty tough engineering challenge. So here's a quick overview of Solana's mainnet state. We have about 1 billion small accounts that together make up 0.5 terabyte of data. We have to download that data, unpack, and index it as fast as possible, because before we can replay the first transaction, we have to have all of that data local. An earlier version of that code about a year ago took about 20 minutes just doing the cryptographic verifications of that data. And if you took an average cloud storage provider, it would take you about 40 minutes to download all that data. But what if you could do all of that in under a minute instead? I mean, we want our operators to come up quickly, since every minute of downtime costs them money and is bad for the network. So let's step a bit back. How fast can the hardware actually go? Since we're at the lock-in stage, some of you might recognize this thing. This is a typical Solana validator. I found this one in our Chicago office, and there's about 1,000 of these that together make up Solana. Let's quickly pick it apart. It has a ton of memory. It has an awesome modern CPU, often latest generation available. And the storage in this box is equally impressive. Just saving the copy of all of that account data would just take 20 seconds if you compress it. The network interface is surprisingly even faster than this, so I'm going to quickly admire this box. But this is not even the top of the line box. I mean, Solana's operator community competes who can rack the fastest hardware, and this is one of the things I love about Solana. So we can say we clearly have fast enough hardware to start up a validator quickly, so maybe the problem is the network. Let's look at what a validator is typically connected to. we probably have a bunch of neighbors in the same rack, or zooming out the topology, data center has multiple racks, and the metro area typically has multiple data centers. And empirically, we've seen that for point-to-point transfers between any of these two boxes that might be in the same metro, we can get speeds of up to 50 gigabits a second. It gets a bit tricky downloading large amounts of data from remote locations, but Solana at this point is a massive global network, so there's probably a major cluster that hosts the data you need, not far away from you. And if it is, physical infrastructure networks and community projects have come a long way optimizing snapshot download speeds. So we can also conclude, the network is likely fast enough, we have fast enough hardware, it's clearly a software optimization problem. So here comes the fun part. The next 10 minutes will be a high-performance computing crash course going through each step of the snapshot loading pipeline, and hopefully we'll give you a behind-the-scenes look of how Firedancer thinks about performance problems. So here's the whole pipeline visualized. You can kind of see the gray boxes as anything to do with data movement. Data flows from left to right, so we download, decompress, and index accounts. We also have to cryptographically verify them, which are the blue boxes. And then finally, we have to store that data so it's useful for transaction replay in the green parts, which is our database. There's a really cool property here, and this is sort of borrowed from our network stack work. Every step of that pipeline runs concurrently in different processes pinned to CPU cores. All data flow is explicit and streamlined. So we practically have no shared state between tiles, helping us to divide up that big problem, which is loading a snapshot, into independent subtasks that we can tackle individually. Another very important property of this is that since you have this nice and streamlined pipeline, there's practically only ever one tile that bottlenecks the overall throughput. So this is literally the bottleneck of the pipeline. Internally, we like to call this a game of whack-a-mole, where we hammer away at the slowest tile until the problem pops up somewhere else. This might seem super obvious, but actually what you find a lot with apps that have complex thread concurrency is that you spend half an hour looking at some weird performance profiler, trying to find out the part that makes it slow. But here, we spend all of that time just actually doing the optimizations because we kept the pipeline simple. So let's go through the pipeline. Starting with downloading and I/O, which are pretty simple. These are all about streamlining physical data movement and avoiding round trips. We've spent plenty of time talking about Firedancer's network stack on previous conferences, so it's the same thing again. Use kernel offloads, zero-copy I/O, get the network adapter to place data in pre-registered buffers with minimal CPU involvement. This gets us up to line rate data transfer speed. As I said, I'll skip through this a bit, but I'd love to talk about this after the talk if anybody would like to learn more about it. I/O is similar. We need to find the right incantations, of course, to kernel APIs to bypass slow cache algorithms, program the NVMe device to fetch data on its own from DRAM with again, minimal CPU involvement, and we're up to hardware speeds. What's a bit more interesting, though, is the next step, which is decompression. Solana accounts are sent over the network compressed, which reduces bandwidth requirements about 4x. We have to uncompress all of these accounts before we can load and verify them. The tape here is meant to visualize the compressed stream as seen on the wire. This compression stream is in the Z standard format by Meta, and internally is made of these small blocks here. Each block is uncompressed and then yields a chunk of decompressed data. But there's a very painful property, which is actually necessary part of this compression format, which is that each compressed block has a sequential dependency on the previous block. This means that we have to process blocks one by one. Our decompressed output rate with a single thread is about 3.5 gigabytes a second, which might seem cool at first, but it's actually way slower than our network interface, and we need to go 10x faster. So this is our first real problem. To understand this a bit more, let's kind of dig into what a snapshot file looks like on the wire. We see that the entire compressed snapshot is in one Z standard frame. A Z standard frame is a sequence of sequentially dependent blocks. Solving this problem on the compression side is literally a single line or letter change. The parallel Z standard compression strategy splits the input in multiple frames. These frames can then be processed independently, which is very useful for the decompressor. The compression ratio penalty is tiny with the snapshot only growing by about 0.2% in size. So looking at this diagram again, now we have threads hammering away independently at multiple frames. So if you want 10x the performance, that just means 10x in the amount of threads. With that, we have the decompression part solved too. Next, we have to index each account. Recall that we need random access to all of these accounts, so we need to build a global index for these building accounts. In Firedancer, the account index is a giant hash map stored on DRAM, spanning about 100 gigabytes. The indexing algorithm is actually quite simple at a high level. It's pictured here by this pseudocode snippet. We hash each key to a place in the hash map, which is statistically random. Check if the account exists, otherwise insert it. But wait a minute. It's actually crazy slow. So we have this 4 gigahertz CPU, and you can theoretically do 4 billion operations a second, yet this algorithm just does 10 million in the simple case, or like the naive implementation. And a simple backwards compatible change that enables awesome optimizations on the snapshot loader side, namely enabling parallel Z-standard compression. With your help, we can push our, I think, already impressive startup speeds even further, get cold starts well under a minute. So yeah, that's snapshot loading. With that, I'd like to hand over to Philip, who will present algorithm work on Firedancer's replay dispatcher. Thank you, everyone. Philip, take it away.
Thanks, Richie. So this brings us to the last stage of booting a validator, replaying all the transactions that happened after the snapshot was produced. But replaying transactions is more important than just a validator boot, because the Solana validator is replaying transactions all the time, as Kevin mentioned. Last year, we showed a demo with the Firedancer leader pipeline producing blocks at 1 million transactions per second. But if the rest of the network can't keep up with that, well, then the chain can't actually do that. So in order to have a high-performance chain, a high-throughput chain, we need both fast leader pipeline and fast replay. And this year, I'm talking about the fast replay. But what even makes replay fast or slow? Well, as I mentioned, the Solana validator is receiving transactions all the time. In this case, say it's a transaction from Charlie to David, and Alice to Bob, and Alice to David. And it can replay these transactions in pretty much any way it wants, as long as the result is the same as having replayed them in the order that they're listed. So for example, it can replay them like this, serially, one at a time, very slowly. Or it could replay them with some parallelism, like this, which is faster. But if it tries to replay them like this, which would be faster, it'll get the wrong answer, because it'll be replaying transactions that are accessing the same accounts at the same time, conflicting transactions. So it's the job of a component we call the replay dispatcher to decide which way to execute the transactions. It needs a way that's both fast and correct. And it needs to be careful to respect the conflicts and make sure it gets the right answer. And here's where the quality of the replay dispatcher can really shine. The faster we can churn through all these transactions, the faster we can execute them all, the faster we can submit our vote or catch up. And so while we could just use the trivial dispatcher, which executes them one at a time very slowly, it would get the right answer, but it would get there very slowly. And as we push Solana to higher and higher throughputs, leveraging the parallelism that's in the transactions becomes more and more necessary. All this might sound familiar. You might just be wondering why I drew all the diagram on the one side of the slide. And it's because it's really similar to another part of the validator that we've talked about quite a bit, which is the block packet. When our leader pipeline receives transactions, they come in one at a time, and we also have to decide how to execute them, potentially in parallel, before we send them out. And so you might wonder why the replay dispatcher can't just reuse the same ordering that the block packer produced, or why we can't just reuse the same code. It might seem a little funny that we go from serial to parallel, back to serial, back to parallel, and then back to serial. But this sort of approach is actually pretty standard in computer science. When Richie was showing the code, you have a normal compiler which looks at your source code, discovers instruction level parallelism, but then outputs, again, a single linear stream of instructions, which then the CPU finds parallelism in and then executes. And it's standard because it buys you something very important, which is decoupling. So having to follow the block packer's parallelism is really constraining. What if we wanted to execute with more cores, or fewer cores, or we could execute transactions faster, or just some transactions faster. So basically, even if we knew how the block packer packed the transactions, and we could encode it easily, we'd be better off just throwing out the results and discovering our own way of executing the transactions that's more finely tuned for our exact setup. And this means there's no way around it. For maximum replay performance, the validator needs to find a way to dispatch the packed transactions in a way that exploits possible parallelism. And it needs to do it very quickly. If we spend 100 milliseconds trying to find a special, using some super complicated algorithm to find a special way of dispatching the transactions that saves 10 milliseconds, well, that's a spectacularly bad trade. But as we saw, this task is pretty similar to what Pack has to do. So for the rest of the talk, I'll first give an overview of how we do it, and then I'll talk about two things that we learned while building the Pack component and how those apply to the replay dispatcher, and then I'll show some results and wrap up. Okay, diving first into the algorithm. So the standard approach for a problem like this is DAG scheduling, directed acyclic graph scheduling. So we represent each transaction as a node on the graph. You can see the three transactions from before and adding a fourth transaction for good measure. And then you add edges to represent the conflicts, transactions that can't run in parallel. And then you run a pretty simple algorithm. You look at the transactions that have no incoming edges, I've circled those, and those are the ones that can be executed right now. And then as they get executed, you delete the node and its edges, and you just repeat this until you've finished all the transactions in the graph. There's basically only two details left to work out: how to represent the graph in memory, and then when you have multiple transactions that are ready to be executed, how you choose which ones you execute. And actually, these are the two questions that our work on Pack helps us decide. Okay, first diving into the question of how to represent the graph in memory. And the way we represent it is mostly a question about CPU caches. Richie was talking a lot about that as well. And they're key for performance. And when we found that when we were building Pack, the code spent a lot of time waiting for data from memory or from lower levels of cache, because we had such a large working set that we had churned through the whole data between accesses to data. So the data that we wanted was no longer in cache because we had accessed so much other data in between. So we knew that the representation was something we needed to put some thought into. And one of the things we found when building Pack is that actually most of the bytes in the transaction don't matter for dispatching, which means that if we're clever with how we represent the data, we can actually store a lot less than you might think. And that will reduce cache misses. So let's quantify this. I looked at about 25 million transactions in a recent day in mainnet. And what we found is that there's actually a lot of data that we can ignore, or as I mentioned. The signatures, the recent block hash, all the instruction data, all this, of course, matters for executing the transactions, but it doesn't matter for dispatching them. So the first optimization is just not to store any of that data in the data structures that matter for performance. But that still leaves this huge section, the address lookup tables and the addresses themselves, frequently called pub keys. And these actually are needed for dispatching because these are where the conflicts are found. And you can see it is actually the biggest field. But again, when we were working on Pack, what we found is that even though these addresses or pub keys are big, 32 bytes or 256 bits, from an information theoretic perspective, the information that they encode is much smaller. It's something around 11 bits on mainnet and for a typical pub key. So the next optimization we employ is to map all of these pub keys from the big 32-byte string to a small index, and then even then, only store the index when absolutely necessary. This mapping is trickier to get right because you have to make sure that even in a worst case, you don't have any mistakes. But we did the work and we have everything carefully bounded, and we know that it will, even a worst case block can't trip this up. Okay, but even throwing out all the data that we don't need, there's still a lot of cache misses. So the second way to optimize cache misses is to pay close attention to how we pack values. Because when you load a value from cache, you get a whole line, typically 64 bytes, which means that if you access a nearby value, it's typically free because it's in the same cache line. So let's show a diagram of how we're representing stuff in memory. in this diagram, each column is a cache line. And on the left is how we represent it in our replay dispatcher. And on the right is how you would maybe represent it if you're just writing code without trying so hard to minimize cache misses. And let's suppose we want to do an operation like iterate over the edges and update some metadata. So the first thing that we would do is maybe load the metadata. And then you load the edge count. And then you load the edges. Nothing too surprising here. With our way of packing the data, we can store about 13 edges in the same cache line as the metadata and the edge count, which means that loading the first 13 edges is basically free. But if you're representing this in a more normal programming language, the first thing you do is dereference some pointer and the vector, say, and that gives you another cache line. And then you load this other cache line, which has the actual edges. And since if you weren't doing the work to squeeze these pub keys down, they'd be larger. So you would only fit, say, 4 account addresses in each cache line. And then finally, you would write back the metadata. So iterating over the average transaction goes from like 3 cache lines down to 1. And since cache misses are so key for performance, this is actually a really significant difference. It's worth mentioning that in order to use a representation like the one we're using, you also need to bound the number of edges, which requires some careful transposing, I guess, or careful representation. But you can already see the benefits. OK, that wraps up learning 1. Common wisdom is that in a graph algorithm, cache misses are inherent because of lots of random accesses. But what we see is that with careful coding, we can actually reduce the cache misses a lot and improve performance. That brings us to the second question, the second detail to work out. When we have multiple transactions that are ready to be executed, which one do we execute first? And flashing back to our toy example from a few slides back, in this case, we had 2 transactions that were ready to be executed. And actually, in this case, they're both equally good. But if instead of CD, we had CE, you could see that at the start, we would still have 2 transactions to execute, but CE would be less beneficial towards finishing the block. Because when we finish AB, that unblocks AD. But when we finish CE, that doesn't unblock anything. The precise way to think about this is in terms of the critical path of the graph. The critical path is the longest path through the graph measured with the appropriate weight. And it's important because no matter how many parallel resources we throw at the problem, no matter how many cores we're using to execute this, it's not possible to finish the graph faster than it is to execute the critical path on a single core. So the way to finish replaying the block as fast as possible is to focus our execution resources on the critical path whenever we can. When we were building Pack, we spent time getting familiar with the structure of these graphs in real mainnet blocks, and we also saw there how important the critical path is. But you might remember that we're actually executing these transactions and receiving them in a stream. We want to start executing them before we've received the whole graph. So we can't wait, build the graph, analyze it, find the critical path, and then start executing. We want to start even before that. So we turn to some heuristics. Certain accounts are hotly contended. So if a transaction accesses one of those, then it's much more likely that another transaction is also going to be executing it, and then those 2 transactions will be on the critical path. Other accounts are much less likely to cause contention, and so those transactions are probably not on the critical path, so we can wait to execute those. So as we insert transactions into the graph, we're measuring over many blocks how frequently transactions are executed. And then we can just use, based on our past history, we might guess that, for example, C and E are hot, A is pretty warm, and C and E are not hot, they're cold. A and B are hot, and B might be warm, D is extra hot. And then we can use that to color the transactions when we're comparing them. So then we would know to pick the transaction involving A and B, because they're hot accounts, before we execute C and E. And we can make this determination before we even receive the transactions in the rest of the graph. And the best part of this is that all this metadata fits in the same cache line as the node itself, so we get this basically for free with no extra cache misses. And that wraps up learning 2. To execute a block quickly, we need to focus on transactions on the critical path. Okay, now let's move on to some results. Michael and Onway are going to show the fruit of all this work in a few minutes, but let me show one or two graphs that summarize everything. On the x-axis, we have the number of cores we're using to execute transactions, and on the y-axis, we have the simulated time to execute the block. Here, the simulator uses the real replay dispatcher code, but simulates execution of the transactions. So what we see is that the graph at the beginning is decreasing, which means the replay dispatcher is finding parallelism in the block. But then that only goes up to a point. After about 3 or 4 cores, we hit the critical path. And basically, we're constantly executing transactions on the critical path, so more parallelism hardly helps. And thirdly, if we zoom way in, we can see what was just a speck before is this is the red section, which shows how much time is spent running the replay dispatcher, not executing transactions. And the light red is when the replay dispatcher is busy, but it is also executing transactions at the same time. We can see that the replay dispatcher is mostly idle, and these are executing mainnet blocks faster than real time. That means, the replay dispatcher can handle much more, much bigger blocks and much higher transaction loads. Okay, finally, I want to show a similar graph taking from a smaller data set. We can use an integer linear programming formulation to get a bound on the best possible execution over all ways of executing the blocks. Well, this form of computing it is extremely computationally intensive. For small blocks, it takes tens of minutes or even hours, and sometimes it still doesn't even converge. But I've shown this bound in the line. And what we can see is that even in less than a millisecond for these blocks, we're getting close to the theoretical average, or theoretical optimum of the best way to execute these transactions. You can see it's quickly choosing a way of dispatching transactions that's close to optimal. Okay, in conclusion, echoing some of the themes that Kevin mentioned, we're here grinding away on tiny details, worrying about cache misses and how data is laid out, and learning from our past experience to make our code even better. We're doing it so that we can keep making Firedancer and Solana faster and faster. Now we'll turn it over to Michael and Onway, who are going to show all this code in action.
All right. Thank you very much. So you guys have seen a lot of the cool stuff we're doing, how we're optimizing the validator to make it super, super fast. You're probably pretty excited to see it in action. So Onway's going to do what I would call a proof of restart here. We're going to restart a validator live in front of you and boot it up. Here you have it. A fresh, from-scratch validator, written entirely in C. It's running live, highly staked, and on mainnet. There is not a single line of Rust code running here. Yeah. This represents a lot of work by the team, countless years of nights, weekends, a lot of hint waters, Diet Cokes. The GUI we're showing you, if there's any validator operators watching, we kind of built it for you. The software is sophisticated, complex, it's got a lot of moving parts. Kind of think of it like an airplane. And these operators are something like pilots, right? We want to teach them with the instruments we have how to operate it well, so they can make the network faster too, and also help in an emergency. If anything's going wrong, to quickly diagnose and see what went wrong. Here we booted into the snapshot loading screen. Richie talked a lot about this. And we're booting this snapshot in real time. You can see the pipeline parts of the system running on 3 CPU cores here. Where we're getting the snapshot from, we're actually downloading this from the network, from a live peer, decompressing it, and inserting it into our accounts database. See, it's about halfway done. Should take around 2 minutes. I'm going to briefly explain what you'll see after this, because it's going to go by pretty quick. Once we finish loading the snapshot, we have to catch up to the chain. We fell a little behind as the chain kept moving forward from the snapshot. So we have to repair and replay. On this screen, so we kind of start a bit behind, and we're going to aggressively start catching up. Right before that, actually, there'll be an incremental snapshot. So there's kind of 2 snapshots we have to load. a full, and an incremental. You see we're doing about 3 gigabytes a second of output, inserting a little over 6 million accounts. Yeah, and here we're bottlenecked on this insertion stage. We'll watch for a second in silence while we wait for this. And again, we'll see really quickly the incremental snapshot, and then repair and catch up, which is a lot of what Philip talked about. Hopefully we'll catch up quickly. There's the incremental. And here we're catching up. So here you have Firedancer, a lot of information all at once. We have a bunch of new visualizations we're excited for you guys to see. Slots, right at the top. This shows the validator is keeping time. It's on pace with the chain. It's not falling behind. You've got your turbine slot. This is the tip of the network. And our process slot, which is falling right behind it. We're routing well. And you can see we have a leader slot here. It's a pretty highly staked node in about 1.5 minutes. This slot's visualization is really good just for making sure your validator is healthy and nothing has gone wrong. Below this, we have shreds. I think the Solana network has kind of intricate and beautiful protocol underneath it. And a lot of what we're doing here is trying to show you inside the validator to help you understand. I want us all to kind of just sit and stare at the shreds thing for a second. I'll explain it after. I think this is kind of art. If we're talking about slots, each one of these vertical columns represents a slot produced by some other leader on the network. This is live, real time, that they produced. And every row within that vertical column is a network packet they had to send to us for us to replay that slot. So these are the shreds. We're showing us receiving these shreds, replaying them in green. Here you can see a little red. This means the validators had to do a repair. That's pretty rare, so this is showing the validator is healthy. I'll point you again, time until leader, about 10 seconds. So we're about to produce a block here. And hopefully we'll see that go well. So this is a live mainnet block. We'll prove it to you. Go to the leader schedule, and we'll grab this slot number. And we'll just pull it up in Solana Block Explorer. Feel free to do this on your phone. There it is, just on the chain about 30 seconds ago. It's well packed, the chain's not at capacity, but you can see if we scroll down, this is DNVZR validator. And we put a bunch of stuff in it, a lot of votes, a lot of transactions. If we go back to the validator now, and we'll go back to the overview, continue showing you a few more things here. So a lot of you might have seen some of these visualizations. These are for Firedancer. This is representing the leader pipeline in motion, building up to whenever our next leader slot is. But we'll keep scrolling down and show you a few other new things. Here is every part of the Solana protocol, live running, network and egress that they're taking up. You can see repair here operating pretty easily with the TPU, gossip, turbine, our metric system. If we keep going down, this is a bit of a more interesting section. These tiles, we refer to these, are really CPU cores of the system, showing how busy it is, what each CPU core is doing. If you scroll down a bit more, you'll see there's a lot of these, but they're mostly idle. Firedancer is massively over-provisioned. We've designed it to do 1 million TPS, and it would, if it could. So these exec tiles, we have about 6 of them. These are actually executing the replayed transactions. So as blocks come in here, these are executing transactions, as Philip showed you from that dispatcher, and these are pretty much idle. Yeah, so validator is just unchallenged right now. If we scroll back up, I think, another leader block there. OK, we'll cut over to the slot details, actually. So we'll pull up one of these leader blocks we produced. We're going to show you a little information about it. Here is the slot detail information for the block we produced. Pretty detailed. We're showing you a bunch of information here you might find useful. Protocol limits, busy accounts, cumulative execution time. Our goal with Firedancer is to make the execution incredibly, incredibly fast. And so we have a ton of detailed information here and metrics for making sure that happens. Keep going across. We have all the fees in the block, income, where it came from. Is it a bundle? Is it a transaction? And then performance. So we talked about the scheduler as one of the most important parts of the system. It often represents a bottleneck. So here we're showing all the decisions the scheduler took throughout that block, why it took it, how many transactions were in your buffer, and a bunch of other interesting metrics about the block. We keep scrolling down here. I'm going to try and show you something interesting. We get to the bottom here. This is what we call the banks visualization. This is showing what every CPU core did that was executing transactions for this block and which transaction it was doing. So we're going to filter this to just the votes that went into the block and just those that were successful. And remember, this is a block we just produced live. We're going to take a look at the first few votes we received. And with any luck, not that one. Here we go. This first one is likely someone voting late on a prior slot. But here, this vote we received is from this interesting looking validator, FBBQ. Might be wondering how this guy vote so fast. Took him 26 milliseconds. A little bit of a secret, but we'll reveal it to you. This is Firedancer too. So we run one other node, and it is the fastest voter on the chain. Just to explain what goes into that, voting quickly involves every other part of the validator that wasn't in Firedancer. We have to receive shreds, replay them really quickly, come to consensus, cast a vote quickly, send it out. We're able to do all of that in 25 milliseconds. You can see here kind of the rest of the cluster and about how long it takes on average, and us with our sample size of 1. Wouldn't be fair to just take a sample size of 1, so we're going to show you a bit of a bigger one. As part of building Firedancer, we wanted to track data and compare all the validators, and we couldn't really do that easily, so we built an entire reporting site of our own. Here, you can see we just added, a few days ago, Firedancer, so you'll be able to track the deployment and rollout of the validators as we make it better, add more stake. But here, we're going to go to the daily view. This is showing literally today or yesterday. We're going to sort by an interesting metric we call lat1 vote rate. This is the percentage of time the validator voted on a block in the very next block. This is the quickest you can possibly do it. And you'll see the number one validator yesterday was us. All right, we can go back to the validator. We'll just show you one other thing here. There's a ton of components involved in running the validator. We've implemented all of them. Repair, gossip, snapshot, load, a ton of stuff we don't have time to go into. We'll show you one more screen here. Gossip, this is kind of one of the more interesting components of the network. This is the first thing you have to do when you boot. Gossip is a table of information we have to get from other validators about their IP address, where they're located, what snapshots they're serving. Here you can see the whole gossip network live in action, who we're receiving from, who we're sending to, what the bandwidth is. If we scroll down, how much data we're storing, what types of information we're storing in this table, and here we keep going down. Just seeing that it's healthy, we're not receiving too many duplicates or failed data. And here is every other peer in the cluster that our validator is connected to and receiving live. This table infinitely scrolls, it's updated in real time. We're pulling a ton of information to allow us to diagnose and debug stuff quickly and make this validator really, really good. One other thing that's kind of interesting, this UI is live. You can view it yourself, gui.firedancer.io. We'll leave this validator up and running today for a few hours so you can take a look. I want to close with a couple of remarks. Well, the talk is called When Firedancer. And as Kevin said, if you look kind of at what we did with Firedancer, we were at 0% stake last breakpoint, and now we've got up pretty high. I think the deployment trajectory is going to look pretty similar for Firedancer. We have 0% stake now, effectively, but it's about to go up. But people kind of think there's going to be this big bang moment with Firedancer where one day it's not deployed, and the next day it is. And reality is like kind of nuanced. The chain is not at capacity. So when Firedancer ships, probably nobody will notice. In some sense, when for Firedancer was 3 years ago, right? It's when we started contributing to the core protocol, started hosting performance meetings with Anza, started putting our design in, bringing our technology over, and contributing all to the community, open source and free. The chain is already, in a lot of ways, a product of Firedancer. We'll finish with an anecdote. When I started it on the Firedancer project, I was chatting with Kevin Bowers. And I asked him, well, you know, this technology is really valuable. We have a lot of expertise in stuff we're doing. And we come here and we give it open source and give it away for free. Why? And he said, well, I've found in my experience you can put up barriers and try and prevent people learning what you're doing and hope that that keeps you ahead. But it doesn't really work. The best strategy I ever found is you just run faster than everybody else. And I hope that's what we're doing with Solana and what we're contributing here. So thank you for coming. It is a lunch break. They cut my mic. Oh, yeah, it is now lunch, apparently, so you can come back here in an hour for more talks. But thank you again.
All right. Hey, everyone. My name is Mike, and I'm the DevRel for Solana Mobile. Today, I wanted to talk about our growing developer ecosystem and why the Solana Dapp Store is the best place to launch an app. But first, for those who don't know, I'll explain what Solana Mobile is and what we're doing. Our mission is to bring crypto onto mobile and enable mass adoption. Mobile accounts for 63% of all web traffic and 73% of all e-commerce transactions. I think at this point, most people understand that mobile is really important and it should be part of a product strategy. But most crypto experiences today are still only built for desktop. Why is that? Well, there are still major roadblocks in crypto's mobile landscape. Apple and Google are gatekeepers to distribution, and they're hostile to crypto apps. This is a real problem for developers. I've talked to a lot of teams who have basically had to abandon their mobile apps because of this hostility. You can't justify time investing into a mobile app if you're not even sure it'll get approved, and you can't experiment with crypto app ideas and crypto features if it'll risk your app's approval. So innovation suffers, and that's been holding back the whole ecosystem. So how are we solving this? In August, our team launched Seeker, a crypto-native mobile phone built to address this problem. We wanted to build an open mobile platform where crypto can thrive. So what makes Seeker crypto-native, and how does it solve these problems? A couple of things. First, every Seeker has the seed vault, a built-in hardware wallet for secure storage and transaction signing. Any app on the device can connect to it and request signing with user approval. As a developer, this is huge. Your users can connect to the seed vault and receive a seamless signing experience, all without ever leaving the app. It's like having an Apple Pay API available to you at all times, but for crypto transactions. And here's a demo of what that signing experience looks like on Jupiter. Here, the user initiates a swap transaction. Seed vault draws a bottom sheet. The user approves by double tapping and then confirming with a fingerprint scan. The bottom sheet is dismissed, and the transaction is submitted. And we think this is one of the best signing experiences on mobile today. There's no jarring app switches and no janky wallet browsers. It all happens within the app. And this is a big unlock for crypto apps. So that's the wallet experience. Now the second piece. Every Seeker ships with the Solana Dapp Store, an alternative app store built to be a friendly home for crypto apps. We have no hostile policies towards crypto and no 30% platform tax. As a developer, you can build a mobile app with crypto features and not have to worry about that being a risk to your app. And the Dapp Store is where you'll find distribution. We have over 100,000 Seekers activated across multiple countries around the world. We have over 200 apps published in the Dapp Store today. And these are crypto power users that are actively trying out downloading apps on the Dapp Store. They're signing transactions, making purchases, playing games. To this date, we've had over 1 million app installs on the dApp Store and over $100 million in economic activity flowing through the Solana mobile ecosystem. So for developers, the dApp Store should look like prime real estate. Unlike Apple and Google, where your app is buried alongside millions of other apps, on the dApp Store, you're competing against a much smaller pool of apps to a higher signal group of users. So if you're building an app, especially if it's in the early stages, this is one of the highest value user bases that you can tap into and find distribution. And we've heard a lot of success stories so far from teams launching on the dApp Store. Moonwalk Fitness is a gamified daily fitness app. And when they launched, they received 12,000 new user signups just in their first week. And later, they went on to achieve all-time highs for daily active users. We also have Perena, a DeFi app that provides yield on stablecoins. During their launch, they saw over 4,000 user deposits and over $13 million across all Seeker users. And these are just two of the many successful launches that we've seen so far. The feedback we've been getting from developers has been pretty clear. They see the dApp Store as a valuable platform to grow their app and find direct distribution to spendy crypto power users. So how do you actually publish onto the dApp Store? Let's talk about that process. First step, build an Android app. Seeker is an Android phone, and so the dApp Store takes Android apps. There isn't any special framework or operating system you need to build for. It's just Android development. And what that means is you can use any standard Android framework like Kotlin, React Native, Flutter. All that matters is that at the end of the day, you produce an Android APK. And you don't actually even need a Seeker to develop for the dApp Store. You can test and build against any Android app or even an Android emulator. We provide development tools like the mock wallet, so you can simulate what the bottom sheet signing experience looks like on the seed vault. And one of the most common questions we get is, can I publish a web app on the dApp Store? The answer is actually yes. Yes, you can. There's an easy process you can do to convert a PWA into an Android app. And to do that, you can use this open source tool called Bubble Wrap, developed by Google. Bubble Wrap takes a PWA and then wraps that into an Android app that you can publish onto the dApp Store. It's just 2 CLI commands, init and then build, and then it'll generate you that Android APK. There's an app on the dApp Store called Crypto Fantasy League that actually uses Bubble Wrap. And their PWA looks awesome because they optimized it for a mobile browsing experience. Using the app, you can't really tell it's a PWA, and it looks better than a lot of native apps. So the Bubble Wrap route is definitely a viable strategy to get on the dApp Store quickly without having to build a mobile app from the ground up. And after you finish publishing your app, the last step is to submit it to the dApp Store. To do this, we recently launched the Publishing Portal, a website where you can sign up for a developer account and handle the entire app submission flow through a nice web UI. On the portal, you'll find a forum where you can enter your app details, add any screenshots or previews, and then upload your APK and submit your app. And finally, after you've submitted your app, all that's left is just app review. How app review works is our team will take a look at the submission, make sure the metadata and the details are correct. We'll do a light QA check. And if all is good, we'll approve the submission, and your app will be submitted to the App Store. We want this process to be as frictionless and simple as possible while also maintaining a bar for quality. So this is a pretty good idea, or now you have a pretty good idea of how to build for the dApp Store. For this last section, I wanted to talk about some upcoming opportunities to jump into the Solana mobile ecosystem. First announcement, we're launching a grants program. These grants will cover a variety of things like developer tooling, SDKs, public goods, and also app ideas. You can scan the QR code or go to solanamobile.com/grants. And on there, you'll find all the information about this program. You'll find an application form to apply for a grant and also a list of existing RFPs. Definitely check this out. And our last announcement, we're going to be launching our second mobile hackathon in Q1 of 2026. Just like last time, this is going to be an opportunity for developers to build an app and compete and win prizes like cash and also featured placements on our dApp store. So if you win, your app can get higher visibility. Stay tuned for more information here. And here are just some resources. So everything I talked about in this presentation, everything about our wallet SDKs, how to publish on the dApp store, documentation, that can all be found on docs.solanamobile.com. And if you're in the audience and you're thinking about building an app, or the dApp store sounds interesting to you, maybe you don't even have an app yet, maybe you just have a web app and you're interested in bubble wrap, or maybe you already have an existing app that's on the Play Store. Please come find me or any of our team members. We have a booth downstairs where we are giving away free stickers. So come by, find us, talk to us. We're happy to answer your questions and help you guys get onto the dApp store. Thank you so much.
Thank you, Mike. I can't wait to see what everybody makes. The next thing's coming out in Seeker is going to be fantastic. Well, this next talk is something I'm super excited about. Anything that helps us interface with the chain more efficiently, I'm super bullish on. So talking about accelerating Solana, please welcome with a big round of applause, Head of Engineering at 00, Ben Marks.
Hello, everyone. Good afternoon. We have a lot to cover today, so let's get right into it. So first of all, let's level set. What is 00? So 00 is the protocol. We're building a protocol at Malbec Labs. And the protocol is a thing that we've been working on since the white paper was created last December. And the realization of the protocol is what we've all come to know and love, which is the high-performance, decentralized global network. And what I want to stop here and focus on decentralization for a second. So this is something that has been really dear to my heart since I was a teenager working with Linux and being anti-Microsoft and all these kind of things. And this also flies in the face of basically everything that's happened over the last 20 to 30 years in terms of consolidation, in terms of monopolization and conglomeration. And so this also provides different incentives and means that we can build things together that we couldn't build alone. Now, let's take a look at a high level of what the 00 architecture looks like. So we have in the middle the protocol, and we've highlighted two bits here, serviceability and telemetry. So the serviceability program basically defines what the network is. The locations, the exchanges, the links, the latencies, the jitter, the bandwidth, and so on. And the telemetry is we pull data from our private network or from the collective's private network, and then we also compare our private network against the public internet, and this is how rewards are generated for the network contributors. And all this data is on-chain. We have our own DZ ledger. Anyone can read it and see the data that we have, and we also expose this in public metrics on our site. Now, on the left, we have tenants, which implies that there's more than one tenant, or can be. Our first tenant is Solana, and our primary users are validators. And we have about 40% of validators on the network. Now, on the reward side, what I want to highlight really quickly is that we use Shapley values to calculate rewards. And Shapley values essentially drive the quality up. So the way we measure it is if you're not part of the network, how much worse is the network? And this is really important because the ISPs have a race to the bottom. We have a race to the top. Quality generates quality. Now, let's talk about what high performance is. So we always talk about reducing latency, but that's not enough, right? Latency without control, you get a lot of jitter, and it makes predictions that much harder to guess. So performance is speed and control. And so we've launched mainnet beta in October, and we have some interesting data to show. And now I'm going to show something from an RPC provider here, and we're going to take a moment on this slide. So here on the y-axis, we have the RTT time in seconds, and then on the x-axis, we have the date, or the time that has transpired. And on the left, you can see this is on the public internet. The middle, the 00 difference, is in the middle, and on the right is when going back onto the public internet. So P50 is kind of stable throughout, but P95 and P99, this is where you see a wide variety of latency. And this is what, if I remember my undergraduate economics degree, this is where the margins where you can actually get a lot of economic value. And you can see on the middle that even though there is still some jitter, it's significantly reduced. And so if you're on 00 and you want to land a transaction, you can do that in maybe, at the worst, about 500 milliseconds. But then on the public internet, it's over a second, maybe a second and a half. And that's a significant amount of time for you to make better decisions. And really what this is all about is having better information, more reliable delivery, so that you can have better economic results for yourself. And so the reason here that this particular RPC provider went off the public internet was because there's an edge case. And this brings us to the next case, what we're going to talk about, which is how do we understand how the network is working? Is it healthy? What parts of the network are degrading? And a global network, especially a decentralized global network at that, is rarely, if ever, fully healthy. There's always some parts of degradation. There's always some parts, some links are coming up, some links are going down, unexpected fiber cuts, and so on. And so this is a way for us to very easily and efficiently see what's going on in the network. And so here you can see, for instance, we have the overview of the links, and we also have healthy drift, telemetry, and so, missing telemetry, and so on. And we have, looks like, 16 links here that have drift here, which you might think, well, that's not great. But I would actually argue, in fact, that that is very good, because now we have the data to be able to understand that we have this issue in the system, and now we can work with the network contributors to resolve that, and then we can continue to build tooling in that will make these things more easy to understand and easier to resolve. Now, we've talked about things that have existed on the public internet. All the things that I've said so far are existing in the public internet, but let's turn to something else, which is multicast. Multicast does not exist and cannot exist on the public internet. And so we have two case studies here, one with Jito Labs and one with Anza. And we basically have shred stream over multicast and then turbine over double zero multicast. And we're going to focus on the Jito side, but I want to show a graphical representation using real data of what it looks like with turbine over unicast and then turbine over multicast. So here, Frankfurt is the leader. If we click through this, we can see going out to Frankfurt, to Amsterdam, to London, and you can see that this is taking a while. It's going to these different places, and then now it's going to go over to the US and back. And so you can see this is lots of stuff going back and forth. Now, if we look at multicast, this really shows an equitable view of the world. You can see that as soon as a packet goes out, it goes out all over the world. And as we all know, physics can't be beaten, right? So if you're in Frankfurt going to Amsterdam, that's always going to go faster than if you're going to, say, Tampa or Miami. That's just the way that things are right now. So here we have shred stream. So this is the shred stream, architectural overview. You have the Jito Solana sending to turbine, shreds the turbine, shreds the Amsterdam block engine, and these are all over unicast. And these Amsterdam workers are having to basically approximate unicast or multicast rather. And so what happens when you add in double zero multicast is that, as Andrew, our CTO, likes to say, multicast is just a different destination IP. And so here it's very simple. We just have another place where we send it to, and multicast within the double zero network intelligently replicates this packet throughout and then gets to the other side. And then if we take a look at a higher level, this shows all of the block engines around the world. And you can see the same pattern applies, sending a single packet into that double zero private network, which is intelligently replicated throughout there, and then gets over to the shred stream the shred proxy on the other side. And we did a test. The test shows that we wanted to measure the difference between the unicast and the multicast thread. And we wanted to make this as simple as possible, so we basically took packet captures and took the timestamps of those packets to measure this. So we measured the difference between the unicast and the multicast packets. So this is kind of a convoluted thread here a little bit. But on the left side, we have Tokyo and we have Frankfurt. And on the right side, again, Tokyo on the top and Frankfurt on the bottom. And so you can see here that there's a substantial increase in millisecond improvements on both Tokyo and on Frankfurt. And Frankfurt even goes up to more than 60 milliseconds. And even here, even though there are some cases where the public internet is faster, we're still getting these P99, P50, or P75, and so on that make it a lot better, where you're much more likely to get this marginal return and potentially a much bigger outsized return than you would on the public internet, this P50 and so on. And then likewise, on the top you have the Tokyo again here, and you can see the percentage of 00 multicast wins over the unicast wins. And likewise on Frankfurt as well. So this shows very clearly that there's a real advantage to using 00 multicasts over unicasts. And what makes this especially nice is that this is a really simple way for something like Turbine, something like Jito Shredstream, or any other thing that would benefit from this replication throughout the world to add on, because it's just a different destination IP. And this is technology that has existed for a long time, and that it's high-frequency trading firms have been using this to reap these benefits for many, many years. And this is something that we value at 00, and the reason that we've been able to move so quickly is because we're using technologies that have been tried and true and that have existed for, in some cases, 20 or 30 years. So we understand the problem, and we can build a quality system, and one that has been tested by some of the biggest firms and biggest tech companies in the world, and we can bring this into a new way so that people here can benefit from this in a way that wouldn't be possible on the public internet. And so, while physics can't be beaten on 00, you can shrink the world. Thank you.
Thank you so much. All right, so this next talk is something that is definitely top of mind for us at Easy Labs. We do payments and stablecoin infrastructure, so we've been following this company for the last couple of years. So coming up next here, speaking on building encrypted Solana apps, is Nico Shapler, and he is from Archium.
Hey everyone, my name is Nico, and I'm one of the co-founders and CTO at Archium. Now, my talk is titled, as you can see here, Fully Encrypted Solana Execution with Archium. And for those of you who perhaps have not heard of Archium before, or maybe if you have heard of it before, just based on that title, that probably already spins up, first, what is that? Second, why should I care about this? Or why is this important? And lastly, most importantly, how does this work? And hopefully after that, how can I use this within my own products to add privacy? So first, for the first part, fully encrypted. What do we mean by this? So generally speaking, if you go to Solana today and you go to the Block Explorer and pull up any account or transaction or what have you that you like, you can see any information that you want about that there, basically. Who the sender is, who the recipient is, what data was input, and so on. There's some stuff you can do to hide that a little bit. For example, not uploading your IDL, writing your code in such a way that's difficult to reverse engineer. But these obfuscation techniques obviously are just a band-aid that doesn't really solve that problem. The other technique that you can, of course, say as well is that you store your data off-chain, which is what many institutionals, for example, are forced to do today, and only interface with Solana for certain operations. But of course, this isn't great either, because that means you rely on a trusted third party. So what we're enabling with Archium is that we allow you to use provable cryptography to have everything hidden, meaning that instead of having an adversary have to capture a third party or have to deobfuscate a little bit, your adversary would have to gain a Nobel Prize for breaking cryptography, basically, to be able to withdraw private information that you want to keep hidden. And yeah, when we say hide everything, we mean everything, meaning inputs, intermediary values, outputs, the whole full thing. And yeah, the last aspect that we mean with fully encrypted as well is zero information leakage. Concretely, what I mean by this is that traditionally, when people think about privacy on general purpose blockchains, they think of mixers, but even though these are based on cryptography, they don't have zero information leakage in the sense that if you deposit $1,200 into it and 10 seconds later withdraw $1,200 once more, it's quite obvious to an outside observer using statistical methods what you're doing. The second part, Solana execution, I don't think I have to really explain what that is. Obviously, we're at this conference for a reason. But concretely, for our use case, what this means is that any operation is executable that you'd be able to execute on Solana in an encrypted manner, not just a subset. And on top of that, having direct compatibility with Solana, meaning you don't have to go to a different chain or set up some off-chain thing or whatnot. Just your Solana smart contract lives just like a normal program on Solana. Your accounts, all the state lives on Solana. You execute things on Solana. So, direct compatibility. And yeah, the thing that we built to make this happen is Archium. We sometimes like to call it the encrypted supercomputer. But more concretely, in I guess a bit more layman's terms, it's a network extension for private states and private execution, which is powered by secure multi-party computation, or MPC for short. And yeah, we'll learn about how that works a little bit more. Before that, real quick though, now that we said the what Archium is and what it's used for, what properties it has, quickly just why should you care about this aside from it just being kind of cool, I guess. The first part is wealth and payments. So as the presenters Andrew just said, generally speaking, you don't want the entire world to know how much money you have on chain. On one hand, because it feels a little bit awkward, but also on the other hand, because especially over the last year and a half, there's been quite a few attacks in the real world against people who unfortunately were targeted because their balance was visible on chain. So, if you make this private, that kind of solves the problem because you won't get targeted if someone doesn't know if you have $1 or $1 million. Second part, private data management. I think this is quite general, the term, but what I mean by this is that Solana has grown a lot in the sense that it's much faster, much cheaper, much more efficient, so it can support a lot of use cases nowadays, even from traditional finance and other sectors. However, a lot of those have to still keep many of that off-chain because they don't want their private information or their client's private information or whatnot to be visible on-chain. And the last part, MEV. At the highest level, MEV is really just that since a validator can see your transaction and see what state changes they'll affect, they can take advantage of that by putting stuff in front or behind or just taking advantage of that while block building. So of course, if the state changes in the transaction are encrypted, not much MEV you can really do there. I won't say it solves it 100% because it's a very complex issue, but at least for the most common type of MEV, such as sandwiching, it does work quite well. So now that we've talked about what we're building, why we're building it, most important part, how does this stuff actually work, especially after such bold claims? So here we have a little picture of the high-level overview of how this works. As you can see there, on the very left, we have Solana, then we have some stuff in the middle, and back to Solana. So let's start from the left. The idea is basically that you have some account living on Solana, and you want this account to contain some data that you want to keep private. So you encrypt it, upload it to the account, and store it there. So nice. That means if someone tries to fetch it from the block explorer, they only see a ciphertext and not the plaintext that you're actually hiding inside of it. But now the more interesting part is you actually want to compute with this data instead of just storing it on-chain. So let's say we want to have a simple computation like adding 5. What we basically do then is we take this data, this encrypted data, and split it into so-called MPC secret shares. This is this little 3 shares thing there. And an MPC secret share basically has the property that if you put it back together, it gives you a secret. However, any of the individual shares doesn't leak any information about that secret. Then what we do is we take each of those shares, pass it to one of the nodes inside the Archium network. They compute on it using secure multi-party computation. Produce the result, adding 5, for example, in the example. And then after that, re-encrypt it to a single ciphertext that basically encrypts the result of that computation on the initial encrypted data. The important thing here is the individual nodes in the middle here never learn what the private data is. They only ever see shares. Solana and anyone observing Solana only ever sees ciphertext as well. So that means we are computing on data without anyone actually seeing what that data is. Now, I realize this is a decently bold claim to make as well because it raised a lot of questions about, okay, how do we make this secure? How do we need to trust these nodes in the middle since it's not on Solana and so on? And the way that we do this is by using our MPC backends developed in-house by our cryptographers called Cerberus. And this is a general purpose MPC backend, meaning that as opposed to what people generally associate with MPC being signatures, you can calculate anything that you want on this, be it a signature or be it a DeFi operation, be it whatever you might like. The 2 most important properties of this is dishonest majority and malicious security. So what these 2 words mean is dishonest majority means that you have to trust that one node in the entire cluster is honest, as opposed to 51% or 66%, as is more generally the case in blockchain consensus or other types of MPC, for example. And malicious security means that we assume that malicious nodes can do literally anything, meaning they can go offline, send incorrect data, mess with the network in any one way that they like. And this essentially gives us very strong security assumptions because dishonest majority plus malicious security means that as long as one node is honest, the other nodes can do pretty much whatever they want, but we still won't produce invalid outputs, and private data still won't be revealed. This is particularly useful if you're building on Archium and you think, I'm not sure if I quite trust this network or something like this. You can just say, I'll deploy a node myself. That means you then have at least one node that is honest, fulfilling the dishonest majority assumption, and therefore being sure that your private data stays private and that no incorrect outputs get produced by the network, basically. And I know most of us here are developers, so concretely you're probably thinking, okay, this cryptography stuff is cool and all, but how can I actually use this without being a cryptographer or having a degree in this or whatnot? And for this, we built Arcus, which is the first Rust to MPC bytecode compiler. In Arcus, we allow you to write regular Rust code and compile this down to Cerberus bytecode, Cerberus being the MPC backend that we wrote. So this means that if you want to write an encrypted program on Arcium, on Solana, you don't need to have some cryptography background or actually fully understand how all these things functions and whatnot. You can write regular Rust code, at the click of a button, compile it down to Cerberus bytecode, deploy this to Solana, and you're basically done. And yeah, I would be remiss if I had a whole tech talk and didn't at least have a little bit of code to show for this. So that's the next slide here. This is just a quick example of how, generally speaking, some Arcus code might look. The example here is a little voting program. And yeah, as you can see here, this is regular Rust code. The only difference is basically the inputs and the outputs here. As you can see, those are with the little enc generic struct here, which basically just means you're taking in an encrypted data. And yeah, internally, you're doing some operations on it. And then at the end, you return encrypted value once more. So yeah, in that sense, if you know Rust, you can use Arcium. And yeah, that means the last question to ask is, now that we've learned what it is, why it's necessary, how it works, how can I use it in my own app? So for that, we have 2 QR codes here. The left one is the Twitter. There you can, of course, follow the latest news on it and whatnot. But the more interesting one for developers is obviously the one on the right, which is our docs on how to actually build with it, which contains some examples, more information and whatnot. And yeah, if you're interested, feel free to scan it and help us complete our mission of having the majority of TPS on Solana be encrypted by next breakpoint. Thank you.
It's super, super cool stuff. There's a lot of different things in our ecosystem, in our network, but there's a lot of things that a lot of us don't understand. One of them for myself is prop AMMs. I get it at the high point, but it's very complicated. And so for all of us that don't know as much, I'd like to bring on Chris Chang, from co-founder of Ghost, also known as Sandwich.me, to talk about prop AMMs.
Hello, my name is Chris Chang, co-founder of Ghost, also the team behind Sandwich.me, the Solana metadata hub. Today, we'll be demystifying the inner works of prop AMMs. Prop AMMs now represent 90% of aggregator swap volume. They're a hot topic on Solana. And today, we will pop the hood and discover how they work, and then showing you how to reverse engineer them. And then we'll zoom in and look at the cat and mouse game between toxic flow and prop AMMs. So what is prop AMM? Let's read it quickly. Prop AMM looks like just another AMM from user's perspective, but they behave more like an on-chain market makers with active coding logic. They're closed source with private strategies and curves. And operators actively manage inventory and quote. They don't take deposit, and they oftentimes don't have front end. So you usually interact with them through aggregators. Some aggregators lean on prop AMM more than the others, but they are but they all make a dip big on them because their price is great. Prop AMM are very cool. They allow for permissionless swap. It's very competitive because they core very tightly. And update a core is very cheap, and so they can react very quickly. Generally, we see about 2 to 4 prop AMMs that dominate the industry, but landscape can shift very quickly. So we became very interested in prop AMM about 9 months ago. Since then, we improved our simulation and infra and built visualizer on Sandwich.me. So let's dive into the tech. For given prop AMMs, we want to build a quote function that takes input, direction, and relevant account, and then go from there to get the output amounts as you would get if you swap on chain. So we don't want to run SVN simulation to get the answer. The goal is to create a readable Rust port of swapping logic. So prop NM don't provide decoded or open core interface. To see the output at any given time, you kind of have to swap or do the simulation, but we don't want to do that, right? It doesn't reveal the how. So what we want to do is that it's to educate you guys. It's fun, and closed and obfuscated sources can raise the bar, but they shouldn't be impossible to read. Here's some important gotcha. There isn't a universal quote. Different signers and transaction composition can actually lead to different outputs. More on this later. So before going over the tools and technique, let's go over one of the popular prop NMs and how they work. You probably already heard or maybe even used SchoolFi. So let's look at how it works and think about it as an Oracle anchor market maker with some with some controls. So one is the inventory control, which keeps reserve at a target, and flow control, which rate limit how much can be traded at a given price tier per slot. Now the orange value up there are from the pool parameters. Still, Oracle protection is explicit. If core is too far away from the Oracle function, the core simply refuses to quote. So on layer 1, we have start from Oracle. Layer 2, adjust price based on this reserve and desired reserve. Layer 3, we penalize quote as Oracle becomes stale. And layer 4, we have execution across up to 10 lanes. And think about each lane as a separate tranche of liquidity of its own spread. The pool fill from the base tranche first, and then slowly walk down the ladder. So 10 lanes per side, each with its own cap, meters, and ppn spray. By the way, ppn is parts per million. There's also building backfill logic, where next lap, after being consumed, refill half of the lane's capacity. And then the following slot after that, if it hasn't been consumed again, then refill completely. And you can see why quoting is not smooth. It's actually piecewise with explicit state per lane limits. And think about total out as a result of filling your order across 10 lanes, right? We scan from 0 to 9, and if the lane is full, then skip it. Otherwise, we take as much as we can and then fill it in. And for the slide, we compute an out I, which using the lens quote, and then add it to the total out. And then the final total out then is the sum of the slide by slide fills. So now let's dive into how to reverse engineer one of them. So 3 pillars that we have in mind. We have simulator, trace, and static. A simulator is to execute transactions on the known state, right? And a trace is our fork of SBPF, which instructs the VM and logs structured trace of what happened. And static is we decompile the Onchain program using Binary Ninja's high-level intermediate language. And then lastly, we tie everything together using an AI agent. So everything is based on an accurate simulator. You need to be able to answer what would this user get running the state and this input mount. Ghost SBPF is fork where we instruct the VM, and then so that every meaningful action, such as function call, return, account rewrite, operation, the output is a trace pocket file. From the trace, we can then rebuild the code summary. Here we see a summary of Tessera V swap, which you can see which function were invoked and how often, as well as how many times each function reads write to the stack, the heap, and account data. It's a nice bird's eye view. With just the trace, we can then instantly follow the output backward and figure out how it was built up. And this is often a nice starting point, because then you can see how obfuscated a program is or isn't, and then get a sense of what's happening here. And now you can use the tool like Binary Ninja to decompile the prop AMM, which you then need to install a plugin from AutoStack, dump the Onchain program, and then select Solana. The TheraV has 415 functions, but a swap only touches 68. We use our code summary to explore those functions, and then putting everything together into a repeatable prop pipeline. One script simulates a swap, and then write a full report bundle. And then the idea is that for every single swap simulation, it becomes a case file for your AI agent to consume, or you can read it. Topologically sorting code trees also means that agent can start from the ground up, translate them first, and then keep on going up. The AI agent would get to get all the traces, metadata, decompile code. It's a glue layer. So now, let's talk about prop AM, actually, and the toxic flow. When we look at atomic ops and exclusively touch prop AM, they account for 5 to 10% of atomic op revenue. And reacting to toxic flow is one of the top priority for prop AMs. And some prop AM actually give a different output depending on which aggregator program and method that involves the swap. Many prop AM use the instruction sysvar to inspect full transactions, who calls me, and what the swaps are present and ordering. If not called by whitelisted router, apply PBS penalty. The TheraV, missing a proper Jidodong from, about 2 BPS penalty. If another prop AM swap is in the same transaction, Humidify may add 25 BPS. And then SoFi V2, 3.6 BPS. This is involving and bot adopt and cycle continues. So here's the arbitrage bot that has for discrimination. They start from one transaction to multiple transactions now with a single bundle. And then we look into atomic ARBs that has grown, and now it's the majority. And as you can see here, top pools, it lasts 30 seconds. And lastly, be on the lookout for unique data set coming soon. The data will execute every on-chain transactions, swap a prop AM against other prop AMs, and then what the output will have been. And then kind of like ideal post-facto G to understand the gap between execution and achievable execution. Thank you so much.
Thank you, Chris. Thank you, Chris. So I'm not going to even try to explain what the next speaker is going to what they do for work. I would completely butcher it, but she does important work on our chain, makes it much more efficient. Please give a warm welcome to Claire Fan, software engineer at Blueshift.
Hello, everyone. I'm Claire from Blueshift, and today I'm talking about SBPF linker and compilers. And so I think this tweet pretty much sums up the developer experience of Solana, that it is pretty terrible. And so part of the reasons behind that from the tool chain perspective is that Solana uses BPF, but instead of adapting from upstream eBPF, we created this custom SBPF backend and also maintained a fork of the Rust compiler. And so whenever there's an upstream upgrade or improvement, it takes time to pull down those changes. And sometimes it's so diverged that it's impossible to do so. But then, in my opinion, there's no real reason to do that because yes, eBPF is very constrained. It's something used inside the kernels, so it's very limited in many ways. But Solana compilers use LLVM that supports all kinds of targets and that don't have these limitations. And so LLVM is well capable of supporting these features. And so I believe if we can find the right transform path or configure the compiler in a proper way, then it should just work. And so I like to take this chance to demystify compilers, because I think a lot of people kind of treat them as a black box. But compilers are just softwares. It's a software that takes the source code of your program as input and runs through pipelines of transforms and generate code that you can deploy on your hardware. it's also the first layer that makes your program portable. That's why you can compile and run the same Rust program on a Windows computer, on a MacBook, or even on a Raspberry Pi. And that is because toward the final stage of the compilation pipeline, it starts to generate machine instructions. But like computers still don't read them, right? Like computers still only read binaries. And so we have to pack them into a bytecode format that these machines understand. So for BPF targets, they use the L format, stands for executable and linkable file. And it starts with ELF headers, program headers, and ends with section headers. In the middle is the sections you use to compose a program. And I'll use a Solana program to give you a concrete example. So Dean did anatomy on the SBPF bytecode. We basically figure out the sections we need to compose a Solana program. And so just like any other ELF files, it starts with the ELF header, which also tells you the architecture and entry point that points to like the first instruction got executed when you start a program. And then next, we've got 3 program headers for dynamic programs. But we also realized that for static programs, we don't need any program headers. And right now, the only thing that make a program dynamic is syscalls, because SVM does dynamic relocation for syscalls. And so that's why we've been pushing the direction of static syscalls, because if we do that, then we don't need any program headers. Like, we can save all these bytes. And so next is text section, which is the code of your program. So if you like decode these bytes, you'll get the disassembly of your program. And next, this program is logging hello Solana. So then the string is stored in the read-only section. And OK, this is not updated. So and then the symbol is referenced by one of the load instruction in text. And so next, we've got all these sections, tables to basically facilitate dynamic relocation for syscalls. I'll skip like how that works today, but basically SVM looks into these sections and tables and figure out, oh, I'm actually doing a solog at this code instruction at this program offset. So then again, if we do static syscalls by just encoding the hash of the function into the code instruction, then like we don't need any of these. And then the bottom part is the section headers, which indicates the size, offset, types of the sections we just went through. So like now that you understand this, like you can handle this, right? Like you can create a Solana program by just using Vim. But don't do it. You'll get me blocked by many people after this talk. And so how do we get here? How do we get here from upstream eBPF? And then like, what is upstream eBPF? So 5 years ago, an Italian guy added the BPF target to the Rust compiler, meaning that kernel developers can now write Rust programs and use Rust compiler to generate BPF programs and deploy them into the kernels. And because of the Rust compilation model, a BPF linker is added as part of the new target support. So Rust compiles each dependency, each crate, as a standalone compilation unit. So then we need a linker to basically merge all the dependencies and generate one single executable file. And so let's look at the bytecode that generated from upstream BPF through BPF linker. Right, so I'll just point out the difference here. First, upstream BPF does relocation for read-only data. So then we basically need to reverse the relocation and figure out which symbol is actually loading, and then encode that offset into the load instruction. And then second is upstream BPF does static syscalls. And so we do the opposite for them. We basically convert them into dynamic relocation-based syscalls, and then by generating all those sections and tables we just in the previous slides. And so then again, if like we do static syscalls, then we can save this big step, and then it works pretty well in the upstream. And so And so I hope things have become somewhat trivial here. To generate a Solana program from upstream eBPF, we only need two things. One is a BPF linker to compile ROS programs into one single object file, and then another tool to basically repackage this into a bytecode format that SVM understands. So we actually have that for a while. For people who have been following Blueshift, you might know that we have a BPF assembler that's not dependent on any LLVM toolchain. And this is actually what powers the SBPF linker. How it works is it parses the assembly program into abstract syntax tree. And this AST is capable of calculating offset, sizes, generating sections, headers, and encoding instructions, generating dynamic relocation for syscalls, and so basically do a direct bytecode generation for a Solana program. So the only difference between the assembler and the linker is just that assembler parses a string file, while the linker parses an object file. And so if you look at the code for SBPF linker, this is all it's doing. First, call the BPF linker to link to a single object file. And then we grab that object file, and then we reparse it and generate a Solana program from the AST. And so that's about SBPF linker. The last thing I want to mention is just that now that work with upstream eBPF is possible, and I'm quoting Ding here, we should stop being a bad consumer of the technology we're using. We should try to be a good contributor. Because, so for example, if I find something useful for the BPF target in general, we should try to upstream it so that people outside Solana can also benefit from it. To me, this is not just about credibility. I think from an engineering perspective, if I have an optimization path, the more people use it, the more bulletproof it will become, because it will be better tested and more edge cases will be discovered. And I think SBPF linker opens up that path. And so for people who are interested, check our website, follow our Twitter, and that's all I have today. Thank you very much.
Thank you, Claire. So our next speaker is going to be talking on fixing rent for DeFi and payments. Please welcome co-founder at Light Protocol, Swen Shefayuhan.
Thank you. This is bright. Hello, everybody. My name is Sven. I'm co-founder at Light Protocol. And you might have heard about us last year. We're not super in the spotlight usually, but last year, Breakpoint, we launched a protocol. It's called ZK compression. We launched it together with Helios Labs. And what it does is, just to give you a brief context, it reduces the data storage costs on Solana by orders of magnitude. And so it's a very powerful primitive, but I'm going to talk about some very specific products that we've built on top of this this year. And that's what I'm going to focus this talk about on. So a little hint, it's about fixing rent, specifically for Solana DeFi and payments. Now, you might wonder, first question, OK, so why does Solana need to fix rent for DeFi and internet finance more broadly? Well, Solana wants to be the market for everything, right? The everything exchange. And so, meaning anything that wants to be tokenized should be tradable on Solana. Now, to that end, we all know Solana has a very clear goal, which is 1 million TPS capacity. And they call it increase bandwidth, reduce latency. Now, the world also has billions of people. And so if you want to bring 1 billion plus people on chain and their ideas and their wallets, then what do? Well, you need to fix rent. Specifically, right now on Solana, if you want to coin something, this could be a piece of content, a piece of data, you actually pay $5 roughly for that market and for that coin. So most of that cost is going into various different accounts. Those are token accounts, PDA accounts, the mint account that you use when you that you get when you use the SPL token program, and metadata accounts. And structurally, these markets and coins, they're kind of permanent. You can't really close them again. And so what that means is this $5 cost is effectively a fee or a tax that you incur on Solana right now. Now, if we look at the competition right now is much cheaper, actually roughly 100 times cheaper. So if you coin something on Base, for instance, it's roughly 5 cents. Now, I think we all agree, I think we should be much slower with the rent exemption cost on Solana. And so, it would be nice if we could undercut Base even. Maybe something like 2 cents would be quite nice. And effectively what this is we need to IBRL, but also for account creation cost. And so that's why we've built, over the last couple of months, the Light token program, which we're announcing today. And it's basically a high-performance token standard that is specifically for rent-free internet capital markets. And so what does that mean? It's kind of like SPL token. It feels like SPL token. But it's also 200 times cheaper to create these mint accounts and these token accounts that you use when you interact with the SPL token program. Now, there are 3 very important things that you need to deal with if you want to build a token standard that actually is usable in DeFi. And this is kind of from all our learnings, from building ZK compression, bringing it to market, and learning from customer feedback, etc., what worked, what didn't work. And so there's 3 main things. Well, first of all, it has to be rent-free, right? That's the value prop that you take if you want to compete against something like the SPL token standard. This is fixed, 200 times cheaper allocation cost. We figured that out a while back. So actually, 200 times cheaper, if you look at it, it's roughly in that area that we want to get to, right? So it's actually undercutting Base. We're cheaper on the Solana L1 than we are on the Base L2, which is kind of nice. And now the second thing, that's the most difficult part, is your program has to be super high performance, right? So it needs to be at least like SPL token with regards to performance. Performance meaning compute consumption as you do transfers, as you do trades on chain. Otherwise, your new token standard will have no chance in the market. So basically, we figured that out with our Light token program. Turns out it's actually pretty competitive with SPL token and then also with the upcoming P token in specific hot paths. So, and the last part is you want to have great UX, and that's super important because there are a lot of different DeFi players and clients. So when we designed the Light token program and the SDKs, we really thought through that and how we can create really great UX and make it easy for people to upgrade. So we spent a lot of time on this to get the SDKs right. The solution to this is the token interface SDK. If you interacted with token 22, which is another SPL token standard, and if you've built something that supports this token standard, you kind of already use token interfaces. And it's a really neat design. You basically say, well, there's an interface, and it kind of supports all these different token standards. And so what we've built is an SDK that does just that. So here you have an example, just Radium fork that we made rent-free. And you can see it's just using the Anchor's existing interface account feature. It kind of just works. This is just the program side on this side. So I'm going to show you a couple of quick examples, walk you through the snippets really quick. You can see that the interface is matched. The call signatures are very similar. On the left side, you see the SPL token programs SDK, and then that includes SPL token and token 22 tokens. And then on the right side, you see our transfer interface SDK, which includes the light token as well. So it supports all three. Now I'm going to play this demo real quick on DevNet. So the token program is on DevNet right now. And you can see it's just a lot of setup. On the left side, you see we stream with laser stream, which is listening to the transaction events. And we're seeing a token transfer. And then there you see it's extremely efficient on the CO cost. And also what this transfer did is in the first instruction, it's a compute budget. In the second instruction, it's creating an ATA account, an associated token account, and see it's extremely cheap. It's much cheaper than the SPL ATA program. And then the third instruction is a regular transfer from one light token account to another light token account. And interestingly, you can also see that the actual fee paid for the token account is much lower than what you'd pay to allocate an SPL token account. Cool. Anyway, so to move on and go to kind of a quick summary to showcase all the different features of this kind of rent-free stack. We now have rent-free ATAs, already seen that. Rent-free SPL support, so the light token program actually supports wrapping with SPL. And then we have program-owned token accounts as well, mint accounts, and also token metadata, and it's all rent-free. So here's just a quick example to show you that it's very easy using these macros to create a new mint with metadata. It's very simple. And then just very quickly, I want to go into the how. I'll spare you of all the deep dives on the tech. But essentially, the insight is that you can distinguish between hot state and cold state. And so what you see is you have a DeFi pool, for instance. It's hot state, it's very active. But at some point, and you see this if you look at the chain, you look at the block explorers with meme coin launchpads, etc., you will see that these accounts become dormant at some point. And so when that happens, our miners can compress them into Merkle trees. You see that there. And that's using ZK compression, by the way. And then now the last part is really just, you might be wondering, well, how do you load a compressed account without actually impacting the UX of all these different clients and programs? And we do that with this little helper. It's called the load instruction. And so it just dynamically checks if a transaction interacts with a cold account, and it loads these accounts atomically into the transaction. And you can, in many cases, you can actually do this atomically. For instance, on Radium, you can actually load a whole cold market in one transaction and still execute a trade on it. And here you see, it's just this extra load instruction in front of the regular transfer instruction. Cool. So to close this up, it's live on DevNet right now, the token program, and coming to mainnet really soon. And the SDKs are live. You can use them. If you scan the QR code, you'll get to the Twitter account, which gets you to the docs. It's all open source, and I hope you check it out and start building with it. You know, if you're a DeFi team, Launchpad, or even a payments company is looking to reduce the storage cost of ATAs, hit me up, find us. We're here at the conference. You can DM us on Twitter as well. All right, thank you.
Thank you, Sven. I know a lot of us are going to be messing around with that later. So next up to the stage, I've got Michael Gildenberg. He's going to be talking about oracles and how BAM is changing the execution framework. CTO of Switchboard and Dr. Blocks. Give him a round of applause.
Perfect. How's it going, everybody? Thanks for coming. I loved presenting at my 5th Breakpoint here. It's been a long time coming, and we're really changing the space now. My name is Dr. Blocks. We'll go with Dr. Blocks, and I'm CTO of Switchboard. And we've been an Oracle provider for Solana for about 5 years now. And you know, in 2020 and 2021, 2022, there was a very different model for how to connect information to blockchains. And we'll get to how this has changed over the years now. So really, when we started Switchboard, there was only a single method that people really used to push information from off-chain to on-chain. And when you think about why you need oracles, it's really because you have a large source of information that's actually off-chain, that is actually from the internet. And when you think about information from the internet versus information from on-chain, there's actually not a clear way to come to consensus on what that information is. If I am pulling some data from a website, how can I actually verify what this is? And this price is honest and true, and actually a strong and legitimate price. So what we build is something called oracles, which is a consensus mechanism for information. This can be information from the internet, information from actually first-party sources that actually produce this information. But Switchboard actually turned this a bit to be a platform to build your own oracles. And you can actually make a layout of how you push and transform this information on the blockchain. So Switchboard is actually the first Oracle platform where you can build your own information workflows and sources. So with that, we actually launched our push Oracle in 2021, but they've been around since 2017 with the advent of Chainlink or so. And the first 2 years, we were doing between 3 to 7% of Solana's traffic. This, of course, pushing this data constantly, even when it's not used, is highly inefficient and unsustainable. And with that, we actually had this advent of what we call a pull oracle, which you pull this information on-chain when the user actually needs it. What we're coming to now is just-in-time oracles. And when I actually talk about this, we're talking about this whole execution environment for when you only pull information when somebody has already used it. So you don't actually have this flow of needing to constantly update this information or even letting the users be subject to choosing the ordering. So yeah, in the push model era, 2017 to 2022, this was very expensive because a lot of this was before the advent of Solana. Some of this and most of this was actually in the EVM/Ethereum days, in which Chainlink was trying to push information for a lot of first-party assets on-chain, but because it's so expensive, it could be hundreds of dollars of gas fees a day, maybe even thousands. They actually had a heartbeat interval of 30 minutes. This is fine for things like lending, because lending is actually over-collateralized. And if you can actually make a system that you can check the volatility of how far things can actually manage to be pushed in a 30-minute period, and it's over-collateralized, there's actually limited risk to doing this. So when you have oracles and it's actually at this cadence, you can do it for certain types of DeFi, but it's focused on lending, and we don't get to many more derivatives other than maybe started the add-in of early perps. And there are applications like GMX that found ways around this. And when Oracle started to speed up and we started seeing updates per minute, GMX actually implied a system of they'll take the worst price before and after a trade, making sure that people executing trades could not exactly front-run the Oracle's price. Then we get to the pull model, where we actually delegate the responsibility of pushing the information of oracles to the user. And in this way, it's much more practical for oracles to actually operate, because actually, even on Solana, there was getting to the point that some Oracle platforms were stipending their oracles $500,000 a month just to keep information up to date. Unsustainable for any platform that's pushing information. And also, if nobody's using the information between requests, it's wasted money and wasted block space. So with this pull model, it allows these users to actually request the price be updated only when they want to use it. And there's actually an off-chain consensus layer for where all this information goes. And when it's ready to be pulled on, the user pulls it on. Beyond that, beyond having just a consensus layer, since Switchboard is a permissionless platform, we actually employed this new model that we called an on-demand oracle, where the information isn't only just brought from another layer onto the blockchain that you want at that specific time, but the oracles actually do the work to go fetch the information right when the user's requesting it. And with this, it becomes a lot more practical to start running some of these more high-fidelity applications. So if something like a perp dex, you can actually start doing this at sub 5 seconds for the whole flow to get this information. But really, this is still not competitive with centralized perpetuals or centralized dexes even. So, or spot prices, excuse me. So when you're looking at these future platforms, when you're looking at actually competitive, or you could say prop perpetuals that we're going to get to soon, or prop AMMs for spot prices, there's a whole different flow you have to employ. But this really did open up the bar for having something that's pretty competitive for use case for perpetuals on-chain, or even margined spot. So now we're getting to this whole year where everyone's talking about prop AMMs. It's prop AMMs everywhere, and they're taking over all the spot traffic. So what actually is a prop AMM? You know, for some context here, many of you are going to know exactly what an AMM is. You have basically a book. It's not an order book, but it's basically a market that has two treasuries of assets, one in a base token, one in a growth token. And you can actually get the price of these tokens based off of the curve or the levels of these pools. And as one side of the pool depletes, the other increases. This changes the price. This still is not great for price discovery since it's algorithmic, and not actually what a market maker is willing to quote for all of these services. So when people actually deploy liquidity, it is still mostly off-chain. Now we're getting to this point where we have prop AMMs where people are saying constantly what they're willing to quote, and they're actually pushing their own Oracle updates every single slot. Although this is very expensive, we've come to the point where Oracle updates are extremely cheap. We've optimized this down to 20 or so compute units on-chain, and if you actually push this every slot, you can get up to about 70,000 to 120,000 compute units per asset. And if you can actually expand on this to more compressed updates, you can get a little more advantageous. But even so, with this, we're seeing a lot of updates. And if you're actually going to be expanding to all the prop AMMs coming up, this is millions and millions, an epoch that are going to be spent just to support a few prop AMMs. So is this really sustainable as we're going forward for Solana if everyone's going to have a fair and balanced chance to actually make these applications? So now we talk about how we're limited in Oracle updates. When you're actually submitting an Oracle update for these prop AMMs, they're trying to squeeze these prices and price updates as tight as possible. If you're trading on the New York Stock Exchange, they're talking about 50 microseconds for price updates and a change. If Solana or any decentralized system is going to compete with that, we need to be coming to that as our golden bar or golden standard. So we come to this one slot problem in which we have a single leader that has multiple Oracle updates they're seeing. Why would they not be motivated just to drop all the other transactions that are in a less than beneficial spot for them to execute their own trades? Why would they just not use the single best price update that they get? So when you're actually getting updates from a prop AMM, it's not incentivized for them to do more than one Oracle update per slot, because these validators can basically freeformly drop whatever Oracle updates they do not like. So enter Jito BAM. Now we have actual marketplace for ordering transactions. This is going to be coming very soon to Solana. Jito is just finishing up their execution of this, and I think it's going to be a very big revolution of how we order blocks and how we can verifiably order blocks to prevent sandwiching. Now, if you can actually verifiably order blocks, you can have multiple updates in a slot. So this is intra-slot price updates. So even though Solana slots are 200 milliseconds, we can actually do price updates at any point in the block. Now we can actually get to the microsecond level of pricing and trading. So when you have these solutions like 00 that have actually really optimized the networking layer between all of the validators, we're really seeing the benefits of this coming into fruition, because now we no longer care about the distance between when slots finish. If you can get a price update before the Oracle, before the next Oracle update actually finishes, it's still very, very meaningful for you. We're running out of time, so I'm going to speed through the rest of these. But anyways, when Switchboard is created, we're enabled to make all these new mechanisms for people to push these prices. If you want to get the NAV price of your own treasuries, you can do that now, and that's exactly what Keel did for instantiating their $2.5 billion fund for MakerDAO on Solana. They've actually used Switchboard to get their NAV price. You use this for prediction markets, just how Jupiter is using this with the Kalshi data on Solana. And now we're doing this for prop AMMs. And with Switchboard actually doing their own BAM plugin, now people can freeformly add their own Oracle updates into the BAM layer to not spam the network and only put Oracle transactions right before trades actually execute, and do this verifiably to not waste their own money. So this is kind of the summary of the bespoke tactics that BAM will actually employ for Oracle updates. And really, this whole block auction mechanism employs a whole new flow for actually ordering and pricing how much these updates are actually worth in value for making these trades. Summary there. Key takeaways here: the evolution of oracles has gone from a push-pull back to a very efficient push-put oracle or program-based. And now with Jito BAM, we can make a platform for people actually executing oracle updates just before trades. So be as efficient as possible, as timely as possible. Now, it's really interesting now because with the advent of prop AMMs, price discovery is for the first time ever moving on-chain rather than off-chain. And now it's very interesting because now people that are quoting prices might look on-chain or on Solana first before even a SEX. If any questions here, please message me. I am Dr. Blocks on Telegram or switchword XYZ. And please look at our docs and message with any questions. Thank you so much.
Oh my gosh, thank you so much. We've got another great talk coming up next. So around 6 months ago, this was the CTO of Corda. They announced that they were moving the Corda blockchain to Solana. He's the wizard of RWAs, CEO at R3 Labs. This is Richard Brown.
Thanks for that introduction. Hi, everybody. Yep, so I'm Richard Brown. I'm CEO at R3 Labs. Now, don't lynch me, but we're the firm who invented the private permissioned blockchain. So over 10 years, we've built dozens of live networks. We've got tens of billions of dollars of assets issued across them. But there really is only so far you can take that model. So yes, we've got these dozens of live networks, billions of assets. Most of the world's largest financial institutions are using our technology. They're transacting across these Corda networks. These banks, these financial institutions are also our shareholders. So in the TradFi world, the Corda ecosystem, the R3 ecosystem, it really is a big deal. But there's only so far you can take this. There's only so far you can take these private networks. So as soon as the regulatory affordances, as soon as the regulation allowed, we were looking as fast as we could to figure out which of the permissionless networks could we wholeheartedly align to. Back then, I was CTO, so I led the work that analyzed these networks and concluded wholeheartedly and decisively that the network we should align to and converge to was the Solana network. And you know what? 6 months in, we made the right choice. It's just so obviously the right choice then, and it's so obviously the right choice now. So I'm going to talk about 3 things super quickly. Very, very quickly, what were some of the reasons why we, as representatives, if you like, of TradFi or of Wall Street, why did we select the Solana architecture? What was it that stood out to us? Number 1, I'll do that super quickly. Second thing is the internet capital markets. It sounds like a meme. I suspect there are probably people in the technical stage rolling their eyes when this supposed marketing phrase is uttered. But I think there is a genuine technical underpinning to that, which I want to articulate. But there's also a key missing piece, which is a real-world asset marketplace that is preventing the full success and the full rollout of the internet capital markets on Solana. And I'm going to talk about that. And then I'll announce what R3 Labs is launching at the start of next year to fill that gap. So, already too slow, so I'm not going to talk about the technical case for Solana. You can read my blog post on that, except to say the underlying architecture, the way that the transactions are processed in parallel by each transaction committing to the part of the ledger it touches. It seems so simple, but obviously to everybody in this room, it's the reason why the transactions can be processed in parallel. The EVM can't do that. SVM can do that. It's absolutely critical to being a compelling and credible target for Wall Street to move its transactions to. So when we're out there talking about Solana, we shouldn't hide or be shy to talk about its architecture. It really is a really quite clever design that can't be replicated by the EVM ecosystem. Also don't have time to talk about what we're doing to bring all these live Corda networks over to Solana, except to say again, starting next year, there will be a live Rust program that is able to process Corda transactions, so R3 transactions, live on Solana mainnet, providing consensus to any of the existing private Corda networks that wish to opt into that will also allow them to bridge their assets over. What I want to talk about instead is the internet capital markets and how I think we can be better at explaining what we on the Solana side are doing to traditional finance. Because when I say capital markets to a regular traditional finance person, This is the kind of thing they think about. So this is just a tiny diagram of one tiny part of the traditional capital markets, how shares are bought and sold and how they move across. So when we talk about things like, so there's a whole bunch of things, central securities depositories, brokers, custodians, all these things. So when we talk about things like looping and decentralized lending protocols and AMMs, they kind of like their eyes glaze over and they wonder why we're so excited about what we're doing. But it's not because those terms are wrong or mad. It's because a lot of what we're doing has already been done by TradFi. It's just been done on a very isolated and disparate scale. So we say collateralized lending pools, they think repo. We might say yield boost with looping, they think securities lending. So these features of DeFi, specifically Solana DeFi, that are so powerful, it's not them individually that are so powerful. What it is that they're all in one place. So back to the technical case for Solana, the fact that there is a single high performance, high bandwidth, low latency, relentlessly high performance, single shared substrate, single shared layer one. It's an unbelievable killer feature of the Solana platform because all these different things, whether it's the lending pools, the dexes, the looping, all these different features, many of which exist in isolation in TradFi, are all in one place, endlessly composable. That's the killer feature, and that's what I think enables the internet capital markets to be built specifically and exclusively on Solana. But there's a missing piece, and I guess this is like the key part of my talk, which is it's fine to have these on-chain capabilities. It's fine to have on-chain self-referential yield, if you like. But it's only when we can bring a huge amount of real-world assets, real cash flows originating from real activity in the real world, it's only when the full power of the capital markets can converge. But right now, if I look at what's actually been achieved with real-world assets so far, there's so much further we can go. It's almost as if there's kind of like an impedance mismatch. There's all these assets that could be brought on-chain, whether they're bonds or equities or funds or whatever they are. But just because they can be brought on-chain doesn't mean anybody on-chain will actually want to buy them. And that's perhaps not surprising. If those of us in this room who've lived on this ecosystem, we're used to better. We're used to what the on-chain markets can provide. We're used to being able to access things, access assets anywhere in the world in any ticket size, with instant liquidity, even if the underlying asset is illiquid, with yield that is actually commensurate with the risk we're taking. But there's an impedance mismatch. That's typically not what's being supplied. Now, of course, that's also a solved problem. That problem was solved in the traditional financial markets by a little technology invented, depending on who you ask, maybe 101 years ago, the mutual fund. That's the solution to this problem. You've got some assets that aren't quite right for what the investors want. You package them up in the mutual fund world in a legal structure with perhaps a layer of liquidity or a layer of structuring, so that what pops out the other side is exactly what the investor wants. But it's slow, it's clunky, it's a centuries-old technology, it's expensive, and it doesn't do a good job particularly for anybody. But there is a solution. There's a direct parallel in DeFi. It's the yield vault. It's an on-chain contract, very cheap, very quick, very easy to write, that does exactly the same thing, but permissionlessly on a network, on a permissionless network. You can own the underlying assets, and then with a curator, think of it as a fund manager, they can then mix the assets in the right form, with the right liquidity, with the right liquidation profile for the underlying investor. So that's the missing piece, if you like. That's the way to bridge this impedance mismatch. So this isn't a technical problem. This isn't a software engineering problem. If you like, it's a financial engineering problem. If we could somehow transform the assets from what are being supplied off-chain into what's demanded on-chain, suddenly we can unlock explosive growth in the availability of real-world assets, and hence complete those internet capital markets. Move it from being, say, something of a marketing term to being something that is a genuine description of what can be achieved, and can be achieved solely on Solana, going back to that point about it being a single shared, massively performant substrate, rather than a collection of satellite L2s and private networks. So that's what R3 is bringing to market. So R3 Labs, early next year, will be launching the real-world asset marketplace for Solana, a single unified place where off-chain traditional issuers can issue their assets in a way that will in a way that will give them distribution directly into these on-chain vaults that are curated by a collection of high-quality curators who can turn these assets into a form that the on-chain investors actually want to and actually can buy, and importantly, can then connect directly into the DeFi ecosystem. So that bridging of the world giving the asset issuers what they want, which is distribution in the right form to what the people on-chain want, which is assets that actually meet their needs with the right access profile, the right liquidity profile, and the right yield. It sounds so simple, it sounds so easy because it has been achieved to some extent, albeit very imperfectly on the traditional side. What we're doing is bringing it onto Solana to be the on-chain real-world asset marketplace. So there's a lot more to talk about. If you want to be one of the first to give this a try, make sure you register at corda.xyz or go to enter your Solflare Quest code there. But just to finish, real-world asset marketplace can only be done on Solana because of Solana's unique architecture. We chose Solana as the representative of a huge amount of TradFi for a reason, and I haven't regretted that choice once. So thanks very much for your time, and I'll speak to anyone afterwards. Thank you.
Thank you for that. Well, everybody, I'm going to be taking off and leaving you for now. We are going to take a short break. Next session will start at 3:50. Look forward to seeing you then.
How's everyone doing? Yeah? Are you ready for the fanciest time of the evening? We now have the Anza block. So I'm excited to welcome Brennan Watt, VP Core Engineering, to talk about Anza and what they have cooking. So Brennan.
All right, thanks Manish. So I'm Brennan from Anza. We're going to have a few Anza folks here. I'm just going to kick stuff off and cover things at a high level. So as you all know, at Anza, we're heavily involved in steering core protocol development. Most notably, we build the Agave client. And during the next 9.5 minutes, we're going to go on a journey and recap a few exciting wins, but more importantly, illuminate the path of where we're taking the protocol. And we'll structure things by talking about these categories on the screen one at a time. And we'll start with resiliency. So that's almost 2 years of solid green liveness, around 200 billion transactions. And the message is Solana stays up, right? And it keeps servicing transactions. And that's been the case for a long time now. And I think October 10th really served as a proof point of just the level of maturity of the Agave client, but also the Solana ecosystem and its ability to handle immense transaction load and keep packing thousands of user transactions per second. And through all of this, we've kept the Agave quarterly releases rolling out like clockwork. The 3.1 release is coming up next before 4.0 brings a bunch of new, exciting, fun stuff in the new year. And the reason we're able to keep this aggressive cadence is because of the immense stress testing and red teaming that we perform. The Validator team at Anza is attacking the public testnet with a unique set of attacks triggering every hour. And we haven't been super open with what this team does for what I assume are obvious reasons, but we've fixed enough of the problems at this point that I think we can give this team a little bit of shine. So the attacks mostly fall into two categories. We've got network DOS attacks, and we're stressing load shedding, back pressure handling, things of that nature. And the second bucket is these highly curated blocks packing with super strange transactions, stressing the far corners of the SVM and replay execution. And this graph just shows our malicious testnet node cycling through those attacks. Here's an example of a malicious node hosing down a bunch of the other nodes with gigabits per second of network traffic, but the network was still screaming along, making blocks on time, tower height steady at 32, all the things we want. But this wasn't always the case, right? We used to be able to make nodes crash, then we got a little better, then we could disrupt nodes, then we got a little more better, and now we can handle these things without a hitch. And it's only this level of paranoia and obsession that helps us provide the confidence that it takes to ship this aggressively. And we've been shipping a lot. 2025 has been the year of IBRL on Solana. We've got a lot to talk about here. So let's start by talking about the major resource bottlenecks. We have about 4x headroom on compute side, so plenty of excess there. Similar story on disk. For the typical case, we've got a lot of excess capacity there. Memory, this has really been the story of this year. We've cleaned up so many things when it comes to memory, so we've created headroom there as well. And on the network side, we've got a lot of validators running 10 gig or 25 gig NICs, and so we've got lots of headroom there as well, assuming we load the dang thing properly. And we were able to translate this into 25% throughput improvements on Solana mainnet this year. And even if we're not always filling the blocks, having that burst capacity is super important, right? You get an economic activity like as simple as a market open, the blocks are full. It's really nice not to leak that economic activity. And as I'm sure most of you know, throughput is governed by block limits. So we raised the overall limit from 48 million to 60 million CUs this year. And we tend to meter on these compute unit things. So every BPF instruction, serializing data, precompiles, all this stuff gets translated into CUs. We also linearize account data loading into CUs for reasons. I mean, I could rant on this stuff for a while, but I think the bottom line is we want to constrain things so that we can keep slots coming out every 400 milliseconds. So why haven't we activated the 100 million CU increase yet? Well, the key feature enabling this is creating a kernel bypass for the network layer. And it's funny because we often talk about network being the bottleneck for blockchains or like the Solana blockchain, but it's kind of not true actually at the moment when it comes to Solana. I wish it was true, but we're actually not saturating the NICs most of the time. But we do often max out on slamming the send M message syscall, allocating memory in the kernel, and context switching. And XDP bypasses this by allowing us to interact with the NIC from user space. and increase throughput of this performance bottleneck by 200x. And this chart shows that latency difference between the legacy Agave code in blue and the new and improved zero copy XDP code, the purple line down at the bottom. And notice that we had to make the y-axis log scale so it would even show up. I mean, this thing is crazy fast. And call your validator today. This is in 3.0. Tell them to turn it on, right? We need critical adoption, and we'll get those 100 million CUs. There's another important block space limit that we've increased, and that's we've doubled the amount of throughput to the hottest accounts. And these are often the most popular assets, or it might just be the pump fund global volume accumulator. I don't know, but I digress. And this chart shows when we doubled that limit from 12 to 24 million and how users immediately gobbled it up. In addition to increasing the block capacity, we've also increased the ingestion TPS, oftentimes sustaining 100K TPS on mainnet. And this is essentially a measure of how efficiently we can move bidders into the auction house, which is really essential for building efficient markets, because to have an efficient market, the highest bid needs to win. For it to win, you have to actually look at all the bids. Right? And this used to give us a lot of problems because allocating all the memory for all these packets caused a lot of churn and a lot of issues. But we've been able to overcome a lot of that. But this is the historical reason for why we used to use stake connections, stake-weighted QoS for managing this. So we had something else as kind of a heuristic for quality transaction flow. And speaking of connections and ingest, we're making some changes to the default limits. So we are increasing the overall ingestion constants to 1 million packets per second. We're increasing the number of unstaked connections from 500 to 4,000. And we're unthrottling the per connection packet limits when global congestion is low. So lots of good fun things coming to get more transactions in. And finally, Alpenglow is coming. And Alpenglow, of course, is the new consensus engine that we're dropping in to replace Tower. It reduces transaction finality times down to 150 milliseconds, comes with increased safety, and enables us to have some much more intelligent ways of defeating the slot laggers. We first announced Alpenglow in the middle of this year, but we've made a bunch of progress. So we've been running a 50-node globally distributed test cluster under load for the last more than 4 months. And we've had so few problems, I fail to believe it sometimes. I had to get in there and make sure it's actually running stuff. But the team's really been cooking on this one, doing amazing stuff. And we're working to get this feature complete and rolled out on testnet early next year. And this also sets the foundation for a bunch more interesting stuff, such as better market structure. So Solana showed everyone that blockchains can be fast and affordable, and now we're going to show them that they can be fair and highly efficient while remaining trustless. So how are we going to do it? It's multiple concurrent proposers, or MCP. We're ending the single builder monopoly. Users and dApps want optionality in regional network latencies, traders want to have censorship resistance, and MCP is going to deliver all these things. And there's no middleman here. This is all the validator just playing different roles, right? So yeah, just keeping that pipeline flowing from the client. And we're already incrementally building towards this vision. We'll start shipping features to move closer to this ideal state with each release in the coming future. And by the way, I've been collecting the receipts of everyone doubting us, saying that MCP is going to take 2 years. Spite-driven development is the most amazing thing ever. Thank you for fueling us. All right, the last thing we'll talk about is DevX and OpEx. So we've heard the cries from the community. The rent is too damn high, and the transactions are too damn small. And so we're going to fix this. We are lowering the cost of state on the blockchain to make it more affordable for projects to bootstrap. Lots of users, lots of accounts, all that good stuff. I believe the state bond is somewhere around $1 million per gigabyte on mainnet, which, I mean, you get a lot of replication on Solana, but still, like, NVMEs are, what, 10 cents a gig? So this is a little crazy. We're going to do better here. And we're also increasing the transaction size up to 4 KB. So this is going to allow us to touch more accounts without using ALTs, and be able to craft more complex atomic operations in protocol. On the operational side, we're going to stop wearing out your disks so fast. We're making restarts faster, and we're going to do this by slowing down the incremental snapshot frequency, using win code instead of bin code for faster SerDes, and being smarter with what we actually write to disk. Yeah, shout out win code. Yeah, thank you. All right, and finally, SIMD 123 is going to ship, and so we're going to make it simpler for validators to share revenue from different sources with stakers and infra providers in protocol. Delegated stake directly increases the number of blocks you get. Those blocks can be valuable. We're bringing a lot of trading activity to Solana, and so it's important that we have a fair way of sharing those profits with stakers. All right. That was a whirlwind look at all the exciting protocol changes that are coming to Solana. Thanks for listening. You should now be properly amped up for all this cool stuff that we're going to ship next year. At Anza, we don't do roadmaps, we do releases. Follow me on X to stay up on all things agave. Tune into the Anza blogs. And as always, the real alpha exists in plain sight on GitHub. All right, thanks, everyone.
All right. Thanks, Brennan. The next on the Anza block, we got Alessandro Decina. Come on in.
All right. Just in case anyone is wondering what it's like working with Trent, I recently discovered I have anxiety to ship. We were having a conversation on Slack where I was profiling Agave 3.0. And I saw a slowdown, which we fixed. And so I was making sure that we backported the fix to 3.1. And yeah, this is what I get from Trent, to which I'm like, you're welcome, Trent. So today, I do want to talk to you about some of the things that I am very anxious to ship and that we're shipping soon, starting from XDP, which is actually in 3.0. We've been telling you, we've been asking you to test, because this is the one thing that will allow us to increase block space. I don't know if you remember, but at Accelerate, I showed you some performance profiles of XDP while we were doing some load testing. In the meantime, we've been doing some actual testing on both testnet and mainnet. And we measured that a turbine with XDP is as far as 200x faster than the legacy turbine with sockets, which is amazing. And you've also been helping us in testing different drivers and hardware. And we found some bugs, and we have fixed those bugs. So this was me sending a patch to the Linux kernel, fixing a bug in the Intel driver. And I have a patch coming for the Broadcom driver as well. I am mentioning this because we are literally the only team across all of blockchains sending patches to the Linux kernel, right? Probably something. The AFXDP that we created for Agave is not only usable within Agave, but it's a standalone, reusable, general-purpose crate for Rust. And so it can be used by any project. And Harsh from Tinydancer has been contributing the receive side of the code. My initial implementation only included the transmit side, which is what we use in Turbine. I've been helping him with some performance tweaks, but he's been doing an amazing job. And now we're planning on integrating this code in TPU in Q1 next year. So we will also start ingesting transactions using XDP soon. Also, the guys over at the Overclock Validator, one of my favorite validators, so please go stick with them. They just released Shredcaster, which is a Jito Shredstream-like crate project that can be used to stream shreds outside of Turbine. But because it uses XDP, it has much lower overhead and sends with a much lower latency. So if you're using Jito Shredstream, consider also checking out Shredcaster, which uses Agave XDP. Another huge thing that we just very recently released is Wing code. As you may know, Bing code is the serialization format used by Solana, both in protocol, regrettably, and by on-chain applications. Bing code, as far as the bitwire format goes, is pretty good. It's not too bad, but the implementation is extremely slow. This has been a long-standing issue in Agave, because often we found bottlenecks in Bing code-related code, and we had to fix them, and this happened like dozens of times. Until a couple of months ago, when Zach, tired of fixing the same bug over and over in different spots in the code base, created Wing code. Wing code went from not existing to being the second fastest Rust serialization library in the first release. Obviously, when we saw that, we all went to Zach, and we told him that we were extremely disappointed that it was second fastest. So the second Wing code release is the fastest Rust serialization library available today. Also, at Accelerate, you might remember I showed many profiles, including a profile of Agave crossing the epoch boundary. At the time, I don't remember exactly what release we were running on mainnet, but it used to take more than 2 seconds to cross the epoch boundary due to some computations that we have to do right at the boundary. I told you that we were starting to look into them, and yeah, we've been looking into them. Now in master, we can cross the boundary in less than 400 milliseconds. We are very close to not skipping slots anymore. We still sometimes do skip one slot, but Michal is working on a fix so that we will never skip blocks again. Shout out to Horan and Michal for the amazing work that they've been doing here. This is probably the most exciting change that is coming to replay in Agave. This is 10 seconds worth of profiling Agave while doing replay of mainnet transactions, actual mainnet load. If you see the red lines, the red markers in the profile, each one of them is a disk operation, right? In these seconds alone, there's over 1,100 disk operations, right? That is bad because every time you hit the disk, you need to wait for the I/O request to complete, so that adds jitter to both banking and replay. And also, it's bad for the lifetime of your disk, right? The more we write, the sooner your disk wears out. This is the same profile with the code in master, and I actually believe that we backported most of the fixes to 3.1. You can barely see the markers. In these 10 seconds, there's less than 80 I/O operations. So great work, I/O people. And it's actually pretty funny that the accounts database is probably the component that has improved the most in the last year. Because when I first started this performance push almost 2 years ago, whenever I tweaked something in Agave and I wanted to recompile and restart the validator to see whether my fix was effective, I would have to wait more than half an hour to restart. And I would go to Brooks and complain, like, why does it take so long to restart a piece of software? It's like mental, right? And the answer used to be, why are you so obsessed with restarts? Maybe just don't restart. And I was like, but this is where we are today. It used to take more than 30 minutes to restart 1.x. 2.x restarted in less than 10 minutes. 3.1 will restart in less than a minute, and 4.x will restart in less than 30 seconds. And this is only with the changes we've done to the accounts DB. Does not include some changes that we're planning to do to replay and repair. So we will start even faster. And finally, at Accelerate, towards the end, I showed you some bugs in the scheduler, including this one, where the scheduler is actually busier doing some overhead synchronizing with POH instead of actually executing transactions. So in this specific profile, we're spending 61% of the time, the banking time, so while Agave is a leader, just doing this overhead, not actually scheduling transactions. And this is 3.1 instead. We have completely fixed the bug, and the workers are busy. They're processing transactions for 91% of the time, and the remaining 10%, you just need to send more transactions, okay? This is how that conversation ended with a trend. I love 3.0. It's the fastest release we've ever done. 3.1 is so much better, and I can't wait to release it. Thank you.
All right. There we go. The next up is Max Resner. Please give it up for Max.
Hi, everyone. This is the MCP final V2 final this time, for real. We've been talking all year about MCP. I want to talk about the first steps to getting it into production. But first, let me tell you why we've been talking about it all year. Solana is fundamentally for trading and about trading, and it has been from day one. That's why we started off with Serum. But now we're here. We have these new prop AMMs. And the question is, how do we accelerate that, make it better at the protocol layer? So let me talk you through some examples. Usually in finance, we have these kind of common value things that look like auctions. So here, the yellow, we don't know where those candles are going because that hasn't happened yet. But the green and red, those are candles that have already happened. So that's our setting here. And usually we'll have something like a prop AMM Oracle update that will happen at various times. And one thing that's interesting in our current structure is there's a single leader, and so everything goes through that leader. And so that leader gets to act slightly later because they can co-locate with their validator and they can insert things right at the end. But what happens when that leader decides they want to be the only person who's allowed to submit new information to the chain? In the current protocol, they actually can do that. And we actually are seeing some interesting stuff on mainnet where oracles are not getting in for various reasons because of late packing or because of other reasons. And so this has kind of transformed from not necessarily a theoretical attack to something that's going on right now on mainnet with late packing. So we want to guarantee with MCP that censorship resistance is impossible. So another thing that we're maybe interested in, and we're not going to talk about too much how to solve it today, but just so you understand where we're going, is because the leader gets to bid later, he gets to see a little bit more of the price data. And as an auction theorist, that makes the auction much less efficient. And the idea is that if the price goes up, like here, the price went up, he'll get outbid by the guy who bids later. If the price goes down, he's actually overbid. This causes what we call unraveling in financial markets, and it makes the market much less efficient. So what happens? How do we fix that? Well, if we could hide the Oracle update from the leader, and we had censorship resistance, you can do a mixed strategy if you're the player who acts earlier. And that mixed strategy will allow you to still play the game without that complete unraveling that we're worried about. And moreover, the less time advantage you get, the more we IBRL that difference between the leader and the Oracle updater who's not the leader, the less distortion there is in this mixed strategy model. So that gives us two properties that we can formally define that we're trying to achieve. And today I'll be talking about how to achieve selective censorship resistance. It's very simple. When you submit a transaction to the chain, either you should get in or nobody should get in. That's fairness. Another property that we might want, and it's related to the mixed strategy that I talked about, is hiding. And there's two definitions up here. One of them is valency, which is, you can sort of think of like finality, but before any node knows it's final. Just means the last slot such that no matter what happens from that point onwards, the things in the log are going to get confirmed. And that allows us to define a hiding property, which could also be called pre-trade privacy. Basically says that an adversary can't guess what's in an honest leader's block before the protocol becomes valent. So let's talk about how to actually achieve that. Stop talking about what and start talking about when and how. Here is an example of the modified flow that we would have going from Alpenglow to Supernova Part 1, which is the kind of minimal version of MCP that will get us to multiple leaders and censorship resistance. Every box on here, as Brennan said, he had a similar graphic, is a validator. They're just chosen to participate in different roles. And as you can see, in Alpenglow, that's also the case. So we have clients sending transactions to a leader. That leader sends shreds to relays or turbine routes. And those get sent to validators who vote and participate in Alpenglow's voter consensus protocol. So the flow is actually quite similar in Supernova Part 1. The client sends transactions to proposers. Now there are multiple of them, as we hoped. We ended the leader monopoly. Those proposers each send shreds to the relays or turbine routes. And then those relays immediately forward those shreds to the validators as they do today in the retransmit stage. Hopefully, if you're running Agave, you're using zero copy, so that happens faster. But another thing is happening. The relays are sending one more message, which is an attestation to the leader. And the leader is aggregating those attestation messages, and that's the block that we actually come to consensus on. And I'll talk in a little bit in more detail. That'll be the most technical part of my talk, is how does that happen. So just as a recap of Turbine, we use this core technology called erasure coding, which is super sick, and it's one of the coolest parts of Solana. It lets us drop some packets and not be too worried about message delivery. And the structure kind of looks like this. You shred the block into erasure-coded packets, you send it to the relays or turbine routes, and they broadcast it on to everybody else. We're keeping that same structure here, only we have multiple proposers. They each create a block of transactions, shred those blocks into erasure-coded packets, and send them to the turbine routes or relays. Then those relays will immediately broadcast them onto the validators as they do today. But another thing they will do is they will send messages to the consensus leader about which shreds they've received. They will send signed I have messages, and we call those relay attestations. They're attesting to which shreds they've received. Now the consensus leader, let me just go a little bit into what that is. Basically, it's just a mapping, just a dictionary between what proposer 1 sent in the root of their shred. So all it is proposer 1 sent this block. That's just the digest of the block or the block ID. So once you have sent all of those to the consensus leader, it's the consensus leader's job to pack an aggregate block, which has an aggregation of the attestations. That's what actually gets sent out. What does that look like? Well, it's just a matrix aggregating those attestations in the structure that you see here. So once they send that out, validator's job is to vote in Alpenglow, in voter, but we have a slightly different voter validation protocol here. So first of all, the aggregation must include an attestation from at least 60% of the relays. Second, if any block has 40% of shreds present in the aggregation that are valid, then that block is scheduled to be included. If it has less than 40%, it won't be included. And then if we have 20% shreds, that means that we can reconstruct the block. And all validators reconstruct the block locally and make sure it reconstructs before voting. And they can do that without a delay because they should have received the shreds already. Now, what do we do with all these proposals? We take them, we order them by priority fee and dedupe them, and then we execute them in order with some additional fee payer checks to prevent DOS. So that's basically the whole protocol. And what we tried to do with this is basically give the minimal thing that gets us to censorship resistance as fast as possible, but is also safe and live. And as I said, we've been through so many of these designs. So on the top, you can see Alpenglow here, and it's great. It's provably bandwidth and latency optimal, but it doesn't have censorship resistance, which is what we're trying to achieve. A couple of years ago, we proposed a protocol called multiplicity that worked with Tendermint. The key issue there was that the proposer, the leader still had too much power to censor proposals, so we didn't achieve that full censorship resistance property that we had. Braid was a proposal where each thread was a separate consensus algorithm. The issue with that is the intricacy of consensus means that each consensus thread can sometimes hang, and so you go at the pace of the slowest chain. That's that log k factor there, which can sometimes be pretty bad. Then we had this other thing that I think maybe totally suggested at some point, which was, what if we just send all the blocks on Turbine and then we vote on the aggregate of them? The issue with that is it multiplies the failure rate from Byzantine nodes by a factor of the number of proposers. In Chicago, at Core Dev Day, I presented this protocol called GNR, and it was kind of almost what we see here. The issue was there was a kind of slight liveness issue, and then there were some latency and bandwidth issues. We fixed them in Supernova Part 1, and so that's what we want to bring. As Brennan said, we're collecting the receipts of everybody who says we're not going to be able to ship this thing quickly, and I will be posting them on Twitter. So you have 5 minutes to delete. I'm going to go backstage and save the folder, OK? Thank you, guys.
All right. Thanks, Max. The next one from the Anza block, we got Alexander Meissner. Alexander, come on up.
Cool, nice to see you. So today I'm going to talk about all the things you need to know for the next roughly half a year that we're going to change. Because we at the SVM team, we develop SDN in place, the SVM. So What we try to do is improve mostly bandwidth and performance in terms of throughput. There's not so much we can do in terms of latency, unfortunately. We try to reduce protocol complexity, which helps mostly other validator implementations like Firedancer catching up. And also it reduces attack surfaces and therefore improves stability and robustness. And finally, a point which we have been ignoring a bit too much in the past, which we're trying to do better now, is improving usability for you guys. All right, but unfortunately, all medicine has side effects, and there are things we need to do, and specifically also you need to do, so that we can unlock the performance gains and the robustness gains we want to have on our chain. Specifically, we are going to introduce, mandatory for all programs, even the deployed ones, a few new restrictions. All of these should not be done in sane programs, but for some historic reasons, they are, for example, part of the SDK or have been. So please test your programs with a recent, or hopefully the most recent test validator, and all feature gates enabled. And some of you will see these 3 error messages. And the fixes for them are pretty simple, but they need to be fixed. Specifically, I want to call out programs here. And if you find yourself in there, that means that your program is not going to break entirely, but some of the instructions will fail. So please take a look and run the latest test validators. So, but again, there's an upside to all of this. What we're planning next after that is so-called ABI v2, which will allow us to expose most of the transaction information all the time, basically for free. That includes the signers and all the pub keys in a transaction. We will change that you will have to do account metadata changes through syscalls. That means you have to kind of adjust some parts of your program. In turn, you gain basically unrestricted resizing of accounts, no more limits in terms of 10 kilobytes. You get a lot cheaper entry points, you get a lot cheaper CPI, and a lot simpler CPI. So we're getting rid of account info. And we're also getting rid of the pub key and the account meta, which will be replaced by an index. So furthermore, we're going to introduce SBPF v3, which for you guys mostly just means you have to recompile your program with the latest toolchain once. And that should be it. There should be no changes to the actual source code. And hopefully then your programs will simply become much smaller. And furthermore, it will also allow you to use more different toolchains because we're much closer to other eBPF toolings, especially the upstream LVM. So then we have further protocol complexity reductions. Specifically, the loader is going to change. There will be an overhaul of the upgradable loader. That means both inside how the account layout works, we have to do that to unlock some performance gains in the validator, and also to what specific actions you can do in the upgradable loader. The entire thing is codenamed loader v4. If there will be an actual change to the owner, we don't know yet. The thing will be opt-in in the beginning and then become mandatory later. Specifically, I think what a lot of you are looking forward here is after that, you will be able to completely close and reclaim program accounts, including the address and including all funds, like entirely deleting the account. And existing workflows like the buffered redeployment will continue to function. All right. Further improvements we want to do for you guys. There has been a lot on quite a rise in increase in interest for debugging specifically, and also for code coverage tooling. So we have been working with our partners and trying to improve the situation there. And I think we're close to enabling debuggers to even go through CPI throughout an entire transaction stack. Furthermore, there have been some smaller changes. For example, there is this issue that you have to pass all the instruction accounts before you get to the instruction data. We now also pass in the instruction data pointer as one of the arguments. So you will be able to first discriminate your instruction and then pass your instruction accounts or skip them entirely. And now the most interesting part probably is we will be able to raise the limits of the CPI nesting depth from 4 to 8. And we will be able to raise the number of instruction accounts in CPI from 64 to 255, which means you can CPI all accounts simultaneously of the entire transaction at once. All right. Finally, a few things which we are looking forward to in the future is we're still on the mission trying to basically migrate all the built-in programs we have to core programs being deployed on-chain in BPF itself. And specifically, that includes, like I mentioned, the loader. That also covers the vote program and the proof program. And we have been looking into potentially exploring different ISAs or more compiler options and a few more complex performance optimizations, which probably are not too interesting for you guys. But if all of you have anything that has always been on your mind, like this is the feature I need in the SVM, and I've been dreaming of this all my life, essentially, then please come to us, meet us on Discord or on the Simd discussion groups, or simply after the talk. You will see me because I'm wearing red. All right. Thank you, guys.
On time, and we got some time left. All right, so the next one is going to be an interesting one. It's the team from Anchor. Robert and Jacob, come on up.
How's everyone doing? All right, so we are here to talk about Anchor, where Anchor is today and where we kind of see Anchor going in the future. So for those who do not know me, my name is Jacob Creech. I do developer relations at Solana Foundation.
My name is Robert, and I'm the CEO and auditor at OtterSec.
Yes, so as developer relations, one of the things that I really care about with Anchor and with Solana in general is I want to make sure that we have the absolute best developer experience, tooling, and also the most optimal way of building Solana smart contracts or programs today. And so that's a lot of what I want to see on Anchor, and we have a lot of work to do, but we'll talk about that a little bit today.
So I said this at MEVCamp, actually, but one thing that we really hate as auditors is framework proliferation. And in the past 1 or 2 years, one thing that we saw was every protocol, or not every protocol, but a lot of protocols designing their own frameworks. I think we saw 2 or 3 custom frameworks launch in the past 2 years. One thing that we're really excited to do when working on Anchor is to take all of those learnings from these separate frameworks and bring them into Anchor. Having different frameworks increases the complexity, not just for developers, but also for auditors. It takes a lot of time to learn the nuances of each different framework and also to understand where it can go wrong. If you have 2 or 3 different frameworks, you need to learn each one individually. And one reason we're so excited to work with Jacob here from Foundation on Anchor is because we can consolidate everything and make Anchor, the one framework to rule them all.
Yes, and with that, we are excited to announce that if you can go out and try an Anchor 1.0 release candidate right now. It is actually released. Don't check the release time. It'll be very fun.
It was like 20 minutes ago.
Yes. But we're going to talk a little bit about what goes into the 1.0 release. Please try it out. Give us some feedback before we can actually make it a full 1.0 release. It's part of a release candidate, right? But The idea for Anchor 1.0 is that it is a step in the direction of what we just said, right? It is a stable version. I know a lot of people have had issues with Anchor in the past. It's a stable version that you can rely on to build Solana programs for now and for the foreseeable future. So let's go into some of the changes that we can see on it. Go for it.
OK, so if you're a developer, maybe you don't care that much about this. But if you're an auditor, hopefully you're super excited. One of the things that has been super annoying in Solana development in general, but also in Anchor, is duplicate accounts, and specifically duplicate mutable accounts. This is a super common foot gun in Solana, where you can pass the same account multiple times. And in Anchor, what this does is only the last account persists. And the reason for this is a little technical, but essentially the Anchor exit handler will serialize each account in order. But because it's doing these sequential serializations, only the last version of that duplicate account gets serialized back, which means, for example, if you have like a token account and you're transferring tokens, only the second version of that token account gets persisted back into memory. And this is a huge problem because a lot of Anchor developers don't know about this. And it's a very common foot gun that we see as auditors that we have to manually point out and remind developers. And it's been the cause of quite a few critical issues that we've seen. So in Anchor 1.0, this will no longer be a thing. You can always opt into duplicate mutable accounts, but by default, the framework will handle this edge case for you. It will prevent you from passing in two accounts of the same pub key into two separate Anchor accounts.
Yes, and as part of making Anchor stable, we're also going to be upgrading Borsch. So Borsch is currently in the current version of Anchor of 0.32.1. It's kind of like on a 3-year-old version of Anchor at this point, and it actually can't work today with Solana SDK 3.0 or higher. So we actually had to upgrade it to a V1. So this will not only allow us to make sure that we are stable from now into the future, but it will also make sure that we don't have all these weird dependency conflicts just suddenly in a 1.0, because no one wants that kind of issue. And on dependency conflicts, one of the things that we wanted to also talk about with Anchor V1 is that Anchor, part of V1 is it's not just a framework anymore, but it's also a tool chain in itself. We have a bunch of different tools within the ecosystem that people use today. We have Surfpool, right? A lot of people, if you're not using Surfpool, go use it. It's awesome. But Surfpool is an awesome little Solana test validator, which is a direct upgrade from the current Solana test validator. We have a lot of people using LightSVM or Mollusk or a bunch of other tools in the ecosystem. A lot of people use verifiable builds. What we did this time around is we packaged all those tools all under Anchor as the tool chain. And not only can you use Anchor to build Anchor framework programs, but you can also use Anchor with all these tools with your native programs, your Pinocchio, whatever, and it should build and work just fine. What's also great about this is in Anchor 1.0, everybody kind of talks about like, oh, I ran into dependency issue with this library or dependency issue with that library. What we kind of did with this is instead of having this mix and matching of a Solana CLI version, a platform tools version, an Anchor version, you would just have to know the Anchor version. Because in Anchor 1.0, we removed the requirement of the Solana CLI, and we also have the platform tools version tied to the Anchor version as well. So you don't have to worry about that. It will just work whenever you build. That's part of being stable in Anchor today.
Yeah, I mean, that was super cool. I mean, I feel like we can't overstate how amazing this is. I mean, there's been countless times where we're trying to audit a program, and I'm like, how do I compile this thing? Because of all the different versions of tools that you need. And yeah, we're going to talk a bit more about the toolchain later, but this is, I think, a super great addition to Anchor.
So as part of getting to an Anchor 1.0, we did a lot of work since we took it over this year to actually get it into a maintained state. So we did, as you can see from this graph, you can basically see when both Robin and I started working on it, especially on the issues closed part. Thank you also Henry, if he's in the crowd here, for helping us out. He helped us a ton as well. But we wanted to make it into a maintained state so that if people are making new contributions or they want to make an issue or they want to contribute back, they can. It's a lot easier. So we have under 100, under 100 PRs open now.
Yeah, we got under 100 PRs finally.
Yeah,
it was like 300 for the longest time.
Yeah, it was a big cleanup. We moved a bunch of things in that have been sitting forever. But we really, if you are in the crowd and you had problems contributing back to Anchor, please open an issue. We can talk it out. We are here to maintain it and make it better.
Another thing that we've been doing is trying to involve the community more. I think a big part of what makes Anchor successful is the fact that everyone uses it, and we want to be mindful of the impact it has on everyone's development cycle. If you have thoughts or feedback or ideas for where you want Anchor 1.0 or 2.0 to be, you should join our community calls. We host them once a month. We skipped it for this month because we're at Breakpoint, but next month will be on January 14th, and we host it around that time every month. And both Jacob and I and other people from the team are there, and we want, again, to hear your feedback, to hear what you have to say, to understand your pain points, so we know what we should be doing to make it better. And I think, as Jacob said, we are really putting in a lot more effort to maintain this thing, and we want to engage the community and understand how we can make this the best version of the framework it can be. Sort of on that note, a lot of people don't know this, but Anchor actually has been audited. We audited some of the previous versions, and we're auditing the 1.0 release. If you want, you can go to the URL on screen to see the audits. And we're also working on the security lifecycle for Anchor as a whole. So we launched a bug bounty program where you can email your issues or ideas. Actually, they go directly to Jacob and I. So we will see the issues if you have any, and I actually check my email and respond to them relatively quickly. So I think the point here is that if you have concerns or ideas or anything that you see on Anchor, we're here to look at them and here to help. And we really want to make Anchor the best it can be.
On that note, we wanted to also talk about, so we talked about Anchor of where it is today, right? We wanted to talk about where we want Anchor to go in the future. So there's a whole bunch of things that we talked about at the beginning of hey, we want to make sure it's the best developer experience. It is able to do all the things that these different frameworks are doing, or that are being built today are doing already. It can have good defaults. It can have, it's optimized but easy to move to something low level like Pinocchio, rather than there were some teams in the ecosystem that spent 8+ months moving their programs from Anchor or native to Pinocchio to get the extra juice out of their program on chain. And so we want to make that easy. So as part of that, the first thing that we want to do is we want to switch out the internals of Solana program with Pinocchio. You may have seen me talk about this every once in a while on socials, but that is really important to us because one, it gets us almost no dependencies, but two, it also makes it very easy to optimize. And then we're going to also make, instead of Borscht and a bunch of the other work that goes in today, we're going to make zero copy of first class citizen within Anchor v2 so that you don't have to worry so much whenever you're doing the loading of accounts or the writing of accounts, that sort of thing. So that is a big effort that's going on right now so that we can get this v2 out the door and make sure that, hey, if you want to use Pinocchio, you have both the optimization that Pinocchio provides, but also the best developer experience that you know and love from Anchor.
One important theme for us around Anchor v2 is also making it extensible. We want this to be the framework that all developers can use regardless of your skill level. And that we have worked with developers who have built their initial programs on Anchor. They realized they wanted to get more control over the framework, and then they couldn't get that with Anchor. So one of the things that we're adding along this theme is a better trait-based system, where if you're a developer, you can override parts of Anchor to get exactly the functionality you want. So for example, if you don't want to use the default entry point and you don't want to use the default account parsing, you can now override that in Anchor v2. If you really want to optimize, for example, if you're a prop AMM and you really want to optimize your Oracle updates, you should be able to do that in Anchor v2, where you only have to opt into the parts that you actually want to. And the goal here is, and the hope here is that regardless of your level as a developer, you can use Anchor. And it can be the framework that you stick with. Another thing that we're really excited to announce is Anchor Fuzz. So we want to bring native fuzz testing to the Anchor framework. Fuzzing is an immensely useful tool. And we think every developer should be able to access it and write it, similar to how you might write a unit test. So as part of this, we're adding, this is a screenshot from the test instance we have, but we're adding a suite of CLI tools where you can create a harness, you can run the harness, you can check the coverage, you can check your crashes, and you can see, sort of get all the features you expect of a normal fuzzing tool. We don't have that much time today here, but if you're interested in learning more, we're actually going to, or someone from the team is going to be giving a talk at the Dev Cave tomorrow. I don't know exactly what time, but he'll be there. Also, the Dev Cave is a little hard to find, so if you don't know where that is, it's like you go into Breakpoint and then you take a hard left, and it's on floor 1.5. So not floor 2, it's like 1.5, and it's like kind of stuck in the corner somewhere. We're also hosting a CTF there, so if you want to compete and you want to win some prizes, I think that the top prize is 30 Sol, which is like $4,000. But yeah, if you want to compete and win some prizes, definitely encourage you to go there and check it out.
So also on Anchor Fuzz, it's part of, if you remember, I'm talking about making Anchor also a tool chain that you can use to build programs. This is just going to be put in. So this is not specific to 2.0. We'll also add it to a 1.0 eventually when it gets built and fully released. So you'll have like a 1.1 or 1.2 or something at that point. It's just building the best tool set for you as a developer to build your programs.
Yeah, one thing we need to figure out is the disambiguation of the naming, right? Because there's Anchor, the framework, and then now we have Anchor, the tool chain. But that's a tomorrow problem. Another thing that we're excited to talk about is linting. So this is similar to the fuzzing, where we want to bring more, we want to increase the water level of security in the Solana ecosystem. And adding more features to the Anchor toolchain is one of the best ways to do that. So we're also excited to announce Anchor linting, which is a DY-lint-based linting framework. Essentially, it's static analysis. So we have hard-coded some rules for Anchor programs. There's, for example, maybe you want to check for reloading an account after a CPI, which is a pretty common footgun that a lot of new developers miss. We want to write these rules and then enable everyone to run them as part of their product lifecycle. So before you submit your code to an audit, you should be able to run Anchor lint, pull down the latest rules, see how it looks, and fix them before you even submit it to an audit. Another thing that we want to do with this is to make it open to everyone. So you don't have to use our rules. Anyone in the community can contribute rules and add rules either to our repository or even self-hosted. And Anchor lint will give you ways to pull down these community rules and run them on your project. So if you have ideas for interesting bugs that you think we should be looking for, you can post your own rules, and everyone in the community can use them.
Cool. So thank you for coming to learn about Anchor. If you have any questions, feel free to message us on Discord. You can see our two usernames right there. Or join the Discord for Anchor. Join the Anchor contributors channel and start messaging us. We're happy to have a chat on any new features or any problems that you might have building with Anchor, especially as we build towards V2. But thank you, everyone.
Jacob. So now it's my pleasure to welcome Francisco Piccoli, the co-founder and CEO of Almanex. Come on up.
Hi, everyone. I'm Francesco, co-founder and CEO of Almanex. At Almanex, we're building an AI security engineer that can help teams building on Solana ship code without bugs and catch any bugs before bad actors do. We're soon going to have trillions of dollars moving on chain, from life savings, real world assets, and institutions building products on Solana. Blockchains are becoming critical infrastructure. Solana is becoming critical infrastructure, and projects on Solana and protocols on Solana are critical infrastructure. And so we need the best defensive tools we can build to prevent bad actors from exploiting this critical infrastructure. So we're soon going to have superhuman capabilities in many different fields. And at Almanex, we're building superhuman capabilities for security. We are a team of AI and security researchers based in New York. At my previous company, I investigated some of the largest hacks and exploits that ever happened in crypto. And I grew frustrated because a lot of teams were not taking securities seriously, or they were shipping bugs that companies that were well-known and companies that like the folks before me can help catch. Unfortunately, audits are very expensive as well, right? And so having a tool that runs continuously during your PR process is something that we thought was needed, and ideally having like an auditor available 24/7, available via API. My co-founder was at Coinbase, and we built a team of folks coming from all across the industry. There's a few trends that have been worrying me quite a bit recently, and vibe coding is one of these. Like, we entered this age of vibe coding where literally teams are shipping millions of lines of code a day. We have companies like Coinbase and Google that are generating 40, 50% of their code, accepted code via AI. Cursor alone, this was like a statistic from April. They're pushing, their users are actually like pushing 1 billion lines of accepted code a day. Those numbers are only going to grow from here. And so these, unfortunately, produces massive bottlenecks, right? Because if we're moving towards a stage where teams are shipping entire vibe-coded apps, and I was just talking to the co-founder of another security company backstage, and they're seeing programs and smart contracts also being vibe-coded. Who is checking that there's no bugs, or there's no malicious code that is being injected, or simply buggy code that is making it into production? Today, security and engineering teams are literally swamped with alerts from static analysis tools. They do some fortunately, they often do audits. They run bug bounties. They have other tools, but the massive amount of alerts that they get makes it very hard for them to go and then triage and then pass it to the engineering team to go and actually patch these issues. And so often, especially large organizations, we see that what actually gets patched is not the entirety of what gets caught, right? Because there's a lot of noise. And so you guys, how many of you guys have seen the recent Anthropic report that were released around security? Quite a few, right? And it's funny because they released two recently. The first one that they released talks about cyber espionage, and it's a large-scale cyber attacks that they took down from Chinese state-sponsored hacker, where these bad actors were using AI in their exploit. And then a week or 2 weeks after, they released another report where they used AI to exploit smart contracts deployed on chain. And it's getting kind of scary, right? These models are getting to abilities of very thoughtful and very senior security engineers. We're not there yet, right? We're at this moment we're probably at the level of junior security engineer, but if the trend continues, we're soon going to be at superhuman ability when it comes to security as well. And there's some hints around the Balancer hack, 120 million lost recently, where the attackers might have used AI in their exploits. And so that's kind of the main reason why we started Almanax. We wanted to build the best AI tools from a defensive perspective to teams that are building on chain. And so Almanax is an AI security engineer that scales with your code base, continuously reviews code, investigates and triages alerts, and help actually patch alerts and security issues at scale. I was supposed to do a demo, but I'll do a few slides so I have the clicker. We built a system that kind of reasons through a code base, no matter its complexity, like a security engineer would, right? And so in order to do that, there's multiple things that you need to do, because code bases are very large, context windows are small. And so you need to give these agents the ability to navigate the code base, right? And so when we start a scan, and when our customers start a scan, whether they're running on their full repo or they're running their CI/CD pipelines or PR review process, we create a threat model of the repo. We look at invariants. we create an abstract syntax tree, we create like a function call graph, so that the agents are able to navigate to different parts of the code base and understand like the logic of certain functions like a security engineer would. And so this runs 24/7 in the PR review process, but it can also like be used as a tool that runs like before an audit, for example. So we work with a lot of teams that are about to go and do an audit. We work with auditors as well. They're using these tools during like their review process. And then we also investigate existing like alerts and help like teams triage. If you're a large organization, you're probably running different security tools. And generally, what we've seen historically is that 90% of the alerts that teams get are false positives. And so you're drawn, like these teams are drowning in noise from like these alerts, and often they might like dismiss something that isn't really a false positive. And so what we developed is this system that kind of like does, with the context of the code base, does an automatic pass of triaging to help prioritize what to fix. And then the very last step is actually going and patching. And so if you have like hundreds of alerts or hundreds of vulnerabilities that are found, well, I hope it's not a program that you're about to launch on chain, because that would be very worrying. But if it's like a large like monorepo or a large code base, you want to be able to like patch at scale. And so back in the days, you would like the security team would pass all these alerts to the engineers. Now, like we can patch directly in line if an issue is like an easy one, or we create a draft PR. So we're working with like security teams today from like various protocols and like wallet infrastructure team, working with Privy, and we're working with a bunch of Solana programs, Solana protocols as well. And today, I want to announce our collaboration with the Solana Foundation. We worked very hard to build an agent that is good at understanding Solana protocols. It's good at understanding Solana programs. It has context on like Anchor. It has context on anything that matters when like building something on Solana. And as part of the collaboration, we're providing, and Solana Foundation is helping us like provide like 1 year of like free audits for projects that are building on Solana. And so this is the moment where you guys clap. I was like, this is cool. This is amazing. And with this one, I'll pause. You can get in touch. You can sign up. And if you want to see this directly on your code base, you don't even need to talk to me. This is my information. But you can go at app.almanax.ai, and you can run like an AI audit. And then we'll send you to some of the fantastic auditors that I see here in the space and in the audience, like runtime verification. But thank you, guys. I'm Francesco. I'll talk to you later.
Thank you, Francesco. All right, next we have Felix Wilhelm. He is the CTO co-founder of Asymmetric Research. Felix, come on up.
Hi everyone, thanks for having me. So my name is Felix. I'm the co-founder and CTO of Asymmetric Research. We are a Web3 security company, and we spend a lot of time securing Solana infrastructure, like validators or bridges, as well as like on-chain programs. And in this talk, I want to give want to highlight a couple of key takeaways about the state of Solana program security in 2025. So I think overall we are seeing the space maturing. So like the security of on-chain programs is improving, but we are also seeing some movement in the other direction. So I have a couple of like high-level things I want to call out, and then wrap it up with kind of a forward-looking statement, like how do we make sure we get this space into an even better shape. So the first thing I want to talk about is a bit like the onboarding story for new developers, right? So over the last 2 years, especially 2024, we have seen a lot of like new teams onboarding to Solana that develop new and complex on-chain projects. And on the one side, Solana is lucky that we have like the experienced developer teams who deeply understand the runtime. They know like the bug classes, they know the pitfalls, and they're able to write secure and highly complex code. But for like these new developer teams that maybe come from the EVM world, we see that they still struggle with insecure by default APIs and pitfalls. And I know there are quite a few auditors in the audience, right? And I think everyone has like these different type of bug classes that they're always looking for if they review code written by new teams, right? It's just stuff that's very hard to get right. We see basically the same mistakes repeated over the last 2, 3, even 4 years. My typical example is everything related to instruction introspection, right? Every time you look at like the instruction sysvar and try to reason about what happened in the transaction before or after you, that's really hard to get right, especially once you involve CPI. Related to that is like the extreme power and complexity of these SEC P and ED 25519 native programs for signature verification, right? They're very easy to misuse, very easy to introduce critical bugs, and I think every developer who has worked with them know how hard it is to make them secure on first try. On the framework side, I mean, the one thing that Robert and Jacob are fortunately addressing is like the pitfalls around the duplicated mutable accounts, right? Due to like runtime behavior and framework internals, you basically just lose modifications as soon as you work with duplicated mutable accounts. And then if you step away from frameworks, you run into different issues like bump seed, canonicalization is something that I think a lot of developers struggle with when they're newly on board on Solana. And I think an interesting example that we can publicly talk about was a vulnerability we recently reported to the Relay Link team. So Relay Link is like a intent-based cross-chain bridge. And on the Solana side, the intent here was run this ED 25519 instruction to verify signature, right? Use that to like protect withdrawal of funds. But the team didn't fully parse the instruction format out of the instruction stream. Instead, they would just take the sign-up hub key as well as the message hash out of hard-coded offsets. So these are like the yellow numbers you see when they access the instruction data. That's completely, or that's very broken. So you can relatively easy bypass that, get a full signature verification bypass, and steal all the funds in the protocol. I won't go through the full vulnerability and exploit, but you can check it out on our blog where we did a write-up when the bug was patched. Another topic that becomes more and more interesting as Solana becomes more mature and you actually have on-chain programs that are running on-chain for a long time, right? Is regression safety. So what we see normally is you have a core developer team that designs and develops the initial version of a product or a feature. Ideally, they go to audits, so they are confident in the security. The core developers know the code really well. They have a lot of insights about all the security critical invariants in the code base. The auditors have as well, right? Because they reviewed the whole thing. You launch into mainnet. Ideally, you survive. You don't get hacked. Maybe the project is actually super successful, and you keep running in mainnet. And then your developers might change jobs. They might retire, or they get promoted to management. And at some point, you want to introduce this small bug fix. You want to fix a weird issue that's not critical but kind of painful. Or you want to add a small feature, right? And that becomes where it's really critical. At this point, the knowledge you have about the code base might be stale. The developers that really understand this thing might not be available. So maybe a new developer, a really smart person, is adding code to this, just committing a small commit. You might also have an audit on this specific change set. But at this point, probably the auditor are also not familiar with the whole code base, right? Because this thing is 2 years old. And then suddenly, that small change can actually break security invariants in other parts of the code base. And to make this a bit more realistic, one example I wanted to call out was a recent vulnerability we reported in MarginFi, right? So this is a very mature project, has been heavily audited over multiple years, has a lot of TVL. And this commit basically added a new transfer to new account instruction, which if you review it in isolation is pretty simple. It doesn't have complex logic in it, does all the signer checks correctly. Seems pretty harmless. it turns out that it doesn't integrate well with MarginFi's flash loan functionality. So what you could do is you take a flash loan, you invoke this transfer new account handler on the account that's taken the flash loan, and then you never pay it back, right? You never have to pay it back. Instead, you just walk away with the money. So this was like a vulnerability that was introduced with a very simple change and could potentially like lead to a loss of like $160 million. So I think this shows like that a lot of the stuff we have on-chain is really brittle, and it's really important to have like defense in depth measures to make sure you don't introduce these bugs like 2 years after your launch. The other thing I wanted to talk about is the rise of CU golfing, right? And as you probably all know, there's more and more interest in optimizing compute unit usage of Solana programs. So think of like the stuff you see on Twitter or X, like Pinocchio, P-token, Humidify, also like Doppler for like really efficient Oracle updates. And on one side, this is great, right? This shows we are getting more and more experienced developers. It's a sign of a maturing ecosystem that like people get comfortable enough with the runtime to actually do the stuff and invest resources in writing optimized and fast code. However, as like a security team, this also makes you really nervous, right? Like very often, heavy optimizations and security are kind of at odds with each other. A lot of the CU optimization stuff is basically removing safety belts that you normally have just from like the memory safe language that you're writing your contracts in. So with unsafe code and assembly, you're removing like these memory safety safety belts. Assembly makes the whole thing harder to review. Ownership checks is something like if you really understand like the semantics of the SVM runtime well, you might think about removing some of these ownership checks because they are unnecessary. And obviously, a lot of the stuff you care about is like in the SDK, which is like heavily audited functionality. So we are seeing a lot of like rewrites and re-implementations of stuff that's not fast or not optimized, but where we are pretty confident that it's so battle-hardened that it doesn't have like critical vulnerabilities. And the thing with these safety belts is that you don't need them if you don't write bugs, right? So like the argument could be, well, I just write perfect code and then like everything is great. But even if you look at like kind of the projects that are developed by like the best people in the space, so you see even the best developers don't always get it right. So the two examples are here are like pull requests from Pinocchio and P-token, which are probably the highest quality code you can find in the space, right? Especially around like CU optimization. And the two pull requests here is like one is a bug where it's like there's an integer underflow in an unsafe code block, which leads to an out-of-bound write in a logging functionality. The other one is in P-token, and was basically around a missing ownership check that could lead to loss of funds during the processing of batch instructions. So if even like these really experienced developers writing these like really interesting programs struggle with like the security aspects of it, I think the average DeFi project should be really careful before deciding to remove like these safety belts and drive fast, right? So keep that in mind when you want to fully jump on the CU golfing train. The final thing I want to call out is around Oracle risks, right? So I think, as you all know, like DeFi runs on top of oracles for pricing informations. And we do think that the risk of off-chain oracle compromises is not really well understood by a lot of projects in the space. So by the off-chain nature of oracles, you can oftentimes not really inspect where the price updates are coming from, how much you can trust them, and how easy or hard it is to compromise them for an attacker, right? So our suggestion here is that developer should spend much more time thinking about how a corrupted price feed can impact a protocol. And this is, I think, mostly an exercise in defense in depth, right? And again, like the safety belt mechanisms, where you can introduce features like price limits or like an emergency halt mechanism as kind of like these defense in depth mechanism to make sure that like a malicious oracle isn't able to, or like an emissionless Oracle price update isn't able to completely rock your protocol. A recent example that has seen like surprisingly little of public attention was a compromise of the Moonwell DeFi project, which is like an EVM-based DeFi project. They lost over $1 million because of a malfunction of an unsupported Chainlink Oracle price feed, which quoted highly inflated prices for a certain asset, which was then abused by an attacker. And while in this specific case, the like monetary damage might not be super high, right? Just $1 million. We are pretty confident that like we are going to see more and more of these kind of attacks or compromises in the future, especially when the on-chain attack surface gets more hardened, right? Because an attacker is always going to look for like the weakest spot. So if like your on-chain code is perfect, then maybe like your Oracle provider is actually the weakest spot in your security story. So what do we do about that? Like how can we help to get the space into a more secure place, right? And calling out like Roberts and Jacobs talk about the new Anchor development, I think a great way to help improve the space is by building secure by default libraries and primitives. So Anchor trying to address some of the pitfalls in the framework around mutable accounts, but also introducing like helper functions to basically do secure signature verification in a very easy to or like very hard to misuse API. Will make it easier for people to onboard securely onto Solana. We're also investing heavily into improved tooling. I mean, the previous talk talked a little about AI agents, but also like tooling like static analysis, and the newly introduced Anchor fuzzing is hopefully going to help to make your projects more secure against like regression and new security vulnerabilities. And finally, we are also working on stress testing for Oracle compromises and misconfigurations. So ideally, developers should be able to kind of stress test an Oracle compromise against their mainnet deployment and see what actual damage this could trigger in their programs. Thank you so much for listening. If you want to read more about the issues I described, please take a look at our blog, where we always do like technical write-ups of vulnerabilities we discover. If you want to hear more about security in general, security on Solana, or fuzzing, please come to our dev cave. We have a Solana security CTF, where you can like play around with bugs like these. And tomorrow morning, we're also going to give talks about fuzzing on Anchor, as well as binary decompilation of like Solana on-chain contracts. So if this sounds interesting to you, make sure you step by the dev cave tomorrow. And yeah, that's everything. So thank you so much.
Thank you. Next, we have the co-founder of Neodyme, Sebastian Frisch. Sebastian, come on up.
So, welcome guys, welcome to this talk. I'm Sebastian, I'm the co-founder of Neodyme, leading security firm here in the Solana ecosystem. And today we will talk about control, especially about who controls Solana's funds. There's this saying in more conspiracy-minded communities, follow the money. Today we are going to follow the seeds to find the money. So this was our starting question. As security researchers, we want to work efficiently. So if the top protocols by TVL are secure, most funds are secure. And indeed, we again got a Pareto coefficient here, or I don't know how you call it, this 80-20 stuff. Indeed, 80% of the funds in Solana are locked up in the top 7 programs. But how do we actually find out what are the richest protocols on Solana? Is it Camino? Is it Jupiter? Is it Drift? They all got a lot of value locked, or is it squads? Take a minute, pause, and think about it yourself. Most of you would probably just go to some DeFi aggregator and check, but stay tuned. The data may not be that correct there. So how do we find it out trustless? To find this out, we have to understand on a technical level how smart contracts can control Solana funds. In Solana, we got the SBL token program, where all token accounts are stored. Those token accounts have a mint, USDC, Repsol, you name it, an amount, how much of that mint do we have, and most importantly, they also have an owner. This owner is a pub key, and then can be 3 types of pub keys. It could be a normal key pair, as you have it on your hardware wallet, on your hot wallet. It could be a seeded address. That's a bit of a lesser known feature. Think of it as PDAs for key pairs. Or it could be a PDA, a program-derived address. And if a token account is owned by such a PDA, it can control its funds. But what exactly are those PDAs? The goal was quite simple. We want smart contracts to sign for an address, so we can enable cross-program interactions, etc. And the problem is also quite obvious. The program cannot have a normal key pair, as I would do, because I would have to upload the key pair up to chain, and that kind of defeats the purpose of a private key. So the idea is we somehow allow smart contracts to pseudo-sign by deriving addresses from the program ID, which they then can invoke, and the runtime counts it as a signature. On a technical level, this is quite easy. We got 2 inputs. We got the seeds. This is just an array of bytes, so it can be quite everything, and the program ID, so the program that is signing now. And to find a program-derived address, we just take the hash of the seeds, the program ID, and a so-called PDA marker that is just a string program-derived address. And this hash is a valid PDA if it does not lie on the Edwards curve, which you see on the right. Because otherwise, if it lies on that curve, there could be a private key associated with it. It would be still quite hard to find, but better be safe than sorry. So this hash is quite simple. There's actually once was a funny loss of funds bug on Solana with this, because the hash domain, collision domain of those seeded addresses, which I talked about before, collided with the hash domain of PDAs. I think we wrote a blog post about it. If you Google PDA Neodyme Solana, you will find it. But sorry for the derail. Exactly. So now we know how program-derived addresses function, but we want to check which funds are controlled by which smart contract. So what do we need? We need token accounts, so we know where all the money lies on the blockchain. We need those PDA derivations, and we need token prices. Token accounts are easy. Just pass some snapshot ledger using Agave Ledger tool or something else, and extract all the token accounts, put them into a database, done. Next, prices. They are also quite easy to get. Just use some API I wrote. I later found out that it isn't that easy, because pricing of tokens is quite hard. You got a lot of wash-traded meme coins, etc. But you can filter that, it's doable. The really hard part is getting those PDAs, because they aren't materialized anywhere in the ledger. This information of PDAs on Solana is only available at the runtime level. So if you look in the Solana Explorer, you will see a pub key. You will also know that it's a PDA, because this pub key doesn't lie on the Edwards curve. But you won't know which program can sign for this pub key, and you also don't know how it's derived by its seeds. And there has not been a public database yet, so we set out to build it. How did we do that? Well, it isn't that complicated, actually. We just need to patch the runtime of the Solana Validator. Most programs use a syscall, or 2 syscalls to be specific, to calculate those PDAs. Sol try find program address and sol create program address. And they offload those hash calculations to the runtime, because it's cheaper to do it that way than to do it in eBPF. And luckily, we already had a patch-ready emulation of all Solana transactions. This serves as the backend of RiverGuard. It's a tool we built 2 years ago, which actually scans every live transaction that is happening on chain right now. And it mutates it according to known attack rules. And we check if some basic checks like account owner checks, signer checks, self-transfers are possible. You can check it out. It's free of charge, everything. But it was quite lucky for this use case, because we could quite easily patch the client. And then we just push the PDA seeds into a database. And now we got a database of all PDAs and their program derivations live. You can scan the code if you want. We launched this database public, so you can access it all the time. You can just put in the PDA, and you will see its derivations. It's quite cool. And we also built the teaser I showed you at the front, which program controls most of the funds. Are you ready? So it's actually squats. Most DeFi aggregators don't care about squats at all because it doesn't earn money, or not that much. But it has the most funds locked in all Solana smart contracts. Next up is Lend, then Jupiter Perpetual, Squats v3. And it's quite interesting. If you click on that on the website, you will get to a next view. Oh, congrats to everybody who did it right. You will get to the next view, and you will see in which token mints are those funds actually stored. And if you click, for example, on USDC, you will actually get to the view where you see this token account is owned by that address, which is derived by this seeds. And this is super useful. For example, the first, we can already see by the seeds that this program apparently is a multisig. Next one is probably the multisig ID. After that, the vault. So we exactly see how does a program function, even if we don't know the source code of it at all. Some interesting numbers to wrap it up. I thought it would be interesting to share how much of a mint supply is actually locked in contracts, in contrast to it's held in normal wallets. So most value locked in PDAs is by USDC, and it's about 14.6% of the supply. Next up, by total value locked, is Pump, and about 50% of all Pump tokens are locked in contracts. And for Wrapped Sol, for example, it's nearly 73% of all those tokens, which are held in smart contracts and not in any wallets. In total, we roughly have 25 million different PDA-owned token accounts, so quite a number. And our database currently has about 104 million unique PDAs stored. The top program by most PDAs owned is the G2TIP distribution program with 27 million PDAs. This database isn't complete because we don't have historic data. As I showed you, it's a dynamic process of getting those PDAs. But it should have the most common and most recently PDAs in there, and it's still growing quite a lot. That's it for now. Thank you for listening. Follow on socials, etc., and hit us up. I will be back in the hallway. Thank you.
All right. Next, we have the lead formal verification team member from Seratora. Please welcome Pamina Georgieva. Come on up.
Great. Hi, everybody. My name is Pamina Georgiev. It's now Georgiev. It used to be Georgiou, so don't be confused. I'm the formal verification team lead at Seratora. And Seratora is a Web3 security company. And we, among other things, do formal verification. And I will use the next 8 minutes and 40 seconds to try to tell you what that means. OK, so when it comes to code security, most of the times, DeFi protocols use all kinds of things in their security stack. They start with reviews internally and externally, of course, right? They do auditing. They do a lot of testing, for sure. Ideally, they also do fast testing, so at least they cover, a bunch of inputs, and don't only rely on just a few unit tests. However, still, to find bugs with fast testing, it's a little bit, a game of chance. So sometimes you're lucky and you find the bug. Sometimes you're just not. Now, at Seratora, what we do is we do formal verification. What that means is, that we actually try to mathematically specify the intended behavior of your code. And and then mathematically derive those properties from your code with the help of so-called provers. Okay, you might wonder, well, why do we need this in DeFi? There is real money at stake. And of course, you want to make sure that if you're handling money, that you cannot get wrecked. Otherwise, the trust is gone. And formal verification is basically the only way to guarantee any of that. Okay, I'll attempt to give you a small code example. Please bear with me. You can see here a tiny little program. It's a vault program. The only thing that it does, you can deposit assets, and it will mint shares for you in proportion to the total value of assets locked in the vault. And you can redeem the shares with the withdraw function, and you should get your fair share. Simple enough, right? Now, when it comes to computation of values of assets to shares and shares to assets, most of the time you need to use multiplication and division there. Now, when it comes to division of integers, that means there's also rounding in here. In this case, I introduce a bug. Usually, you want to make sure that when you mint assets or when you redeem the shares and you get out the assets, you want to make sure that you do not overestimate the amount of money that you pay out to your users, because that would mean in the long run, the last person to withdraw cannot get their money back. So in this case, I do exactly this, and I seal the muldiv computation rather than rounding down, which means that we overpay by approximately 1 token. Now, a very elegant property to show such rounding issues is to actually show that that your share value cannot decrease after any user operation. So in terms of code security, you really want to make sure that for any public-facing functionality in your code, you make sure that that assets divided by shares, so the value of 1 share, cannot go down. And on the right-hand side here, you can see a partial implementation of a prop test. So I just wrote it as a test, a property-based test. And rather than using the division, I use multiplication, just to make sure that in the test itself, we don't introduce any additional rounding errors as well. And I actually wrote a complete test harness for this example, where I just generate random sequences of deposits and withdrawals from 1 to 200 steps. And I let this run for 100K test cases, and I did not run into a bug. So unfortunately, even with 100K passing cases, that does not necessarily mean that you're bug-free. And the only way to actually guarantee it is to formally verify it. Now, in Satora, we have a nice Satora verification language for Rust that allows you to actually write something that almost looks like a test as a formal specification. So you can see here the same, basically the same thing as for the prop test for the withdraw function. We're trying to assert that the share value cannot go down. Now, formal verification means we want to check all possible inputs to your function, and it also means we want to cover all possible reachable states of your program. In this case, our state is very small, right? It's just assets and shares. So we need to make sure we tell the prover that we actually start in a state where that is valid, so to say. And we already proved before that a valid state in this case means a solvent one. So we assume a state where we always have at least as many assets as we have shares. This is proved separately, but this is how we cover every possible state that is reachable as a starting state for the formal property. Then we take the variable shares and we say it's a non-det. It's a non-deterministic value, meaning that it can have any value that a U64, an unsigned integer, can have. And then we call the function that we want to verify. And then we assert our property. This is just a short macro, but it does the same cross-multiplication as we saw in the test before. And this way, we can now run the Satora Solana prover. It's open source. The link here in the QR code actually leads you to our docs if you're interested. It's super easy to install. It comes with a command line tool, as you can see here on the left side. And you can run you can run basically rules that like the one you just saw. And as a result, you get a link. And that link contains the verification results. In our case, the verification result shows a counterexample. Now, a counterexample means we have one concrete state of values where our property is violated. So here we start in a state where we have 19 assets and 10 shares. Somebody wants to redeem 6 shares. And it turns out they get 12 assets rather than just 11, which would have been their fair share, thereby decreasing the share value. So the prover flags this immediately. This took about 30 seconds, if at all, with sending it off to the cloud and everything. And since we already know what the bug is, we simply fix it. We basically floor the Maldiv in the withdraw function. And if you want to take a look, I actually implemented a few other properties as well. You can scan the QR. It will show you the rule report as we usually do it at Satora. And of course, that was a very, very small example. But we did formal verification projects for quite some big names that you might have heard about already, such as Jito, Camino, Squats, Manifest, and also some work with the Solana Foundation itself. And we also do more than just formal verification at Satora. So Satora is really, we're a fully fledged Web3 security company. We do audits, we do design reviews, we do operational security. We help you with any security needs that you might have. And if you currently have any security needs, I just wanted to do a quick shout out for Arita's security subsidy program. They are funding up to $1 million for Solana builders when it comes to security, and Satora is part of that project. So if you want anything from audit to formal verification, please check it out. Thank you.
Thank you, Pamina. All right, so everybody, we'll take a short break. Everybody, please come back at 5:45 p.m. See you then. Thank you.
Welcome your MC.
All right. How's everybody doing? Yeah? All right. We got CEO of Real Labs, Marcin Kostazeva. Come on up. I think he's coming.
Hey everyone, thanks for coming. This talk is to unveil Sunspot, which is a toolchain that lets you run ZK on Solana without pain, or at least with the minimal amount of pain possible with the current state of ZK tooling. So first of all, let's talk about why should you care? Why is it even important to be talking about zero-knowledge cryptography? How can it help you in your own applications, in your projects? So we have a bunch of different things that ZK enables that are very difficult to achieve otherwise. First of all, private transactions. Obviously, we have things like mixers, which are really controversial. Maybe don't do them. But at the same time, we are talking about onboarding institutions on chain, for example. And the institutions are not going to be super happy about every chain analysis company being able to see what they're doing, what they're buying, what they're selling, and so on and so forth. Moreover, this is not purely about financial transactions. If you are building an on-chain game, you probably have the concept of some sort of fog of war, right? There is a part of the map, a part of the game state that should only be accessible to the player, but you still have to ensure that the player is performing moves according to the rules of your game, even though you cannot show what specifically they are doing. This is also something that's enabled and really only possible with zero-knowledge cryptography nowadays. Second, we have identity use cases. So many times you will want to KYC your client or like soft KYC them, at least make sure they're not a sanctioned person. But you may not want to get their entire identity card, or they may not want to give it to you. So we have solutions like ZK Passport, for example, that let you scan your passport and generate a zero-knowledge proof that says, I'm not a sanctioned person, and for example, I'm 18 years old, and not reveal anything else. Again, something that is enabled with zero knowledge. Web2 integrations. We have protocols like ZK Email or ZK TLS, TLS Notary, that let you certify that some Web2 data on some server in some HTTP session was given to you without revealing the exact contents of the data. So an example flow would be you log into PayPal and you show that you have performed some transaction. You've sent some money on PayPal. You generate a ZK TLS proof that it's been done, but you are not leaking any more information. You are not leaking the fact that this is your username, this is your password, and so on and so forth. And finally, scaling. We have lots of challenges on Solana with rent costs. You've probably heard of things like ZK compression from Light protocol. This is also enabled by the use of zero-knowledge cryptography. So I hope this convinces you that this is actually something you should care about. Now let's talk about how to actually implement something in zero knowledge. In particular, Sunspot uses Noir, which is a programming language for describing your zero knowledge cryptography logic. It's very new and very exciting. It's gaining popularity. There are many popular libraries, popular projects that are currently switching to it or being built from scratch on Noir. It's developed by Aztec, and it has a Rust-like syntax. It's very easy to pick up, very easy to learn. Probably the best-in-class developer experience that you can get in zero-knowledge cryptography nowadays. And yeah, there's a rich ecosystem of libraries and building blocks that you can pull in and you can use in your own projects. So it's actually becoming an ecosystem that enables you to do all of this. Some examples are ZK email that I mentioned before. So that's a protocol that lets you verify that you have received or sent an email with some particular contents in it and generate a proof that you can then verify on chain saying, yes, I've actually received this email. Again, this could be a transfer confirmation. This could be an Uber ride, whatever. and ZK passport, which is the go-to solution if you want to talk about user identity without revealing the identity. So now, what's the biggest challenge that we're facing with doing this on Solana? And the challenge is that the Bartenberg proof system, which underlies Noir, has really big and really expensive to verify proofs. They are not big in terms of normal ZK tooling, but for verification on Solana in particular, they are way too big to be usable. Someone actually built a verifier on chain, and just the rent cost was $30 to verify a single proof. So we've decided that this is not really the way forward, and we have to make it better. We have to solve this challenge. And the way we've solved it is with Sunspot, which is a toolchain that lets you prove circuits that were written in Noir, but they get verified in a different proof system. The proof system is called GNARC. It's based on Grove 16, but I call it Grove 16++, because it actually gives you more power. It's a better proof system than what you would normally do with Grove 16. In particular, it has support for what's called lookup arguments, which in turn are pretty much indispensable if you want to be talking about bitwise operations, memory checking, or other traditional cryptography primitives. And then from Sunspot, you can auto-generate a Solana verifier program. So you push it to chain, users generate their proofs, they verify them on chain. You can actually use this logic. So let's talk about benchmarks. Let's talk about how good this actually is. So our demo application is an SPL token that you can mint, provided that you have that you possess a passport that is not sanctioned. So this uses ZK passport under the hood. You tap your NFC chip on the passport. It generates a proof that, yes, I am not from a sanctioned country. Then you can mint a token. It takes 5 seconds to prove this on a MacBook Pro, which is really good, like compared to the traditional process that you would go through, which is really way more annoying. The proof size is 388 bytes, which for Solana, with your like 1 kilobyte limit of transaction size, this is really good, right? Like this still gives you 600 kilobytes of data that you can use for your actual business logic. And it costs less than 500K compute units. And this may seem like a lot compared to like your normal everyday use cases, but keep in mind that like it's 500K compute units to verify an entire passport and actually do something that you would normally offload to a KYC provider. So yeah, this is it, and this is my call to action. Please scan this or type this on your phone and build something today. And I mean today. I know it's a conference, but build something today. Thank you.
All right. Please help me welcome the co-founder CEO of Magic Block Labs, Andrea Fortuno. Andrea, come on.
Hello, everyone. My name is Andrea. I'm the CEO and co-founder of Magic Block. We're a team of 16 people. Our background spans from AI research to low-level system engineering, and we're on this mission to bring real-time elastic compute to Solana for what we think is going to be the next generation of fully on-chain applications. We want to enable every application to run entirely on Solana. A few weeks ago, we announced MagicNet, which was our canary network. It was supposed to be an experimentation network, but actually we realized that developers are already building production-grade use cases that are producing real revenue on Solana mainnet today. We process more than 1 billion transactions with 250,000 ephemeral rollup sessions across 11,000 unique active addresses. These are some of the cool use cases that are being built on Solana with Magic Block today. Banana Zone has actually been mentioned by Raj as one of the most interesting consumer app out there, and is obviously skewed more towards a degen crowd, whereas Rush Trade or BlockSwap are trying to replicate Robinhood-like interface that simplify the way that consumers interact with prediction markets or financial primitives. We have games that are going after real money platforms that are not processing withdrawal, or they're not processing them in a timely way. And therefore, users have to literally sue these platforms to get their money back. The reason why an app is better off if it's built fully on chain is because whenever the application logic is just really a set of smart contract, you have properties that you wouldn't have otherwise if you're building with a traditional server. Your app is verifiable. You know exactly what's going on with the application logic. It's composable with DeFi across the board. Your application is unstoppable. Nobody can shut it down. And it's permissionless. Nobody can prevent you from interacting with that experience. And most importantly, we think that that is going to unlock a whole bunch of revenue-generating opportunities for developers that are not possible in Web 2. You can take a fee off of the volume. You can take a spread off of a yield that is generating by lending the money that are in these platforms on Camino or things of that nature. Actually, for those of you that might not be familiar with how MagicBlock works, we pioneered a technology that we called ephemeral rollups. We enabled Solana developers to add an instruction into their existing programs on-chain to delegate arbitrary accounts into blazing fast SVM instances on demand. When you run this delegation instruction, a router pings all the available nodes across the globe, clone the state on demand, and allow you to run the state transition for that specific account into this particular instance at light speed. You can always interact with Solana by committing the state diff or committing the state diff and CPIing into another program for composability and more complex interaction with other programs. And when you're done with your job, you can just undelegate and commit back the final state. So effectively, it's like having multi-threading for your Solana programs. You can think of these as different threads, and you can delegate an arbitrary account, an arbitrary number of accounts into an arbitrary number of threads that run in parallel. And when you're done, you just collapse everything back to the main thread, which is Solana itself. It's not only about latency, it's also about customizability. We think that every application should be able to run on the runtimes that they prefer for themselves. Privacy, for example, is a plugin that we have which runs within a trusted execution environment. If you delegate an account within an SVM that runs inside an Intel TDX environment, you can get private state transition. Or you've seen before how important it is for financialized applications to get real-time Oracle price stream that doesn't have to pay transaction every time you update an account. And the same goes for VRF. If you need to build an application that has an insane throughput, but still wants to get provably fair randomness. These are some of the use cases that we're really excited about, and I'm going to run you through some of the plugins and some of the customers that we're working with. When it comes to trading, obviously for use cases like Flash Trade, Archer, or MaxBid, you can imagine how important it is to have 10 millisecond latency. They can generate a lot more volume, which means a lot more fees. Market makers that operate on a first-come, first-served basis can much more confidently quote tighter spread because they can adjust them whenever the market volatility increases. Co-location ensures the best possible latency. And I was mentioning before, these are not isolated environments. You can commit NCPI into other programs with what we call a bundle. And the bundle can either execute atomically or it doesn't execute at all. And then with TE, you can get really interesting dynamics for private auctions or sealed bids. When it comes to games, of course, the onboarding experience for newcomers is a lot better if the whole experience is feeless. It feels like Web 2. But they still can get access to native USDC or USDT across the board. And VRF is extremely important for these guys to provide provably fair games. And then lastly, for dark pools and private payments, we have a fine-grained programmable access control where you can specify on-chain exactly who gets to read or write over the delegated state. You can geofence the IP to prevent sanctioned countries, for example, from interacting with your private application. And the whole thing is still composable with Solana because fundamentally is all SVM based. Our vision is to enable every single application to be built entirely on-chain. And so I'm incredibly excited to announce 4 major protocol upgrades that we're doing that we think is going to bring us much closer to this vision. First, we're announcing a lightweight, first-come, first-served multi-threaded scheduler, which can run up to 50,000 transactions per second on commodity hardware. This can be run as a sidecar to an existing Solana validator, given the much lower node requirements. This is going to enable a whole bunch of cool use cases that are not possible on-chain right now. But there's one other problem that everybody's complaining about, which is storage cost. And that's why we're introducing, and we're excited to announce, that we're bringing account compression transparently and natively within AR. We teamed up with Light Protocol to enable the same benefits that account compression give you with a up to 200 times reduction in the storage cost of rent, while at the same time being able to decompress the accounts within the ephemeral rollup, which gives you a much better way to interact with those accounts. Third, we have a brand new cloning pipeline and transaction streaming. The cloning pipeline is the module within the validator that keeps it in sync with Solana, and is now much faster and much more reliable. And with support for streamings, users and validators can add an extra layer of redundancy and make sure that they validate the state, that is, the state transition that are happening within a specific ephemeral rollup. And fourth, we are deploying some of our TE nodes within military-grade data centers, underground facilities, 24/7 security, armed guard security, 24/7 monitoring, and a very, very strict operational security protocols. So these add a physical layer of security on top of the already secured hardware enclaves. As we progress toward our mainnets, the vision for Magiclock has always been to be a decentralized co-processing layer for those transactions that couldn't run on Solana today, and that instead are running on AWS, on a centralized server. We can completely replace those servers. The applications can host a node themselves, or they can rely on existing node operators that will have a stake and will get slashed if they misbehave, if they don't process the transaction the way they're supposed to be processing the state transition. And so, with that in mind, with Solana native deployment and development workflow, with real-time performance, with Web2-like storage and execution costs, and with opt-in privacy, we think we are well on our way to enable every single application to be built entirely on Solana. Thank you for listening, and remember that we're building in the open. Everything that we do is open source, so we'd love you to check out our Discord, our GitHub, and keep in touch with us on X. Thank you.
Amazing, thank you. All right, now we have the last speaker of the day. Please welcome the founder CEO of Kinetic, Grant Center. Grant.
Final presentation of the day. Last but not least, hopefully. I'm Grant. I'm the founder and CEO of Kinetic, and I'm here to present a new protocol that we've been working on. You guys have been kind of back-to-back, highly technical talks, so we'll keep this one a little bit more high level, and for the more technically inclined, you can go to kinetic.xyz/whitepaper to access all of the gory details. So who am I? I'm Grant Stinger. I run Kinetic. I was initially crypto-pilled by Richard Crabe in 2017, who runs a company called Numerai, and I've been building in the intersection of crypto and quant trading ever since at places like Polychain and Jane Street. Now I work on Kinetic. So lightning tour of the history of Kinetic. We'll blitz through it. We started building on Solana in 2021. Initially building NFT trading infrastructure. From that NFT trading infrastructure, we started working on NFT aggregation in the Solana ecosystem. And then from there, naturally, we got very excited about aggregation broadly. So DEX aggregation has become one of our kind of core pillars of our business. We have a live DEX aggregator on kinetic.xyz that you can access anytime. We have public trading APIs. We recently announced last week that we did a big integration with Titan. We have a number of big integrations coming down the pipeline right now. So if you work at one of these meta aggregators or a wallet or a trading terminal or any of these, would love to get in contact with you and help. Hopefully we can help get your users some of the tightest spreads on Solana. And if you run any of these underlying DEXs themselves, we would also love to integrate you, whether it's one of the brand new exciting prop AMMs or one of the OG DEXs. We're constantly doing these integrations, so please reach out. Kinetic is no longer just a DEX aggregator, though. We have a full suite of products. You can imagine Kinetic is a kind of verticalized trading platform. Our mission is very well parallelized with the rest of the Solana ecosystem. We're really here to accelerate internet capital markets on Solana. And so how do we do this? We, in this kind of vertical stack that we have, we built a fully featured platform. You can imagine the very top of the stack being our community. The community is really sort of the beating heart of Kinetic and is what the rest of the stack is all kind of building towards and is all here for. We're about 10,000 strong across Discord, X, and Telegram, and we're constantly running trading competitions and engaging with our community as much as we can. The next level of the stack, serving our community, is our UI. I would say we have one of the most cracked designers in the crypto ecosystem and an amazing legendary front-end team, shout out, has been doing an amazing job shipping a lot of product surface area for us. We have a mobile browser experience and a desktop browser experience, and these are pretty well balanced for us. On our kind of UI, you'll see many different ways to interact with the Solana ecosystem. You might start with the Discover page, where we have screening, filtering, searching, all the primary activities that you would want for sourcing new trades. We have a trench trading interface. We have all the analytics that you could want about pools and tokens. We have wallet tracking. We have portfolio management. We have ways to view other people's portfolios as well. We have a points program, leaderboard, contest. So we've built a lot over the past year, and we're continuing to build throughout. Next in this stack, you can imagine once you've generated a trade that you're excited to do, you've discovered this exciting new token that you would like to buy. The next level is the aforementioned DEX aggregator, which we are spending a lot of time on. And from this DEX aggregator, this is where we've built a lot of expertise in the Solana ecosystem around the type of architecture that we would want to see in a level deeper. So this is preamble for what we're launching today. We're launching a new market structure on Solana, a DEX of our own. And we're excited to kind of go to this deepest vertical that we've gone so far. So blockchains are natively discrete time in the way that they execute trades versus continuous time in traditional finance. And for a long time, that's been seen as a blemish for the crypto ecosystem, one to be powdered over. I'm very excited about the shred streams work and these types of details, and there are ways of sort of getting around this. But what if for a moment we considered what we used to consider as a blemish of the crypto ecosystem, this sort of discrete time nature of blockchains, if we considered it just for a moment to be a valuable asset? And you might look to traditional financial literature. You'll see there's been much ink spilled around frequent batch auctions. What are frequent batch auctions? They are related to, they're similar to, you might say, the opening and closing auction in equities, where everyone submits an intent to trade, an order, and at the end of the auction, everyone nets out at a specific price. And a frequent batch auction is just this done back to back to back to back over and over again. And one of the benefits of this is the high-frequency trading ecosystem spends hundreds of millions of dollars beaming neutrinos to the center of the Earth and kind of working on executing on the order of microseconds and these sorts of things. But there's no real economically valuable information that happens faster than, call it, 100 milliseconds or a second or something like that. Imagine if markets worked in such a way that once per second there was an auction, and it doesn't matter if you have the microsecond latency optimized execution infrastructure, as long as you place your trade within the second, everyone will get the exact same fair price. So naturally, that begs the question, how might we want to bring that to the crypto ecosystem? And so, as I mentioned, blockchains are natively discrete time. The traditional financial ecosystem, it's been hard to innovate on these types of things. I think there's a lot of regulatory capture and these types of things. So Solana, I think, is the perfect place to introduce frequent batch auctions. And so what are we introducing here today? So we are introducing SUPA, what we call our SUPA protocol. SUPA is an acronym, SUPA, Solana Uniform Price Auction. What are the details here? So in our SUPA protocol, it begins very simply like a constant product market maker, like you would see as one of the kind of primary crypto native market structures. But there are these frequent auctions that occur over and over again. And you can imagine in the same way that a pool creator might specify fee tiers, you could specify different auction durations. Imagine a one-slot auction, 400 milliseconds on Solana, once per minute, once per day, like the closing auctions in equities. You might end up with this sort of like hierarchical structure of these auctions and shelling points at right on the 4 p.m. Eastern and at the end of the hour and these types of things if you have multiple of these auctions. What are some other kind of upshots of a market structure like this? Well, imagine Alice wants to place $1 million buy of Solana, and nefarious Bob wants to sandwich her. So he buys at a good price right before her buy, and then sells right after her sell, capturing this sandwich profit. Well, imagine if everyone nets out within this auction at the same price. Bob is no longer economically incentivized to place this trade anymore. And so this auction structure prevents transaction-specific sandwiching in a very kind of positive way. So traders are benefited from this auction structure because of the sort of anti-sandwiching effects. There are also some details that we discussed in the white paper and much more detail around some of the potential benefits to LPers as well. Roughly, you can imagine running an auction right before an auction right before the closing of the batch, where some of the profits immediately go to the liquidity providers. This is what's potentially a LVR lever reducing mechanism for LPers, so they're losing less money by participating in this type of auction. Users are not being sandwiched in this way, and so it's a kind of much tidier and nicer market structure for kind of all of the participants all around. So I think this is a very rich design space and one that we are pursuing very deeply. And we launched the white paper, and when is the SUPA protocol going to go live? It's actually live right now. We just deployed it. You can go to kinetic.xyz to experiment with these pools. We'd love to get your feedback on some of the white paper details and potentially do integrations with some of the big aggregators or whomever might have interesting flow. So I'm Grant Stinger. Hope you have a wonderful day of the conference, and thanks for having me.
All right. How's everybody doing? This is the wrap up for today. Thank you all for coming, and we'll see you tomorrow. Thanks, everyone.